In 3, 2, 1. Welcome to APEC. It is July 11th, 2026, and I am your moderator, Tim Ventura. Thank you to everybody for joining us on today's conference call. Thank you to everyone who is watching us on YouTube. We are also live streaming to Facebook, X, LinkedIn, Instagram, I believe, several other platforms as well. We are broadcasting it all over the place, and I am very, very excited. Alt propulsion continues to grow. We are an open organization. We are trying to promote involvement, excitement, and trying to basically share the vision for emerging propulsion. So, again, thank you, everyone, for being involved. This is your conference. So today we have Al Baur starting us out. He's going to be speaking on advancements in electrostatic levitation. I'm really excited because Al has real working devices and he has new videos demonstrating those. After that, Gabriel Dias will discuss boundary condition vacuum interaction systems and ZPF tech research. Gabriel is working with Douglas Miller. Douglas did some presentations on stochastic electrodynamics, and he is pushing forward with startup development. And so Gabriel is going to be talking about some of the stuff that they do. After that, Jennifer Nielsen will be discussing torsion cavitation drives in the TUFTS model of physics. I am so pleased to have Jennifer back. I talk with her all the time in email. She continues to refine and develop her theories and models, and I am just absolutely pleased that she was able to join us. She'll be coming up in about 2 hours. After that, Denny Okudinani will be presenting on a brief historical and technical look at solid-state spatial mass displacement. Denny spoke at the last APEC. He is an amazing speaker. He is a builder. He goes deep in his topics. And so I begged him to come back, and I will continue to beg him to come back indefinitely. So a couple of quick updates before we get started. Today's event is on StreamYard. We are broadcasting through the Alt Propulsion YouTube channel. That's our primary. If you haven't subscribed, please subscribe now. You can ask questions using the live chat feature on the right-hand side of the page. We will try to ask them to our presenters depending on time constraints. The challenge with the live chat is those questions can scroll up pretty fast and get lost. So we do our best, but sometimes we miss those. You can also always view conference replays, details, and speaker info on our website at altpropulsion.com. I want to mention that and highlight that again, altpropulsion.com. I have been doing a lot of stories on past work that has been developed. So it's not just conference info. There is a wealth of information, science, physics, models, I guess, of propulsion. I mean, you name it. We have run the gamut in terms of, I mean, Searle effect on one hand to nuclear propulsion on the other, this whole wide range of innovation. We are trying to encompass that. And again, our goal is to promote the people with the ideas doing the work. So we are just a conduit and a community resource. Okay, so that was my preamble. Without any further ado, let me bring in Mr. Al Baur. Al, welcome back. Thank you for joining me. Oops, and you're muted, sir. Oh, actually, you were not muted. Your audio device is not working though. So there should be, and that's okay. We have lots of little technical bugs. Down at the bottom of the screen, there should be a little button with a microphone and an up arrow, and that'll let you choose your microphone. So if you see the little mic button at the bottom of your web browser, there we go. Okay, that's off and on. There should be a little arrow next to it. Try clicking the arrow. And it'll let you choose your device. Oops, and it looks like we just lost Al. So he may have logged out. He may be coming back in. So I should mention that Al is joining us from Israel. It is pretty late his time, so I want to thank him for that. I'm going to give him a minute to log back in, and if he's not able to make it work, that is totally cool. We can find many other ways to skin the cat and reschedule him if need be. So I love it that he is doing the work that he's doing and he's showcasing that. Okay, so let me bring Al back in. There we go, sir. Wonderful.
Okay, I had to bring in all my files.
Yes, I am terribly sorry, sir. I'm terribly sorry. I'm not sure what happened with the microphone. It does happen. StreamYard leverages, just for anybody who's watching as well as yourself, StreamYard uses the Google Meet functionality built into the Chrome browser. And there are some advantages, but also some disadvantages to that. So... Okay. And okay, here's your presentation. So I'm going to put that up. Wonderful. And as before, you can use the back and forward buttons. You've got the slide, you can scroll down or just do the arrow buttons. If you put your mouse over the slideshow, it'll have those. Okay. So Al, let me do this. Let me take myself out. And I would say take it away and thank you again. Just let me know if you need any help. And I will be here in the background.
Okay, thank you, Tim. Before I start my presentation, I want to tell a story. I was working for years in reverse osmosis, and when a group came to the plant, I had to explain how the plant was working, and inside this, I explained what water is. And water is made from H and O. The O is oxygen, and it was for me like a female. It is round, and it gives life. The H, it's a helpless male. And one of these talks, I explained why there's a need for two H's to make water. And then a politician came to me and he told me that I'm a dangerous man. Well, I won't explain what I say then, but what I'm going to do today is to show a different view on electrostatics, because electrostatics and electromagnetics, they are also a pair. And electromagnetic levitation exists already a long time. And it's, for me, a male. The electrostatic is, for me, a female. It's mystic, it's different, it's lighter, it's... and if you combine them, you get electromagnetic wave. What I want to do, I want to show you a different look on electrostatics and in relation also with anti-gravity. So for me to advance the electrostatic levitation, I ask always the question, what else I can do to make it more explainable? And this is what I'm going to do. So the first thing, how to measure the energy use of the levitator. Testing the quality of the levitator, and there will be a movie. The movie will be a little bit mixed up because I had to push videos together. Why the quality is important of the levitator? The use of conductive PLA and electrostatic levitation, EMP detector and AM radio for ion detection, and demo of two levitators in the same trajectory, relation between electrostatics and gravity, electrostatic force essential for creating planets, from Maxwell to Einstein, and the relation between gravity and electromagnetics. Anti-gravity research, wasteful or not? Okay, here's a picture. On the left side, we see a voltage, and in serial there is a 75 mega ohm. This is the internal resistance or impedance, and the 1.8 giga ohm, this is the load when there is nothing there. This is the load of the trajectory. So there is a loss because of this, and there is also drop of voltage. Okay, on the right side we see the same, but the orange is the load of the levitator, and we see again a drop in the voltage, and there will be, of course, a different current, and because of that there will be a different energy taken. By taking the energy of the left and reduce it from the energy from the right, I'm able to know what the energy is taken by the levitator. And from this I can calculate the energy per gram. What defines a stable levitator? A stable levitator exists the following characteristics. When the voltage or current is increased, the levitator moves faster, while its height decreased due to the corona wind. Okay, here, this is a very interesting, because if you ask today all AI what happens when you elevate the voltage, they will say, okay, it goes faster, which is true. But all of them say it will be pulled up, which is not true. When the voltage goes higher, the levitator goes lower. The reason is because it produces a stronger corona wind, and this wind pushes the levitator down. Okay, this behavior continues until the levitator contacts the bottom of the trajectory, so it's a control of the z-axis. When the voltage or the current is reduced, the levitator rises until it touches the high voltage electrode, the trajectory. If the levitator remains stable under the above test conditions, it will also function reliable in both low and high humidity, which is very low electrical noise. Moreover, it can operate with multiple independent levitators within the same trajectory. Additional requirements for stable operation includes elegant motion, free from wobbling, hopping, shifting, or vibrations, uninterrupted movement for at least 1 day at the speed of 0.8 meters a second. This corresponds with 70 kilometers a day. The frequency of the ions is around 200 Hertz. It is possible to see this as a little ionic explosion. The frequency is mostly determined by the internal impedance of the power supply and the capacitance of the trajectory. There are other values that can change it, like temperature and humidity, but the most is determined by the internal resistance and the capacitance of the trajectory. if the impedance of the power supply is low, so the internal resistance is not existent, then the frequency will be high. If you want to see a simulation, you can use the browser. I don't know what. Okay, this won't work. Okay. Okay, there's this browser. You can see a simulation on the electrical circuit. Practical example. Air at the atmosphere pressure of a 1 millimeter gap, ionization start voltage for air is 327 volt. Okay, this is the theoretical Paschen minimum for impact ionization threshold. Okay, the breakdown voltage, however, is higher. For the same gap, it's 3 kilovolts, since secondary process requires high voltage to sustain this discharge. Okay, this difference between ionization and breakdown is important for this technology, because one of the things that is believed to be impossible with electrostatics is that the breakdown of the voltage is problematic, which I will show it's not. In my case, where the difference between the height of trajectory less the levitation height is 110 minus 70 millimeter, this is the height of the levitator, which is 40 millimeter. 40 millimeter and the ionization is 13 kilovolt. 40 millimeter multiplied by 3 would give 120 kilovolt if I want to have a breakdown, which never happened. Okay, here you see different values and related in humidity, okay, and the minimum Paschen voltage. Here you see the influence of the frequency, and this needs confirmation. I invite Jules to look at this, if this could be possible, because it works. Okay. Here, if you push this this HTML, you will get a simulation and see how this works. Now, an AM radio or EMP detector useful to hear or see the ions. It's also a fast checking if a propellant-less drive is ion-free. So if somebody claims that there's a motion or propulsion by electrostatics without ionization, it's very easy to check with the radio. The levitators are handmade, and the process is to make multi-units and then select the stable ones. The unstable levitators are used for understanding what needs to be changed for the improvement. Even when I make the same levitator, the behavior is mostly different. Using the composite materials with 3D printer would improve the repeatability. These materials are heavier than momentary used materials. Okay, Tim, I want to show a movie. Tim?
Okay, yes, I am here, sir. Let me try this.
Is on the same trajectory. The blue one lies on the left, sprawled on the floor, motionless. Then the red one stirs. It begins to move. The hum of its ion thrusters breaks the silence, and the blue one wakes. Groggy but alert, it rises and drifts toward the red. They meet face to face, and without a word, both push thruster against thruster, force against force. The red one is stronger. Steadily, relentlessly, it shoves the blue one back. The blue resists at first, then falters. It gives up. The red levitator glides onward, alone once more. Now both move in the same direction, red ahead, blue trailing behind. But one is always faster. When the faster one draws near the slower, it doesn't shove with thrusters this time. Instead, it reaches out with its static field, the same field that lives inside both of them, and gently, firmly, pushes the slower one forward. No fight, no surrender, just the quiet law of their kind.
Okay. Creating a stable levitator is time consuming, and even when you have a stable one or even the same result, again, is difficult. By using the conductive PLA, I hope that repeatability will improve. If successful, this would make it possible to create more interesting flying objects. Currently, however, this approach seems problematic due to the material high resistance. The energy required is around 200% higher than that is needed for metal levitator. Conductive PLA is a specialized 3D printing filament that blends standard polylactic acid PLA with conductive additives such as carbon black, graphene, carbon nanotubes, or a carbon aerogel. This transformed the material from an electrical insulator into a semiconductor composite, making it, well, sensitive for voltage. Here you see a sample of this interconnecting levitators. The carbon-based levitator is capable of continuous operation, but the frequency is not stable. Okay, I explained before that the frequency is around 200 Hertz, which is dependent on the RC. Here we have a different situation. I will show that it's not stable with the oscilloscope. And the reason I believe is that the carbon works as resistor that changes when there's a high voltage, a variable resistor. Okay, it is, so it's overall not a high quality levitator. When the carbon nanotube becomes commercially available, this technology is expected to advance significantly. Just started to use carbon nanotube PLA. It takes a ton of calibration, still hunting for the perfect printing setup, which looks to be difficult. Regular PLA is cheap, and the carbon-based version is only twice that of normal PLA. But the carbon nanotube, that is a whopping 22 times the price, so it is expensive. So I show here a few objects. This is a trajectory part. It's also made from carbon, and there are wires on both sides to make it more homogenic in the conductivity. I hope you can see it. Okay, now, so you need also these kind of things to make it turn. Okay. So in the moment I stopped this, but it is technically possible to do because of the price difference in alternative materials. Okay, what I see here on the picture with the multimeter, the conductivity of is mostly given in S, in Siemens, is the inverse value of resistance, which is a little bit unpractical because the conductivity is a volume-related value, and because the PLA wire is always the same thickness, I take 100 millimeter and put on the both sides silver wire, and then check the conductivity for to compare. The carbon nanotube is much lower than this value, is below 1 kilo ohm. So you can ask, if you know something about carbon nanotubes, why the value is so high. It is because there's only about 15% carbon nanotubes in this material, because the most is materials that are related to polymers to help to carbon nanotubes to form. And so the resistance go higher. Okay, then I want to show another video.
A levitator shaped as a conductive chicken drifts through the air. Through the crackle of an AM radio, you hear the ions hiss and whisper.
Look at the
Glancing at
frequency.
the oscilloscope, you watch the random ionization dance across the screen, wild, unpredictable, alive. The double conductive levitator glides forward with an air of perfect balance. It looks stable, steady, even graceful. But don't be fooled. Beneath that calm exterior, something is wrong. A subtle wobble, a hidden tremor.
The levitator rises up on high. Through electrostatic fields it'll fly. A force that makes it move and float as if it were a mystic boat with levitation as its power. It defies gravity by the hour, a wondrous sight for all to see. As it continues on its spree, its magic is in the way it moves, as if it's dancing to its groove. A subtle sway, a graceful spin, as it glides on the air so thin. And yet the source of its great might is just an electrostatic light. A field that lifts it off the ground and lets it soar without a sound. So let us marvel at this feat and watch the levitator complete a journey through the air so free, a sight that fills us with pure glee.
Okay. Relations between electrostatics and gravity. How much stronger is electrostatics than gravity? This comparison is one of the most dramatic in all of physics. The short answer is that the electrostatic force is roughly 10 to the 36 to the power of 36 to 40 times stronger than the gravitational force. It's a factor of 1 with a lot of zeros. To put that in perspective, the difference is like comparing the width of an observable universe to the length of a single human hair, or the energy released by a supernova to the energy of a single mosquito in flight. How do we calculate this? The classic comparison is between the gravitational and electrostatic forces acting on two protons in the hydrogen nucleus, separated by a tiny distance. Here, for somebody who's interested, there are the calculations, and this gets us to 1.2 and to 10 to the 36. So the question is, why don't we notice the electrostatic forces everywhere? If it is so mind-boggling stronger, why is gravity the dominant force on the cosmic scale? Planets, stars, galaxies. The answer is cancellation of the charge. Positive and negative charges. Matter is made of equal number of protons and electrons. At the macroscopic scale, the objects are almost perfectly electrically neutral. The tiny gravitational pull from their mass adds up, while the enormous electrostatic force mostly cancels out. Gravity is always attractive. There is no negative mass. Gravity only attracts, so its effect accumulates over a vast distance and a huge amount of matter, eventually overwhelming all other forces at the cosmic scale. Range. Both forces have infinity range, but only gravity, due to its purely attractive nature and the lack of shielding, can shape the universe. Electrostatic is 10 to the power of 36 times stronger than gravity for a given set of elementary particles. Gravity dominates our world because it's always attractive and adds up over massive neutral objects, while the electrostatic forces are usually neutralized by the presence of opposite charges. Stellar and planetary interiors. Without electrostatic repulsion between protons and nuclear fusion would happen uncontrollable because the Coulomb barrier would be gone. So stars would either not form stable or would instantly explode. But let's ignore the stars for the moment. Even if gravity somehow pulled in a diffuse nuclear and electrons, they would not form distinct planets because the atoms themselves aren't stable. Now, here you see comparing the planets are made by electrostatic forces, not by the gravity. The particles that move inside space, they are attracted by electrostatic forces, and this is until it's got around a size of a diameter of 1 kilometer, and then only then the gravity starts to take over. Now, for to make it a round sphere, like a planet, it has to be at least with a diameter of 400 kilometers. This is the reason why all the meteors and things like that are not round. They are too little to be round. So, okay, picture. Okay, from Maxwell to Einstein and the conquest for anti-gravity. Solving the mass in terms of energy and vacuum constant. The energy equation E is mc by square. Solving the m, and then we got E divided by c square. The Maxwell equation with the speed of light relates to the vacuum permittivity and the vacuum permeability. What we get that C is 1 divided by the root of mu and epsilon. What we see here, that the square that was inside the formula of Einstein is removed, and then we get the C square. So, okay. Here we have the values of the vacuum permittivity and the vacuum permeability. Okay. Now, therefore, 1 divided by c square, it's the mu multiplied by the epsilon. So when you substitute this, you get that the mass is equal to the energy multiplied by the mu and multiplied by the epsilon. Both are the values that are considered to be absolute in vacuum. Okay, the vacuum permittivity is space willingness to allow an electric field. In simple words, how easy space lets an electric field pass through it. So epsilon 0 is the price space charges for letting electric field exist. Low epsilon 0 means a high price. Mu 0, the vacuum permeability, is space willingness to allow a magnetic field. Simple words, how easy space lets a magnetic field flow through it. Okay. Okay. The gravitational force between two objects is directly proportional to the product of their masses. So if you double the mass of an object, the gravitational force doubles. Why this is beautiful? The equation of m is energy multiplied by mu and epsilon shows that the mass and energy are the same physical thing, just expressed in different units. The conversion factor of mu and epsilon encapsulates the electromagnetic properties of empty space itself. In the hypothetical universe where electrical and magnetic fields behave different, the relationship between mass and energy would change because the speed of light would be different. So the question is, where could that be? Possible near black holes and for sure inside. And the changes that will be made on these two values is dependent on the size of the black hole. Change one of them and you have anti-gravity and time travel. But nobody knows how. Okay. Now, anti-gravity research, wasteful or not? For practical near-term engineering, yes, it is almost certainly a wasteful endeavor. But for functional physics research, is not wasteful at all. If looking for anti-gravity means trying to build a device that lifts itself or shields weight using unknown physics, then history and our best theories say it's a dead end. It violates our most successful theory, general relativity, has passed every experimental test for over a century. It states that the gravity is not a force like magnetism, but the curvature of space-time caused by mass and energy. There is no negative mass or negative energy density. In the universe that we ever seen, anti-gravity would require a source of repulsive gravity, which in a general relativity only allows for under extreme exotic conditions like negative energy density from the Casimir effect. On a microscopic scale, far too weak to ever lift a paperclip. The energy scales are absurd. To create a repulsive gravitational effect equal to the Earth's pull of 1g, for a small object, you would need a concentration of a manipulated energy on the scale of a neutron star or a black hole. The power requirements would be literally astronomical. The track record is 100% failure. Every claimed anti-gravity device from the Dean drive to the gyroscopic lifter to claim about the Biefeld-Brown effect has either been shown to be a hoax or misinterpreted of a mundane effect like eigenwind lifting and lightweight capacitors, or a simple measurement error. Spending money chasing these specific contraptions is wasteful. Conclusion. For engineering, if your goal is to build a flying car, a hoverboard, or a reaction-less drive for space travel, then looking for anti-gravity in a lab using current methods is guaranteed a path for failure and a waste of resources. If, however, you're looking for anti-gravity means asking a deeper question, is our understanding of gravity complete? Where does it break down? Then it is essential, non-wasteful pursuit. We know that general relativity is incomplete. General relativity and quantum mechanics are incompatible at the singularity of the black hole or the moment of the Big Bang. General relativity breaks down. The search for the quantum theory of gravity and string theory loop quantum gravity is a legitimate, difficult, and important scientific frontier. Some of these theories do predict exotic effects that might be misconstrued as anti-gravity in a certain extreme condition. Serious science is already looking. Scientists are not building anti-gravity rooms, but they are conducting high-precision experiments that could reveal unexpected gravitational behavior. For example, testing the weak equivalent principle which matter and antimatter at CERN. If the antimatter falls up instead of down, it would be a form of anti-gravity. Searching for the fifth force at millimeter range, some theories suggest gravity might have a repulsing component at a very short distance. Study dark energy. The force caused by the universe expand to accelerate is in effect a form of cosmic scale anti-gravity. Understanding it is one of the biggest questions in science. History is full of wasteful search that paid off. Before relativity, looking for a way to explain Mercurius' orbit beyond Newton was not wasteful to a theorist for quantum mechanics. Studying the bizarre spectrum of hot gas seemed esoteric. Basic research often looks pointless until it changed the world. For a PhD student in theoretical physics of research at CERN, no, it's not wasteful. Probing the boundaries of gravity is one of the most important and respectable goals in all of science. You are not looking for anti-gravity, you are asking if Einstein was the final word. The wise paths don't look for anti-gravity, do look for deviations from the general relativity in extreme conditions. Ultra-cold temperature, a very small distance, use energy. That's a real scientific quest. The anti-gravity device is fantasy. The test of fundamental physics is a Nobel Prize waiting to happen. Okay, the last thing that I want to talk about, one of the mysteries that I have, and I want to show a movie before. Tim? The point is to listen to the sound and look at the radio on the right side. Then you are closing the sound. So, okay. As the levitator rotates, it generates approximately 200 ionic explosions per second, so 200 hertz. It produces an electromagnetic field composed of multiple frequencies. This emission is detectable as audio noise on the AM radio. Interestingly, there are two distinct points along the levitator's trajectory where this noise completely disappears. When the receiver is rotated, the opposite effects occurred. The noise is audible only at those points, those 2 points. This behavior indicates that the electromagnetic wave emits by the ionization process is polarized. However, it remains unclear why these two specific points exhibit a different interaction with the receiver compared to the rest of the trajectory. So I show here now a picture. Okay, on left below you see the receiver, and the red is the coil inside the receiver. And on these yellow points, you hear the noise of the ionizations, and the other parts you don't hear. Now, and here you see it from the side, and here you're standing up. Okay, so there's no noise on the yellow points. There's only noise on the yellow points. So I don't have a good explanation at the moment. Okay, so that's all. Okay, thank you.
Al, thank you. Thank you so much. Let me bring everybody in really quick. And let me see, where's the... there we go. I'm going to take the slideshow down. Okay. And guys, true to form, let's give Mr. Al Baur an enormous applause. Al, thank you. That was wonderful. So for folks who are watching, I have posted clips of this to Twitter and other social channels, and there are always critics out there who are like, oh, this could be AI, this could be CGI, those things. I've worked with devices similar to Al's, not as complex in the past. And I can absolutely guarantee you, based on the sound, based on how they move, based on all of that, it is real. His videos are legit. It is really exciting. He sent one of those to Mark Sokol, and Mark demonstrated it for me. So I've seen one of those fly in person. But Al, the thing that I would personally congratulate you on is the engineering that you have put into that is remarkable. Being able to make that ion flow from the top to the bottom, support that levitator in the middle, that is tricky. And that is entirely an engineering challenge. And what you've done is amazing. Absolutely amazing, sir.
Thank you.
Does anybody have any questions for Al? Oh, and there's Jenny. Sorry, Jenny.
Howdy, everybody.
I have a question.
Go for it, Drew.
Al, it looks to me like that thing's some kind of electrostatic attractor pulsed a couple hundred times a second, and you're just setting up the pulses so that you can maintain some sort of a gap underneath the electrostatic ring. Am I right on that? That's how it's being levitated? It's constantly being pulled up a little bit? No.
Well, you could say that. Okay.
Okay.
When I use a good levitator made from aluminum foil, okay, I'm able to get a very constant frequency from the ionization, okay, which is around 200 hertz. Now, when I use a carbon, it's very random. The interesting part is that you don't see it in the levitation. So there's something averaging inside the carbon that doesn't interfere with the levitation itself. Okay.
Sure.
So it works different. So I believe that in the moment that I start to work with carbon nanotubes, it will be more near to metal. Okay.
Okay. So basically, if you had a built-in processor, it could sense, like, let's say you had some sort of very fast adjustment system that replaced your tweaking. It could figure out, it would self-stabilize.
It is self-stabilizing without doing anything.
Sure. Okay. So
there's no special frequency. It's a totally DC. There's no AC. The AC is created by the ionization. Okay.
So
I want to be very clear about this.
If you stick the whole thing in a vacuum, what happens?
It will stop the work.
Right.
In a partial vacuum, it will work, and maybe even better. But
why would it work in a vacuum?
What?
Why would it work in a vacuum?
In a partial vacuum, it will work because you still have gas particles. You need.
Will it work in a high vacuum?
Nothing. It will stop.
Right.
In space, it can't work.
So if there was an electrostatic propulsion system that worked in high vacuum, would you qualify that as a non-hoax? Because you threw out a pretty big blanket statement. You said all of the bifield round and electrostatic propulsion was all a hoax.
I don't
really
get the question.
Viewpoint on that?
Can you repeat the question?
You threw out a blanket statement that said that all electrostatic propulsion was a hoax, was not real. So my question is that really your view, is that there's no
No,
electrostatic propulsion that'll work in vacuum.
Anti-gravity is waste of time for me as an engineer. Okay, let us put it this way. It's a waste of time. Yes.
Okay. What do you define as anti-gravity? The nullification of gravity, or a
Yeah,
thing's ability
nullification. Yes,
to levitate?
yes. Okay, what I believe. Okay, maybe this is easier to put. It is possible to with electrostatics to make something that looks like anti-gravity, but it's not. Okay? Can we agree on that?
Can you define what anti-gravity would be? Is it a liquid, a solid, a feeling? What is it? A negation of the gravitational field?
Anti-gravity is when you have an object and you put it under another object, it will be lifted. And it's not possible.
Okay, yes it is, because I've done it many times. So
well, and guys, we're at the top of the hour.
I want to say something personal to you, because you're working a lot of years on electrostatic devices. You have to check if the not ionization is involved that makes the propulsion.
Well, Drew's working in hard vacuum.
Yeah, we're in hard vacuum.
How high?
10 to the minus 7.
And how far are you from the walls?
1,000 times the distance we are to the nearest ground.
And how you make sure that you have no outgassing?
It's inside of a box, a sealed box.
Yeah, he's in a hard vacuum. Al, so if it's okay, we are at the top of the hour. I want to go to Gabriel if that's okay. Guys, so let me do this. Let's put our hands together one more time and give Al Baur an enormous applause. And I don't mean to cut your dialogue off. I'm just trying to kind of keep us on track. I screwed things up by being a little bit slow on the intro. Let me take everybody out except for Gabriel. Okay. And there we go. Mr. Gabriel Dias. Thank you, sir. Thank you. And let me see. Do you have a presentation to upload? You have a PowerPoint.
Oh, I have already. I'll just share it in my screen.
Oh, perfect. Awesome. Well, yeah, so you were working with Douglas Miller and there we go.
Can you see it now?
I can. It looks wonderful.
Okay, cool.
Oh, perfect. Okay, well, yeah, if it's okay, let me take myself out. I will be here in the background. And I would say take it away, sir, and thank you so much.
Thank you. Just getting set up. Good afternoon. My name is Gabriel Dias. I'm an electrical engineering student and a research assistant at ZPF Technologies. This is the company's third talk at APEC. The first two were given by Douglas Miller, founder and CEO, presenting the company's vision and the physics and motivations behind it. Today, I'll be talking about the diagnostics framework, meaning just how we measure what we're talking about and how we determine what our device is actually doing. And the framework is Douglas's, and the discrimination work near the end is mine. And discrimination being just the job of telling competing explanations apart. Start with some theory first, before I show you the device or just a general idea of it. since I can't actually disclose the real design and materials we're using. And I'll start from a simple question some of you are familiar with, which is, why doesn't the electron collapse into the nucleus of the atom? Or where is the electron getting the energy to keep moving around, jittering indefinitely? Or the stability of the atom problem? Well, according to classical physics, the electron should collapse. Right here. An orbiting electron is an accelerating charge, and that charge radiates energy away over time till the orbit decays and the electron spirals into the nucleus in about 10 trillionths of a second. So classically speaking, atoms shouldn't exist unless something is feeding energy back in. In quantum mechanics, stability is built into the theory through Heisenberg's uncertainty principle. Confine, right, the electron more tightly and its momentum spread grows, costing energy. So there is a lowest possible state, the ground state. And the theory guarantees it's stationary, and it works just fine. No problem with that. Although it could be a little counterintuitive sometimes. But well, in stochastic electrodynamics, SED, there is a third answer, and that is balance. In stochastic electrodynamics, there is a real classical field in the background that's present everywhere all the time, and that field gives us gives the atoms their stability. The electron does radiate energy, exactly as classical physics says, but it also absorbs energy continuously from this background field. And then the two rates cancel, right here. So Dr. Hall Puthoff in 1987 computed that the balance for the ground state of the hydrogen atom is even. So average power emitted equals average power absorbed. So this third answer gives us a real field everywhere all the time. And you just can't feel this field for the same reason you just can't feel the atmospheric pressure pushing your body at every moment, because it just pushes from every direction. It pushes the same from every side. But what is this field exactly? Well, that is the zero-point field, a real random electromagnetic field that's present everywhere all the time. It's also stochastic, meaning is that it has random phases. So it averages to zero, but it never really stops fluctuating. The pendulum analogy. It's homogeneous, meaning it's the same at every point, and isotropic, meaning it's the same at every direction. It's also Lorentz invariant, meaning it's identical to every moving observer. And every field has a spectrum, okay? And the spectrum is just how the field's energy is spread across frequencies. How much of it is low oscillations, how much of it is fast ones. For the zero-point field, the energy density grows as frequency cubed, omega cubed. And omega cubed is the unique spectrum that keeps the field identical in every reference frame. Any other distribution, you could detect your own motion through it. And that's spectrum right here. And that matters because the spectrum grows as frequency cubed. So most of the field's energy lives at very high frequencies or very small scales. The field is most energetic, most responsive at the nanoscale. And at the nanoscale is where our device operates. So that's the energy scale that we work at. And where does this energy scale come from? Not from quantum mechanics, but from Max Planck himself, from his paper from 1912 on the foundation of the law of blackbody radiation, his second theory of radiation. In that theory, emission happens in discrete quanta, that is in whole packets, never in fractions. While absorption stays continuous. And when Planck worked out the average energy of his oscillators, just a little vibrating charges in his model of matter, he noticed one term that will always show up, 1/2 h bar omega, or 1/2 times the reduced Planck constant times the angular frequency, the frequency of each oscillator itself. Every oscillator keeps a half quantum at its own frequency, meaning when you cool your system to absolute zero, remove all thermal energy present, each oscillator still keeps the half quantum. That's the first time zero-point energy appeared in physics. a whole decade before quantum mechanics came to exist. Einstein and Stern picked up the idea the next year, and then by 1916, Nernst was proposing that all space is filled with zero-point radiation. According to Puthoff and also Barry Satterfield, physicist from Australia, the properties of the vacuum can be modified or polarized. And here's the picture. When zero-point waves interfere, they form charge pairs, an electron and a positron, positive and negative together. In quantum field theory, these are called virtual particle pairs. In the stochastic electrodynamics reading, they're real pairs, popping in and out of existence, producing real observable effects. They live for a very short time and then annihilate each other. Particle and antiparticle canceling back into the field, so the vacuum stays neutral the whole time. Now, how do these pairs set the vacuum's properties? If you apply an electric field, before each pair annihilates, it gets slightly stretched, like you can see here, like a dielectric material. Their responsiveness is epsilon naught, right here. The electric constant, and the pair's response to magnetic fields likewise is mu naught, the magnetic constant. And light is exactly the stuff that travels through this medium. An electric field creates a magnetic field, which creates an electric field, and so on. Maxwell's equations. So the medium's two constants set the speed of light. From this equation right here, c squared equals 1 over epsilon naught times mu naught. And so Puthoff developed the polarizable vacuum picture. The vacuum as a medium whose electric and magnetic properties can in principle vary, along with the stability balance we saw at the hydrogen atom. Satterfield extended it, claiming that the density of those charge pairs is what sets epsilon naught and mu naught. So if you change the pair density, in that picture, you change the vacuum's constants locally. So that's part of the theory you're using to build our ZPF array, or zero-point field array, or device. 2 questions in relation to our program. Well, from previous talks from Douglas, can the zero-point field background be changed locally? That's what he discussed. That's the pair section question, and we believe it can. Otherwise, we wouldn't be here investigating it. The question 2, which is this talk, how does the zero-point field participate in dynamic electromagnetic environments? Meaning environments whose electromagnetic boundaries change in time. And when I say that, I'm just meaning those little nanocavities in the array. And by participate, I mean, how does it take part, absorb, push back, organize in these dynamic asymmetric nanocavities? And then we can build the language, the diagnostics, and the models to make the participation visible. Oh, by the way, we're not trying to replace Maxwell's equations. Everything presented here today is modeled with standard electrodynamics, photonics, measurement theory. First, that gives a prediction for what the device should show in every measurement. And that prediction is called the baseline. So only after the baseline is computed do we ask whether anything is left over. And the leftover is called a residual. If the ZPF array has ever has anything to say about propulsion, it will say it as a residual. A directed force left over after everything ordinary is subtracted. The framework is an organization layer on top of that physics. And for the propulsion and fusion questions and our applications, those are more long-term goals, and they come after the diagnostics platform. This is not actually the ZPF array, okay? But what is ZPF Technologies trying to build to answer these questions? The ZPF array, many electromagnetic environments or nanocavities, driven at the micro and nanoscale on one platform. Each environment has dynamic asymmetric boundaries, driven in time and deliberately built different on the two sides, and also special material interfaces. The exact geometry materials are proprietary, but everything I'm showing you here today would apply to any platform of this class. And the ZPF array has channels. A channel is one of independent kind of measurement, and one dial that you can read on the device, light coming out, timing, electrical pushback, noise, or force. The array has many elements and many channels read at once, making the mapping possible. Even if the ZPF array ends up not producing thrust, it is still a measuring instrument built to create measurable contrast against the background field in a unique way, the zero-point field. This is the framework's main equation. In our framework, this is Z of omega t, participation observable. That is a product of these three factors, N sub B, P occupation, and G of omega. And here, observable is just a quantity you can measure. So let me go over each one of these. G of omega is the mode supply from density of states, how many ways the electromagnetic field can vibrate at each frequency in empty space. N sub B is the boundary response, how the walls and structures of the environment change that, which vibrations are allowed here, which are not allowed, and which are amplified. And P-oc, or P-occupation, the occupation term. So of everything the environment allows, we just ask how much actually takes part. Multiply the three, and Xi answers this question. At this frequency, in this environment, how much electromagnetic participation is there? Two of these factors, just standard physics, density states and local density states. And the third, P-occupation, that's where we could find some new content, or we thought so. And here's the idea. The framework proposes that taking part, participation, is just not automatic. When you squeeze the field into a small enough space, participation switches on, weak below a certain degree of confinement and is strong above it. And the switch point is set by geometry. This is the term we have to test the hardest. That's the term that Douglas just gave to me. Near the end, I'll show you one of the first discrimination results, which is that when you write the term in the language of the standard cavity physics, it turns out to equal a quantity the textbooks already have, which is the cavity beta factor from Purcell physics. So by itself, it predicts nothing beyond ordinary physics. And that is useful. It tells us what ordinary looks like in our own variables. It also tells us where anything new will have to hide. So everything in this equation is scalar, by the way, single numbers. So anything new will have to show up in what this equation leaves out, which is direction, correlation, and timing between points, which scalar values cannot account for. And one more thing related to our language. Participation here is not a claim about the physics either. It's just how we organize measurements. And every claim comes later from the measurements built on this equation. Boundaries and modes. Well, imagine a guitar. If you pin both ends of a guitar string, and only certain waves can exist, the waves that fit in it. Well, this equation right here, for the fitting condition, the standing wave condition, says it in one line. The length equals a whole number of half wavelengths. L equals n lambda over 2, where lambda is the wavelength and n counts the mode. And mode is one piece of jargon on this slide. A mode is one allowed pattern of vibration, and nothing more. So you have mode 1, mode 2, mode 3, etc. Walls, they do the same to the electromagnetic field. Boundaries select which configurations are allowed, which are enhanced, which are forbidden. The picture here shows a computed nodal pattern of a vibrating plate. On a real plate, sand collects along exactly those lines where the waves stand still. So you have the standing waves there. The boundary decided the whole pattern. The single idea is where boundary condition field dynamics comes from, another name for our framework. And our platform is engineered boundary selection with boundaries that move. It doesn't look like any dynamic Casimir designs you've probably seen. It's not like just two plates pushing each other, being pushed close like that. It's way different than that. Resonance and equality factor. While bounded systems resonate, near certain frequencies, the response is strong. The quality factor Q measures how sharp the resonance is. And here's the definition. Quality factor Q equals omega naught over delta omega, the resonant frequency divided by the line width, which is the width of the resonant peak, the resonance peak. In energy terms, Q compares energy stored with energy lost per cycle. So high Q means a narrow line and a slow leak. The stored energy survives many cycles before it drains. And the two curves show the contrast, tall and narrow against low and broad. And by the way, remember Q, it's going to show up later on. Density of states, that's the second factor of the main equation we're working with. The density of states asks how many field modes exist per unit of frequency. For free space, the answer is the formula on the slide. So G of omega equals omega squared over pi squared CQ. The count grows at frequency squared. And here's the thing. When you take that mode count and you multiply by the energy each mode carries, the half h bar omega from Planck's slide, the 0 point energy, comes back. So counting modes and weighting energy are basically the same physics. Local density of states. For the first factor itself, inside a structure, the mole count depends on where you stand. If you put an emitter, an atom, or a molecule, or anything that radiates at a bright spot, an untied node where the field is strong, it radiates fast. If you put the emitter at a dead spot or a node, it barely radiates at all. That's just the Purcell effect, and it's measured routinely in labs. So N sub E at position R and frequency omega equals -1 over pi times the imaginary part of the trace of the Green's function G evaluated at R with itself. G is the field's full response function, meaning if you, let's say, you kick the field at one point, G tells you how it rings. The trace sums over directions, and the imaginary part selects the response in phase with dissipation, the part connected to real emission. The -1 over pi normalizes it into account. And in this picture right here, the shaded regions are filled at intensity. The strong emitter sits inside a bright lobe, the weak one at the node between the lobes. And in our work, this is N sub E. Casimir effect, you bring two conducting plates together. Between them, only modes that fit are allowed. Fewer than outside, where every mode exists. More modes outside than inside means more pressure outside than inside. And the plates are pushed together. Just like the atmospheric pressure that you can feel, well, if you unbalance it, you can feel it actually. And that's the Casimir effect. Predicted by Casimir in 1948, measured many times since, and accounted for in nanoscale engineering today. And this is the result right here. Pressure equals minus pi squared h bar c over 240 times the gap to the fourth power, where A is the plate gap. Oh, and note that the fourth power right there, if you have the gap, the pressure grows 16-fold, which is why this physics lives at the nanoscale. Moving boundaries and sidebands. Static boundaries reshape the vacuum's response. The defining feature of our platform is that its boundaries move. If you drive a wall at frequency capital omega, and the response picks up sidebands, or displaced copies of itself, add the frequencies in the equation, omega n equals omega naught plus or minus n times capital omega, where omega naught is the resonance, capital omega is the drive frequency, and n is a whole number. Every modulated system in engineering uses this, like radio, phase modulators, or moving mirrors. And there's also the dynamic Casimir effect, demonstrated by superconducting circuit experiments in 2011, where fast boundary modulation converts vacuum modes into real, measurable photons. So boundary motion coupling to the vacuum is demonstrated physics. What the drive produces is the sideband family in the driven response. And the driven response is tested against the signature family. Whether it holds anything beyond ordinary modulation is a discrimination talk later in this presentation. Measuring a background. So a uniform ever-present background gives no reading, like the zero-point field, for example. There's nothing for you to compare against, and that's the uniform part over here. But if you bound the region, and if you structure it, if you drive its walls, now inside differs from outside, and driven differs from undriven. That's the right panel right here. And then the differences are measurable. So the platform does not measure a uniform background directly. It measures the contrast, the boundaries, materials, and modulation create. The measuring chain. Here's the whole program's logic in just one line, right here, from left to right. So starting from the background, which gives no direct signal, create a boundary contrast with materials in motion. We measured the response, that is spectra, phase, and noise. Then we compute the standard physics baseline, what cavity electrodynamics, photonics, and material science predict for the same geometry and drive. In every ordinary channel, electromagnetic, thermal, acoustic, mechanical, and so on. And then we subtract. And here is the rule on the screen right here. Measure response minus standard baseline equals residual. So only the residual counts for us. A big raw signal means nothing by itself. Structure environments like these produce big ordinary signals all day long. The residual is the only thing that we're trying to get excited about. Claim ladder. This is how the claims are governed. 9 levels from actuation, measure at the bottom of application, implications at the top. Every level is a measurement. Nothing above a level gets said until the level is done. This is us right here, level 0, design define. The device measurement campaign hasn't started yet. The whole upper half of this ladder is off limits today, and I'll explain why. Just one more thing. Every mechanism proposal is run through screens from established physics before it's allowed to survive. Screen 1 is thermodynamics, system in equilibrium with a single heat bath, steady surroundings and 1 temperature. It doesn't do any network. Screen 2 is magnitude. Every force estimates compare against ceilings, and then known physics already sets. for a device of this size and power. And our early estimates on these have not passed those screens. They came off the books, actually, this is why the talk focuses on diagnostics and residuals rather than the application claims. We're still currently working on this part right here. This is the compact version of our discrimination matrix, the actual work product of my track. Each row names a candidate mechanism, the ordinary baseline for it, and the signature or the fingerprint it will produce. And what will have to remain before we could call anything a residual. The first row is the activation result. I'll show you in a moment. Under the single mode per cell reading, the occupation term becomes the cavity beta factor, which is a clean calibration baseline for us. The second row is the driven boundary lesson. Sidebends are real, but the pattern alone does not identify the mechanism because standard modulation produces the same envelope. Third row is still open. That is the live frontier. Chip point field organization or cross density of states. So if the scalar measurement throws away direction, polarization, phase, and correlation, the surviving question is whether that discarded structure contains a residual after the full standard prediction is computed. So the point of the matrix is discipline. Each row just says what ordinary physics predicts before it is allowed to say what will count as new. The activation term. This is one of the first results we got from a few months ago. Just a calibration result. What ordinary cavity physics predicts when written in the framework's own variables. Start from something textbook, Purcell factor, F sub p, which measures how much a cavity enhances an emitter's emission rate. It grows with the quality factor, and it shrinks with the cavity volume. So Q overview. Next, a standard object called the cavity beta factor, which is the fraction of all emission that goes into the cavity mode rather than escaping to free space. It equals Fp over 1 plus Fp. Now the framework's variable, phi sub q, the quantum packing fraction. That is the variable Douglas introduced later this year to me. Basically means roughly how tightly the field is packed by the confinement. It is defined through a cube root of a volume ratio. So volume is phi cubed by definition. When you substitute that into the Purcell factor, and Fp becomes proportional to Q times phi Q cubed. And then we identify the framework's occupation with the beta factor, the fraction of emission the cavity captures. And the algebra will just do the rest. So P occupation equals phi Q cubed over phi Q cubed plus phi Q cubed. That is the first equation on the slide. A Hill curve, the standard S-shaped switch curve, the exponent 3. Within the single mode Purcell interpretation, the exponent is inherited from the cube root in phi q's own definition, so it's not fitted. So it works out nicely. The threshold also follows out too. The second equation, phi q crit times q to the 1/3 times, oh sorry, to the 1/3 equals psi 6 pi to the minus 1. 1/3 times s to the 1/3, where s is just a cavity shape factor. And the threshold has a physical meaning, which is the following. It's just a packing fraction where the Purcell factor reaches 1, or where the cavity emission catches up with free space. That's what it is. The figure shows the verification. I made it with code, recomputed from Python. Below threshold, a log-log slope of exactly 3. So in plain terms, if you double the packing fraction, participation grows 8 times. And the shape factor shifts only the threshold constant. And the result on the slide, the calibration baseline, standard physics written in the framework variables, which is what makes it useful for discrimination, because it defines what ordinary or standard will look like. And that settles the question anyone would ask. What happens to the framework's equation once this new term reduces to standard physics? While its job changes, it becomes the bookkeeping the measurement program runs on. So participation is a measurement architecture. Every channel in the campaign gets computed, measured, and subtracted in these variables. Sideband comparison. This is the second result I'm showing you today. Discrimination lesson. A sideband pattern can be real and still not identify the mechanism. To compute the spectra right here, on the left, the dynamic boundary model of a driven platform. On the right, the classical phase modulator, a device you can buy. The law behind both on the slide, sideband intensity proportional to J sub n of m squared, Bessel's functions. That is a standard mathematical family where m is the drive strength or the modulation index. We call this amplitude shape the sideband envelope. And the point is on the slide. Same pattern at every drive strength. The sideband pattern alone cannot tell you which physics produced it. That's why the baseline gets computed first, and why claims never rest on pattern matching. So we can't identify any mechanisms with just this. Testing deeper participation. So how would deeper participation actually be established? Through the 6 channels on the slide. Photon emission, phase, which is the timing of the response against the drive, impedance, how hard the drive pushes back electrically, sidebands, noise, and force. Each measure after standard effects are subtracted. That's the program's method. Participation beyond the standard prediction is tested for, channel by channel, subtraction by subtraction. These 6 channels are what the diagnostics implements. The background can only be inferred through residuals. So the more independent channels you measure, the more pieces of the picture you hold. One last concept on cross-density of states. Well, the local density of states, it listens at one point. What we want to do is we want to listen at 2 points at the same time and ask whether the field here moves in step with the field over there. It's the same Green's function that we've seen before, but it's evaluated between 2 different points instead of just 1 point with itself. So the slide shows the pair side by side. So n sub e uses g of r with r. The cross density of states uses g of r1 with r2, so 2 points. What carries this? What it carries is what the 1 point number cannot. Correlation, direction, how the structure organizes the field between places. And it's measurable. Labs map it with 2 probes. You can do it anytime. Where a residual could live. This is the narrowing result so far. If scalar mode counting does not discriminate, the search moves into the structure the scalar measurement discards. If you look at the standard measurement formula once more, notice the 2-step compression in it. G evaluated as at the same point, and then a trace. Everything is reduced to 1 plane number per point. That throws away direction, polarization, in polarization, which is the way the field points, right? Near field phase, the field's timing right up against the surfaces. And point-to-point correlation, the cross-density of states that we just met. Everything in this dashed red region is real, measurable structure that the scalar number discards. After all the screenings and all the subtractions, this discarded structure is the one identified place where we think our framework content could still show, and only as a difference from the computed standard prediction for the same geometry, model as a response parameter, and never as a change in the constants. That modeling choice was our governance decision. So we're trying to use cross density of states instead of local density of states because it gives us more information. Six questions before an experiment's done. Before an experiment's built, mechanism proposal must answer the 6 questions. Which part of the field response carries the effect? What sign and where? At which frequencies relative to the drive and the resonances? How does it scale with geometry? How large compare with the baseline uncertainty in the probe floor? And does it live in the dissipative part of the response, the part that absorbs energy, or the reactive part, the part that stores energy and gives it back? Question 5 carries the kill rule. A prediction below both floors means the experiment does not get built. Finding that out on paper costs a week, but finding that out on the lab costs way more. So that's what we're trying to do on paper. Current status, where things stand. Inside the program, every claim carries a tag, established physics, interpretation, or framework hypothesis. And only a calculation moves a claim between tags. Settled by calculation in the program's record. No network from an equilibrium bath. Okay. The activation term reduced to a standard Purcell beta factor baseline with the threshold exponent fixed by geometry. Also, driven sidebands are not mechanism identified by pattern alone. And scalar reweightings reproducing standard results. Raw scalar participation does not by itself establish new physics. And what's open, what we still have to do, work on, the full standard prediction for the device, the noise and error budget for each channel, response time question, and whether any 2-point structure survives as a real residual cross density of states. So those are some of the next steps that we'll have to take. Actually, so the split between those 2 columns is deliberate. So let me say the logic out loud. Everything in the settle column is a parameter-free screen, a calculation that needs no device details, and any one of which could have killed the program for a week of paper. Those run first. Everything on the open column is the device specific baseline. Expensive modeling that is only worth doing if the program actually survives the screens. And it did in a narrow form, which is why the baseline work now sits at the front of the queue. And we had no departure from standard physics or standard electrodynamics here. And the questions are now narrow enough to test. So that's what we're going to work on in the future, next few weeks. From hard boundaries to plasmas, why is ZPF Technologies talking about fusion at all, right? Everything today uses hard boundaries, engineer interfaces. Plasmas have soft ones. They have sheaths, or the thin charged skin where a plasma meets surface. And it also has edge layers, regions where fields organize near boundaries all the time. The bridge is shared diagnostic language, screening, coupling, field organization, near reaction environments. And as ZPF technologies, we're claiming that we should treat the zero-point field as a third body at the nanoscale when fusion happens. More specifically, vacuum catalyzed aneutronic fusion. And aneutronic meaning if you release little or no neutron radiation. And to be precise about what I'm saying, existing plasma modeling is full wave, and it solves already all the complete field equations. So we're not saying there's any problems with it. We're not calling it deficient. The only question is whether an additional variable belongs in the problem, and whether instruments can be built that will tell. And one more thing before I close. If you go back to the hydrogen atom problem from the beginning of the talk, stochastic electrodynamics, the electron stability is a continuous exchange with the background field. It radiates energy and momentum away. It absorbs energy and momentum back, and the exchange balances, netting to zero. So in that picture, momentum exchange with the vacuum is not exotic. It's happening in every atom all the time. The long horizon propulsion question that we have is whether that exchange can be engineered. Can a driven asymmetric environment like the nanocavities that we're working on, can they make its momentum exchange with the vacuum net and directed? Or in other words, if a response is asymmetric, phase locked, and repeatable, it could appear as a candidate directional pressure, a momentum flux residual, but only after the ordinary electromagnetic, thermal, acoustic, etc. Channels are modeled and subtracted. We haven't yet shown that this residual exists. The first channel of the diagnostics is where it would appear, though. That's the path from an instrument to propulsion, a measurement target. So basically, we need to actually figure out the ZPF array before we go for propulsion. Roadmap, the working rule of the whole program, left to right. We simulate, we build a test piece, we measure, we control, subtract, and only then we interpret. That rule sits inside a longer arc, which is our ZPF technologies roadmap from Douglas. Language, variables, diagnostics, and mechanism discrimination, software, and experiments. The framework is young enough that part of it is still at the language stage. The phenomena are described before the form of mathematics fully exists. And building that language is the current work, what I'm doing. Today's talk walked you through the first 4 stations, and the next 2 deliverables are already named. I already told you. The full standard physics prediction for the device and the channel-by-channel error budget. The 2 open items you saw. And computing the standard response before searching for residuals is probably our next milestone in the sequence. And let me be clear about how this ends, because there are exactly 2 endings. If the measurements match standard electrodynamics everywhere, the framework settles into what it already is today, diagnostics language and an instrument. If a residual survives subtraction and controls, then the framework earns its next equation, built to the specification the closed routes already wrote. Either way, the question gets answered by measurement. And I'll close here where I started. You can't feel the atmospheric pressure because it pushes the same from every side. And you can't measure a uniform background until you give it an edge. Well, this program is about building the edges and the discipline to read them. honestly. Thank you.
Gabriel, that is amazing. That is amazing. Thank you. Thank you so much, man. Here, let me do this. I'm going to take down the slideshow. I'm going to bring everybody back in. Thank you so much. And guys, before we do anything else, as true to our tradition, please put your hands together and give Mr. Gabriel Dias an enormous hand. Thank you very, very much. And I know this is a lot because you just started working with Douglas recently. So you're like, you're drinking from the fire hose, right? And trying to present all of that. But I think that was one of the reasons that he asked you to present, so that, he was like, okay, Gabriel is working with me. He's absorbing all of this material. Let's see if he can put that together. And you did wonderfully well. Thank you so much.
I tried. Thank you.
No,
appreciate it.
Well, yeah. Do you guys have any questions?
I do. I have a question. Okay, Drew, you were first.
Mikolaj.
Go ahead.
Okay.
Mikolaj, go for
So
it.
the fundamental thing in what you're doing, the question is, what is the energy density of the 0-point field? Because everybody says, one says this. You see, the lambda CDM says nothing almost, and the quantum field says 1 to the 20th, 120th actually. So where is it? Do you have an idea?
Well, you need a cutoff for that, right?
Yeah. So what is is there something that you predict and you can measure? What's the energy density of vacuum?
Oh, not right now. Well, we have the average energy per mode, which is 1/2 h bar omega.
Yeah, but you can have million modes or billion modes. Where do you stop? That's where the 1 to the 120 comes, because it's been reduced. Okay,
Right,
from
because
infinity.
we normalize
What's your take on that?
Oh, my personal take on the cutoff problem. Well, I know Putoff doesn't solve it on his paper.
No, he doesn't.
The integrals are dirty. They're ugly.
But can you?
I'm not sure. I don't have a formed opinion on the cutoff problem.
No, but can you measure it and can you prove it, either or? Because that's all in the measurement. Because at the moment we have math, nothing else.
Well,
and the boundaries
Mikolaj, if I could
open.
jump in, go easy on Gabriel, because he is.
No, I'm not criticizing. I'm asking a question.
Yeah,
I know. I'm just saying.
I'd like to learn something.
Keep in mind, he is coming in cold with a lot of.
I know that, but I'm not criticizing. I'm asking. I just want to know.
Yeah. Well, what we want to do is we want to be able to create this contrast in this nano cavity, so we're actually able to make these measurements.
Okay.
We don't have the device yet built. What we were doing is the calculations before that.
But so you say in that case you'd be able to tell what the energy, vacuum
I
energy
hope
is.
so. I will hope we could get some measurement from it. Yeah, at least.
Okay. But you don't have a theoretical prediction where to stop basically the modes, or not?
No, I don't.
Okay.
I could give you a personal opinion, but I wouldn't even give you one here.
Yeah, that's what I want. Give me your personal opinion. That's important.
Well, I think there should be a cutoff. Well, my actual opinion, the vacuum could be divided into sectors, but that's I'm just making that up, okay? In the sense that, for example, you have SU2 waves, and they only act at a certain part of the vacuum, I guess. I'm not sure how to word it, but you can only see certain effects in certain parts of the vacuum, in theory. I'm not sure.
Okay, thank you.
Yeah, sorry.
Perfect. It's all good. I mean, you'll measure it. You'll let us know.
Okay.
Gabriel.
Yeah.
Awesome. I understood about 10% of what you said, but
okay.
what I caught was it sounds like if the universe wasn't talking to every electron all the time, that the electron would just spiral down due to its negative and the proton's positive. That's like the Coulomb attraction. Is that what would happen if there weren't energy getting pumped into the electron?
Right, because the 0-point field, since it's everywhere all the time, it's jittering the atoms. It's interacting with it the whole time, and there's absorption and radiation happening all the same time. So it's keeping the balance, absorption and emission.
So there's, and I'm trying to, the Casimir effect thing says that if you have two walls, that there's more pressure on the outside coming in than the inside going out. So the walls kind of come together. So wouldn't there be less pressure between the electron and the proton than between the electron and the rest of the universe? Wouldn't it push the electron inward?
I'm not sure. I could probably take my time to think about it.
Yeah, I'm just thinking. It just seems, it seems like something is keeping it from collapsing inwards.
Right,
and as I understand it, it's not in orbit. It's kind of in a volume of space somewhere.
Right. Yeah.
So here is one thing that to you, Drew, and to you. You drew a picture when the electron is flying around it. That's not what's happening. Nobody knows what's really happening, but mathematically, it just basically is a probability of this being here, there in 3D, not in this. So it's maybe not it moving at all. You don't know.
Oh, that's true.
That's
like a
fallacy, but Jennifer probably knows way more about that than I do.
No, you're right though. Yeah.
Yeah. Well, guys, does anybody else have any questions? We are almost at the top of the hour. Oh, Joel, go for it, sir.
Yeah, maybe just a short. So first of all, a statement. I really like that you guys have like a real diagnostic framework built out, right? That's very good. So you're not just starting with a claim, but you're starting very methodologically sound by how to test, and that's yeah, it sounds very mature and very good. That's how science should be done, right?
Oh,
so maybe you have like a scalar participation. You could maybe have a correlation matrix instead, right? So
okay, a correlation matrix. Okay. I might have something like that actually.
Okay.
Yeah.
So I'm working like in different frameworks, and the Heim theory framework, for example, there is there are correlations that arise between distinct partial structures. So off-diagonal terms are becoming very interesting and important in certain conditions. So a matrix in that direction could be interesting to look at as a model.
Oh, for sure. I should look that up. I'll do some research on that for sure.
Okay. Yeah, that's basically.
Thank you.
I could go on, and maybe I'm going to write you an email after this, but yeah.
I got you.
Well, and for my part, again, I love the work that Douglas is doing. I'm so happy that you are working with him and collaborating with him. It's exciting to see, it's like planting seeds, right? And he has the ZPF technologies that's a seed that he planted a while ago, and it takes a while to germinate, right? But you start to see, it coming up through the soil, and it's like, that's wonderful. And so, yeah, when he told me about the work that you guys are doing, it is really foundational, right? But that's awesome. It's like, okay, again, you're preparing that field to grow some really amazing fruit that no one's ever seen before. So that's really exciting to see. It's really exciting.
Thank you. I appreciate it. And by the way, putting all that blabbering aside, I seen the device. I can't show you. I've seen it. It's super different than anything you've seen before. It's not like two plates like that. It's like completely different. And I can't even give you an idea. You will give it away probably.
Yeah. I don't. Yeah.
I saw it and I started actually studying it. I spent a long time on it, and I was like, this is actually good. This could actually work. This could actually do something. I don't know what it is. Like, of course, propulsion, the cross density states and all that, but the way I see it, you should definitely make something different. You should definitely give us
exciting. That's exciting.
Yes.
Yeah, and don't share secret sauce. I mean, lots and lots of folks. Lots of people who are here with us on the stage right now, they've got secret sauce, and I'm just like, don't keep that stuff private. That's APEC. Really, our goal is more of a community resource than anything else. So,
you got it. Thank you.
Awesome. Awesome. Well, we've got about 2 minutes left, guys. Should we go to Miss Jenny Lorraine Nielsen?
Howdy.
Hey, Jenny.
Howdy.
Okay, well let's do that. But actually, you know what? Let's give Gabriel one more hand. Again, he pushed through a pretty intense presentation, and he is new to that organization and new to the work. So, Gabriel, thank you so much. And what I'm going to do now is I'm going to take everybody out and okay. Oops. Hopefully everybody. There we go. Jenny,
Howdy.
Welcome back.
It's great to be here. It's been forever, it feels like.
Yeah. Well, but I talk, as I mentioned, I talk to you in email frequently. So you're on Jack's list, right? I don't know if I should say that in public. Except that none of us can get off Jack's list. So
we're all permanently on Jack's list.
Yeah.
And the list just keeps growing and growing, and it just goes on in infinite subchains of subchains, like a Borges library.
It's interesting that he specializes in relativity because his email list is like a black hole. Even light can't escape.
You can't. You absolutely cannot.
Yeah. Well, right. Jenny, let me put up. This is a wonderful presentation. Thank you so much for presenting for us today.
It's great to be here. I wanted to have a Python code, but my cat went to the vet, and that kind of cut into my Python coding time. But
okay, well, let me take myself out and take it away. I will be here in the background if you need me.
All right. Okay. So I'm here today to talk about topological space-time torsion. There have been a lot of different approaches to torsion, but most of them are related to spin density. And in TUFT, we don't need to worry about spin density. Spin density does couple to the fiber, and thus it does have torsion, but you don't necessarily have to work with it to get torsion in TUFT. So what's TUFT? If you've been following me, TUFT is my magnum opus thing, my theory of everything. Basically, I show that every gauge field in gauge theory, every force that we know about, gravity, strong nuclear force, weak nuclear force, or E&M, electromagnetism, and hypercharge, all of that can be found on this thing called the complex Hopf vibration. So you'll probably have seen my paper called The Topological Unified Field Theory on the Complex Hopf Vibration. It's on Phil Papers. It's also on preprints.org with a slightly different title, The Complex Hopf Vibration as the Canonical Space for Gauge Gravity Unification. That's the kind of fancy paper title. And anyway, this is the first theory of everything to predict particle masses, at least since Heim. I hear he did it too, with an easily replicable formula that anyone can mess with and replicate with a Python code. And it also is the first one to pass peer review that I know of that does anything sort of like this. So, and I haven't passed all peer review, but I've passed 3 or 4 stages, depending on how you count them as stages. Okay, so in traditional general relativity, Einstein's metric torsion tensor allows a spin field to twist space-time. And now, this is a GIF that I found online. It's really not Einstein's metric torsion. It's the Einstein-Cartan equation. And then it's Sciamma and Kibble also worked with this too. And Sciamma and Kibble were well, where would torsion come from? Cartan mapped torsion onto general relativity. Usually general relativity only allows space-time bending and curvature. What about twist? So twist here, it's kind of a goofy picture that I found and I liked. It shows these crop circles that show spin in the field, but that it's kind of twisting. So you can see the twist of space-time here and right here. And anyway, I just kind of found this because I found it entertaining. The point is that the twist distorts it, right? It's not just curving and bending, it's twisting around like a whirlpool. Anyway, so topological gauge fields and the Botrami potential operator govern torsion coupling in our universe, if my theory is correct. My theory should probably be correct. I predict the neutrino masses and the G-2 for the tau particle. If those come out and they match me, I mean, it's true. And then there's one other thing that's already being verified, is the holonomy in particle paths. So there's been some work by Sala in Science, I believe it was. Anyway, in 2025, and it came out and it kind of showed that particles follow Berry phases, and Berry phases map to the Hopf vibration. And basically, it's something that's been predicted, but only within a certain framework in materials. And they're starting to realize that it's not the material generating the shape, it's something in the background. So they're calling it like a quantum metric and something like that. But anyway, they call it a force-free situation because they can't find a force that's doing it. And basically it's torsion in the field that's causing that kind of effect where the particle does this that you didn't expect. Anyway, so in my gauge gravity unification on the complex Hopf vibration, which is really just this fancy shape, if you look back here, like that's a Hopf vibration, that's a Hopf vibration. They're just different variations on this same build of thing. The potential on this thing, I'm trying to find where I talked about potentials here. Okay, so you see the field lines here. You know, usually in just regular electromagnetism, you see the field lines, they come out from the source, and then the potential lines are around it in circles. It's sort of the same dealio with the Hopf vibration. The Hopf vibration, the lines that extend from it, you can think of as field lines, and then the circular parallel circles you can think of as Beltrami potential modes. So it's the potential is perpendicular to the field mode, just like with a regular field line, just like with regular E&M. Anyway, so electromagnetism is the UN fiber, and gravity is sourced from torsion of the object, which is just the Beltrami potential. That's the torsion. It spins around, and it has a slight twist, and the twist actually drags it in a specific direction, which imparts chirality or helicity. It imparts spin. It imparts all the beautiful things we used to get from the Dirac bundle. So in traditional physics, we have the gauge bundle, and then we talk about particles as if they're excitations of that gauge bundle, but then we don't treat them that way. We glue on this thing called the Dirac bundle, which was sort of a toy model that Dirac was playing with that imparted helicity, spin, the things that we wanted, the things that we needed. And so he took that. Now that thing is just a regular, there's two kinds of multiplication. There's the regular vector multiplication, and then there's the cross product. The Beltrami is the cross product, and Dirac just is the regular product. So the cross product is more accurate. So TUFT replaces the Dirac toy model of the particle. And the reason I call it a toy model isn't because Dirac was like doing something wrong. At the time, he was doing the best thing they knew how, but it didn't put particles on the field. And we always kind of knew they were excitations or eigenvalues of the field. Clues and Klein were going off of that assumption. Everyone just kind of felt like that was what it should be. But then we put on the Dirac bundle because we didn't know how to get them off the field. So in TUFT, you get them off the field. So the eigenvalue, since we map the field with the right principal bundle, which is the Hopf vibration, since we're using the right principal bundle now, we can get the particles off of the bundle itself. Because if you look at that thing at different levels of the gauge, if you look at U1, which is electromagnetism, you can find eigenvalues on there. There's only two. There's the photon and the graviton. And the graviton is from twist, and the photon is just from the connection. And then on SU2, which is S3, which is the field that we're living on, basically we're living on a open force sphere, but the force sphere, the surface of the force sphere is 3D. So we feel like we're in 3D, even though we're really living in 4D. But anyway, there you get the weak nuclear force that lives on S3. Then on the shell right above us that projects down, that's the nuclear strong force, which is kind of a weird thing. It seems to like go forever, but it also seems confined within the quark, which is just kind of the quark like I'm gonna say this wrong. So, but there's confinement to the quark system, and then you don't see the strong force manifesting just anywhere, but maybe it does manifest just anywhere. But you always pull in these other particles if you try to start checking how far apart you can get. You just start bringing new vacuum particles in. I think that's basically because it's an S5 effect. It's at the next dimensional level, but I don't need to get too far afield. Then classical EM fields. I just found this. There was a scientist named Ranyada, I believe is how you say his name, Ranyada. He was working on electromagnetism, and he showed that electromagnetism is U1, and then he showed that means it's on the Hopf vibration on SU2, like I was talking about, except it's the U1 on SU2, and that U1 meaning the circular symmetry on the sphere. So anyway, so he found that the electromagnetic field was working like a Hopf field, which is what I showed, but I didn't even know about his work, but I just found it. And so that's more verification that you can map regular electromagnetic fields as this crazy bundle. And so it's really just a bundle of field lines, and then it's a bundle of potential lines. And then the potential lines carry torsion, although not very much usually, so you don't usually see it. But if you can kick it up, you can find the torsion, is basically how the theory goes. So the topological coupling is physically evidenced by the 1964 Baur experiment. They pulsed water with an acoustic shock source, and they got a spherical shock shells, 3 of them, and there were 20 modes. And basically there was no way to predict that, though, and I went through and I couldn't find a way, and I tried more ways than Baur did. So anyway, but if you use my way, if you show the water as coupling to the torsion field on the Beltrami flow, which kind of makes sense because like Beltrami is linked to Navier-Stokes, but the traditional Navier-Stokes equations don't predict this. So anyway, so topological electromagnetism is this thing that Ranyada found. He found that the electromagnetic field is constructed from pullbacks of the area form on S2, which really just means the S3 to S2 on the traditional level of the Hopf vibration. So the helicity is quantized, and then you get charge quantization, which is what I showed, that you have to use a non-trivial field. So in TUFT, the space-time sector, that's Einstein-Cartan. Then you get the standard model gauge fields, although there are more gauge fields in my theory than in Einstein-Cartan, although it doesn't really, than in the standard model, although it doesn't really matter much because I'm just like color is SU4, and the neutrinos live on SU5, and that's why they're so weird. But nothing is added as an independent Dirac sector. So, or there's just one bundle. And one thing that I proved recently was that just if you take a gauge field, the only way you can get lots of different fields on one, like lots of different gauge symmetries, on one field, is you have to have a non-trivial field, which means a twisted field, which means if the universe is one thing, it's this one thing. It has to be the complex Hopf vibration, because that's the only non-trivial bundle that holds U1. And so since it's the only non-trivial bundle that holds U1, in fact, it's the bundle of all U1 bundles, if you want a unified field theory with electromagnetism on it, it has to be here. And then you see, if you keep moving up, you just keep getting to another higher gauge and another higher gauge level until you get to SU3, and then you can go higher. But you don't really need to go much higher than S9 to find everything that would be impacting us, because the energy it takes to interact with the level up keeps increasing. Like it takes more energy to find the strong nuclear force and to pry quarks apart, than it does to notice E&M. In reality, we interact with E&M all the time. We don't really find the nuclear force and easily pull it apart. So basically there's no real reason to worry about S27, because we're never gonna get there unless we're some space alien superpower at some point. What Michio Kaku talked about, type 3 civilizations or something. Maybe when we're type 4 or something, we'll know about S27. Anyway, the Hopf shells reveal the gauge symmetries. You can think of the gauge symmetries as cross sections. So like the cross section of the regular total space of S3 is just U1. And then when you go to S5, you have different cross sections. You have the SU2, the SU3, and the U1. And there are different cross sections at different levels of the thing. The Beltrami flow here, that's just the perpendicular lines. The flow is everywhere perpendicular to the Hopf fibers. The potential is constant around the fibers. It's just like regular electromagnetism. And the eigenflow of the curl of S3, that's one way of thinking about it. You don't really usually have to think about eigenflows, but you can. So there's no Dirac, so we're just dealing with this thing. That means all the particles are on this thing. So I find different eigenvalues, which are linked to different types of knot configurations on the levels. And then once you find those and you find the stable knot configurations, those things happen to have values of mass that would look like our particles that we have. So I found the leptons on S3. I found the bosons on the knot complement on S3. I found the quarks on S5. I found the gluons on S7. They're kind of trapped there. There's no way for them to interact to project down to S3 from there, because everything has to project to S3, because since leptons and electrons and bosons are on S3, we generally speaking feel like we're on S3 because we're mostly made of electrons. And anyway, so because we're there, we can't easily interact with some of the higher levels. But where was I going with this? Oh, but we can interact with S9, but S7, even though we have effects from S7, mass doesn't project down from there to S3. And that's why we don't have gluons with mass. It's not so much that they don't have something that could be like mass. It's that from where we are, we don't ever see it because it doesn't project down, and we live on S3. So anyway, so TUFT does not begin with a Dirac field. It just starts with this one connection A, and the connection has torque basically. And the fundamental dynamical operator is this B equals star D. B is the Beltrami operator. It's the Hodge star operator here. It's the Beltrami Hodge star operator. Anyway, the Beltrami operator acts on the connection, and the Hessian of that thing provides torsion. That's the torsion action. And I don't know why. Oh, now I can see it. So anyway, all the forces on TUFT actually are from that torsion, which is weird. But if you go through there, and I was going to put this up as a slide, I went through there and I derived the entire standard model Lagrangian because one of my reviewers in their infinite wisdom wanted me to do that. So that's what I did mostly this week, because that's due on Monday. And then I found all of gravity on there, which was very close to Witt in 1988. And you can get gravity off of the thing. Now, he did it in 2D plus time, which is weird. But he then at the end says, well, you really could do this as 3D plus time. And it's like, why didn't you do it that way? That would have been so beautiful. That was it. That was the thing. Why didn't you do the thing? But, well, and then so the point is that spin density isn't the thing. Spin is the tongue, and the whole thing is the worm. So if you remember Sandy the squirrel, torsion is everything. Run, so that's the idea. So space-time torsion is not fundamentally identical to spin density. Spin density is an aspect of it, but it's not the only aspect. You can couple to it in other ways. Spin density is the one source obtained from a particular Poincare gauge construction. But in the complex Hopf framework, gauge holonomy is torsion, which is gravity. So the relevant electromagnetic configurations are topological Beltrami modes. So then, that went over my speech. But anyway, so torsion is this thing. If you don't know what torsion is, I'm sure everyone knows what torsion is. It's basically torque, but it's almost like shear. You're twisting things until they break. And then water supplies a polar medium that can couple directly to the UN field. Now, why is water cool? Well, see, water, this is my next slide. I can't play the video here because we do PDFs, but there's this video by Secure Team that my brother and I watched like years ago. I guess it was from 2017. And it shows this, it's probably just a regular old water spout, but the idea is cool. So it shows this weird UFO thing around that thing. And then it's like, well, it's sucking up the water somehow, but I don't see it as connected to the spout. But anyway, you can imagine maybe these UAPs need water because, we do see a lot of them coming into the water, going out of the water, even if this isn't really legitimately them sucking up water. You get the idea that they're around water a lot. And why would they be around water? Now, if they're not just some optical illusion swamp gas or whatever, if they're legitimately UFOs, or, not legitimately UFOs, if they're legitimately some spacecraft from outer space or from underwater or from some other dimension, whatever they are, if I imagine they need fuel, right? And so since they're around water a lot, well, why would water be their fuel? And then you start wondering, what's the big deal about water? Well, water is where life came from. It couples to field in a different way than a lot of items. If you're in the water and you get hit by lightning, you're dead because the electric field goes everywhere because it conducts really well. So water dipoles and rotating electric fields, it's not really that the electric field has to rotate, it's that the water has to rotate, but in a way that's, if it's exposed to an electric field, it's kind of like the electric field is rotating around it. It's kind of can go either way. But rotating electric fields or rotating water in an electric field engineer macroscopic warp geometry without exotic matter. So this is interesting. So, we hear about, we need negative energy density. We need exotic matter. We need all of these things in order to generate a wormhole or a warp drive. But we don't. We really just need torsion. So torsion is negative energy density in the fancy equations that Hal uses, etc., torsion would work. But everyone is like, well, but we can't get enough torsion because it's just spin or whatever. And how can you get enough spin? I know that Mark Sokol is trying to get enough spin, and maybe he'll do it. But I think that it might be easier just to use water and try to couple to the U1 field as a whole, the torsion of the field as a whole, rather than just worrying about spin. I think this might be easier. So at the cavitation threshold, the cavitation threshold creates an electromagnetic knot. So it's essentially like you're creating a huge particle, kind of. You're creating a non-trivial Hopf invariant. The resulting torsion modified Poisson equation provides an effective negative energy density, generating an Alcubierre-like warp geometry, but without exotic matter. And you don't need much energy either. Now, I was going to go through and I was going to do a Python code explaining exactly how much energy and all those things. And I'm kind of really close to one right now, but I didn't have one before this talk, so maybe next time. So what warp space-time? So you don't need more power. You don't need more energy. You don't need like the bigger, stronger, higher field. You need higher potential. So in TUFT, the effect is driven by topological wrapping or twist, which is not merely stronger field amplitude. It can correspond to that, but that's not the only way to kick it up. So you get more wrapping twist, you need more fiber holonomy, you get more space-time holonomy, and then you get a stronger warp effect. So the key control variable is the topology, the twist, not the raw amplitude. What matters is how tightly the field wraps the Hopf fiber. That's a weird way of saying it, but anyway, but Chern-Simons is twist, not, it's not just curvature, and it's not just the field strength. So why more electromagnetic power is not enough? All fields live on the Hopf fiber geometry, but torsion is sourced when the field couples to the, well, the field is always coupled to fiber, but when you get the matter and you want to couple matter to it, you need to have the matter that will couple to the circular symmetry. So water, if you can get it resonating, basically, you can get it so that all the molecules sort of line up in a ring, and then you can, and then they're really aligned with the U1 field lines. And so it's like you've got a U1 just made of water. And then if you cavitate it and you break the bonds, so it's kind of like a hydrogen engine in a way. So you break the bonds, and then the bonds release torsion. And then basically when that's happening, plasmas are created. And so the plasmas that are created by that thing would be what you'd mistake for the cause of the warp drive. But the plasma is just a side effect. It's actually just a cool firework. It's not what's driving it. It would be the cavitation. So what's pump cavitation? You have a propeller, the propeller, or the impeller, it says here. Yeah, it would actually be an impeller, and the bubbles are generated and they implode, and then you get a large amount of bubbles and you get lots more to cavitation. So, but instead of thinking of it like that, think about it like, so you have a UFO with a hole. I mean, I say UFO, but I mean a propulsion device, and then you have in the hole, there's a concentric circle, and then you swirl water in there and you subject it to electromagnetic fields. You could try it with rotating electromagnetic fields or rotating the water, but even rotating an electric field would get the water swirling because it would basically align with the dipole of the water, and the water would be dragged, and then the water would start creating this U1 circle of bonded water stuck together in that circle as it swirls. And then as you keep pumping the energy, that'll create cavitation. The cavitation creates these bubbles, and then the bubbles are so strong that actually breaks the bonds. And then the paper Barger 1964 that I read that was about cavitation and how weird it is, they were studying that not because they were trying to build a UFO or something, but because they were concerned about how propellers were getting ruined because they were generating cavitation, and then those bubbles would burst and harm the propellers. And so that's why they were studying it, was because of all the energy being generated from where is this coming from and why are they breaking down our propellers. So, but anyway, now I'll go back a bit. So the field configuration isn't a torus. We often think of it as a torus. It actually takes this shape. It looks sort of like a torus when you just look at one set of lines, but then when you get into the 3D, it looks, or even the 4D, it looks more like this. So a Hopfion is a physical realization of the Hopf map. So the shape is a Hopfion. It's a Hopf bundle, but when you talk about the shape, it's Hopfionic. Hopfions are automatically Beltrami fields also. So this is the dynamic mode of the TUFT fiber. A lot of people ask me, where is the dynamics in your theory? And I was like, well, you have to look at the potential. But a lot of people don't realize that the gauge field potential is just the connection of the fiber. And then if you look at the connection of the fiber, see what it does, that's the potential. And ours is torsion. And so torsion is what creates all the forces to some in various ways. So the Beltrami eigenvalues of the S3 radius are follow here. Only some of them are stable as particles, but there are still other eigenvalues that you can use even for cavitation and such. So the Hoppian is that's sort of true, but no, that's kind of trivially true. Like the whole thing is a Hoppian, no matter which eigenmode you're on. But anyway, but the water dipoles don't trace a torus; they trace the Hopf vibration. So I generated some of this based on my paper, and some of it is like, what did you say? This isn't quite what I said. Well, anyway, what is cavitation? Cavitation is what happens when a liquid is locally pulled apart by pressure waves, so it creates these vapor pockets and voids. Rapid pressure drops, liquid can't hold itself together, bubbles form. When it's really high cavitation, bonds rip. You get ultra fast shock patterns and wild symmetry. So negative energy density without exotic matter, this is how we get it. So the Alcubierre drive requires negative energy density. In Einstein-Cartan theory, torsion squared terms enter the effective energy momentum tensor with a negative sign. So this is established. See Troutman and Poplawski cosmological bounce models. They all use this. So anyway, torsion effectively violates the weak energy condition. So the rho effective is less than 0. Sorry if I called that P. It's rho. The torsion modified Poisson equation, delta blah 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 phi t blah blah blah. So you get this where rho effective is less than 0. So the leap is, can you engineer a macroscopic configuration that achieves this? I'm saying the water dipole cavitation mechanism is probably the best way. This is kind of, we already talked about that. Okay, so Beltrami fields are also known as Magnus force-free fields. They're really not force-free because they carry torsion, but we think of them as force-free because the gauge, as we look at it, it doesn't have this. This is gravity. So gravity wasn't treated as a gauge field, partly because gravity shares the same gauge as electromagnetism, which is why electromagnetism and gravity are connected, and why lots of old men in their garage have always said that, like, oh well, I did this thing and it was electromagnetic and I had a radar and I did this and I did that and then there was an antenna, and anyway I got something to float for a few seconds. Anyway, that's because it's not that it was funny, I heard the other guy say there's no such thing as anti-gravity, and that's true, but you can get propulsion from gravity. It's sort of like we hear about the second law of thermodynamics and how that fights with life, but really the second law is what causes life to be able to be here, because it shakes things up, so you get higher and higher levels of disorder. But in those disorders you get like when you shake nuts and bolts, they come together and they join, and then you get higher orders from the disorder, because the disorder generates motion, which allows things to stick together and then create bigger patterns. And so the second law isn't fighting life, it's actually generating life over time by creating these patterns that give rise to new forms. And anyway, it's the same way with gravity. Gravity holds us down, but there's an element of it, this torsion thing, that if you know how to interact with it, it can actually propel. Anyway, so we just talked about cavitation. The Barger experiment, what actually happened. So there was a transducer they put at a point, and then they had the sphere of water. They emitted acoustic waves in the water by just tapping it at a certain point of the sphere. The medium experienced a sharp compressive front followed by rarefaction. Rarefaction triggers the formation of the spherical bubble. The bubble expands and you get all these like shock shells. So that's cavitation. I don't know why I guess they call it cavitation because it's like these imploding bubbles, and it's like cavitating in the sense that it's like making these little cavernous shells. I don't know. But anyway, you get a bright flash, and then they have a bright flash because they give off plasma. There's a set of nested discrete spherical shells expanding outward. It's interesting because you get the spherical shells. It's like the Beltrami effect, the Beltrami torsion. So there's not 2 shells, not 5, but 20. They couldn't ever explain why there's just 20. Physicists expected to see bubbles. They didn't really. The shock shells maybe, but if you were going to get shock shells, you were going to find the number of them from the classical Rayleigh-Plesset, which is sort of from Navier-Stokes. You'd think that you'd get one shock, not like these discrete layers of shocks with quantized looking shells with different like there's this region where they're separated this way, this region where they're separated that way, and this other region where they're separated. It's like there's some kind of almost quantum effect in the sense that there's these quantization patterns that that are discrete. And it's like this looks like it should map to an equation easily because there's these discrete layers, but where's the equation? So they tried spherical Bessel modes, they tried bubble math with Rayleigh Placid, they tried acoustic cymatics, they tried nonlinear steepening, but anyway, they couldn't find a reason for this to be happening. But if you consider Beltrami not just in the regular Navier-Stokes, but if you consider them a potential on this HOP system, so it might really just be in a more advanced level of Navier-Stokes, honestly. But anyway, but the topological interpretation gives us quantized radii, quantized radii, a limited spectral range, and natural grouping into spacing regimes. So at least I have a way to model it, and I modeled it, and I actually got this system to come out of it. I need to start uploading Python codes. But anyway, Barger saw this stuff. TUFT, any polar medium with coherent orientation has an internal fiber phase. The field couples to torsion with this thing. Well, the field is naturally coupled to torsion, but so it's not like the field is coupling, but the matter is coupling to the field, which couples to this thing. So it couples, all matter is created by torsion and linked to torsion, but water has a dipole, which allows it to align in a way that resonates with this shape more easily, basically because it has this dipole that's like allows it to be like holding hands across a system. Anyway, and so it can kind of hold hands in a circle like Michael Jackson, or hands around the world or whatever. But instead of just people, it's molecules, and the molecules are lined up along the fiber, and then the fiber resonates with it, and then it can like amplify torsion in the field this way. Anyway, so during cavitation collapse, the internal phase is not smooth. It has gradient effects. So you get these quantized eigenmodes. Anyway, I went through there and I predicted 20. So you get 20 in this system that you set it up with his radius, etc. Anyway, why the shells group into three regimes: low N region, long wavelength torsion pulses. Then in the mid, there's resonant modes, and in the high, it's closer to the curvature cutoff, and there's compressed spacing. So classical fluid mechanics just can't do this. I don't need to get into why. Space-time manifold has a base and fiber. So the world lines can be thought of as the field lines, which is weird because like in 3D they're field lines, but if you go out to 4D they're basically world lines, which means that you're interacting with time also when you interact with torsion. So when you swirl water at high energies inside a concentric spherical shell, you get pressure gradients driven by the centrifugal acceleration, which pushes water outside against the wall, and then it creates a low pressure zone along the inner wall. And then Bernoulli effects mean the fastest moving fluid sees the lowest pressure, and once that local pressure drops below water vapor pressure, you nucleate bubbles, and that's cavitation. So what makes the spherical shell geometry interesting compared to cylindrical pump or propeller is curvature. The flow can't just go in circles. It has to follow a path along the curved surface, which naturally creates different velocities across the shell thickness. Like you get a gradient, a differential gradient, and along meridian-like lines. So you expect preferential cavitation where the effective channel is narrowest, and the bubble collapse dynamics are shaped by curvature also. But anyway, if you drive by EM instead of mechanical acoustic cavitation, you avoid blade tip vortex cavitation, which is specific to impeller, but you still get bulk hydrodynamic cavitation from the flow itself. And depending on how the EM works, whether you're driving via Lorentz force or torquing, the cavitation conditions shift because the body force distribution through the fluid volume differs from surface-driven mechanical. Anyway, blah, blah, blah. So you surround the core with deionized water shell. Water's molecular dipoles align with the EM fringes, and they kind of proxy a dielectric. It's kind of like a dielectric, which is interesting because people have said that the warp bubbles act like a dielectric, but I can't find that right now, but I remember seeing that. So then the induced shell cavitation, you use radial EM waveguides to generate standing waves. So then So then the EM field lifts to the connection, it connects to the connection, so then it's dealing with the potential. You get the metric perturbed, and via the fiber, you get a pointing vector twisted along S1, which sources a Chern-Simons current, really the Beltrami flow, with level K equals C1, which is just the Chern-Simons level. That's not really particularly worrisome. But anyway, the strength is non-dissipative and topological, so it doesn't break, and the bundle just starts twisting rapidly. And then you can modulate. I don't need to get into that. But anyway, so the cavitation, when you get over 2 pi, like once you've ripped it into another circle, basically, you get a topological horizon linking defect where world lines kind of short circuit. They shortcut via the fiber projection and they contract. So you get this, and basically the space-time is contracting, and you get an Alcubierre-like bubble without negative energy. So basically you're taking the world lines and you're shortening them, and it's like the world is a ball, but you're tangling it harder than it's really tangled. We live on this tangled surface, but if you wrap it like you're a cat playing with a yarn ball and you wrap it into this smaller ball, then you've basically created a torsion drive. You can also open a wormhole this way, but we don't need to get into that. Let's just stick with Alcubierre. So Alcubierre-like bubble without negative energy. You get an induced line element. You get this contortion. It shrinks radial geodesics. When Jack is yelling at AV, he's right about what he says, that it's not like the plasma is doing something or creating something that is like creating effects in the world in a way. You don't have to worry about like air or whatever. It's really just generating a space-time only thing, and the only side effect of that is the plasma, and the plasma isn't doing stuff. It's just a symptom of the electromagnetic energy that's going into this cavitation system. So you basically, when you're breaking the bonds, you're releasing energy. They look like plasma. So you get this asymmetric torsion pump that generates gradients, yielding a thrust, and then you get propulsion, and you also get not just propulsion, you're warping space-time. So you can travel really fast without breaking the light barrier, even though technically maybe you can break the light barrier, but you're not breaking the light barrier within your reference frame, just other people's. And then this is the thing. My parents and brothers saw this Eagle Cam. Well, we all used to watch the Eagle Cam and watch the eagles, and they were hatching. They're hatching. Oh my God. We'd watch. And then one day my parents and brother were watching, and they're like, oh my gosh, there's a UFO. And they're like, my brother's screaming, come, Jenny, see it. And I didn't make it on time. And he's like almost crying. You finally believe this. They're really. But anyway, I missed it because it's like the singing frog. I'm never around when something paranormal happens. Except maybe some fairy weirdness, but that was weird spell kit ages ago. Anyway, so there's no aliens that I've seen, but people have recorded videos. Like I showed you the water spout, and the weird thing zooms by on Tyler's video, and then there are just all kinds of videos on the California coast, Southern California, Catalina Bay Island, and then in that bay there's all kinds of visions of these weird floating objects, and they go into the water and they come out of the water, and everyone likes to watch them, and they record them, and they're like, oh, we saw the things in it. But anyway, what are they doing? What are they going into the water? Well, if they're not like some Atlantean civilization that we don't know about, they're probably refueling. And why do they need water? Well, maybe they need to drink water, but other than just needing to drink water, what do they need water for? Well, I think it's this. So anyway, Alcubierre needs contraction ahead and expansion behind, but in TUFT, spatial intervals are just the fiber structure. So you get asymmetric holonomy density, which is just different twists out here. We're twisting reality differently here than we are out there. And that creates different levels of, the sort of reference frames change. And like we're going really fast out there, but here it just seems like we're just coasting along like a normal Sunday drive. Anyway, the craft never accelerates through space. The fiber geometry it sits in is asymmetrically retwisted. The craft rides the gradient, and the effective metric picks up a contortion, just really distortion, correction this. And then the contortion gives us warp drive. You don't have any exhaust, no inertial effects, no momentum change. So you're riding along in here like you're just coasting, and then everyone else sees you going zoo, 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 because you're just seeing space-time ripple around them. So the topological threshold, again, is this 2π thing. Sorry, I didn't organize this better. Again, my cat was at the vet. He's fine. But anyway, before threshold, I was worried about him, but he's fine. And the fiber identification flips. The S1 over the 2 sphere has acquired like a full extra twist. So it's like getting all tangled up, and except in a way that we can predict. And you get this linking defect where wold lines get tinier. And so this is length contraction. So the fiber connection A is the EM gauge field. Torsion is intrinsic to the fiber. That's just the Chern-Simons number. Like, it doesn't really, the Chern-Simons, the only real Chern-Simons number is 1. You can, if you increase torsion, you can think of it as like this 2 or 3 number, but it's just kind of this weird abstract. It's like you can just put a constant in front of it and multiply by it. You don't have to change the C number, but so it's really just either C is either 1 or 0 really, but people sometimes work with extra Chern numbers. I don't know why. So the geometry is the fiber structure. Modify the connection, modify the geometry. The threshold for a warp is just this topological torsion thing when the holonomy, meaning twist, around a closed loop reaches 2π n, meaning the just multiplied by n, the thing that you're around. The fiber re-identifies and the geometry changes. So if you just keep twisting harder and faster, you can do lots of different things. Water in a cavity acts as a medium where the EM potential A becomes significant, and the cavitation creates extreme local EM conditions that could drive. So basically, you're coupling to the torsion, and then you're amplifying the torsion. Oops, my platform here is. So water dipoles couple P.E. Rotating E fields drive bulk circulation in water. Water physically rotates. Circulating water couples with the Beltrami eigenmode. The cavitation ruptured bonds. Stored vibratorsions released. Coherent torsion burst exceeds threshold. The 2π thing. And then you get a gravitational potential. The warp forms around the hole. I have a paper up right now. It's called Space-Time Torsion is Not Spin Density. And then I talk about this a little bit. I'm still working on the coupling mechanism and some of the math related to that. I'm going to update that paper and there will be more information. I do have some there, but I need more. Why water is the perfect medium. So it has the high dipole moment. So there's strong EM coupling. Water forms stable shells. And then there's no need for, you don't need to start with plasma to do anything fancy. The plasma is just a side effect. Yeah, so we kind of went through this really. I just said it twice. So why does it have to be water? Well, water has the high dielectric constant. It has strong cohesion. It's stable at normal temperatures. Water is really quantum. I know that sounds weird, but basically water, because of the fact that it has this dipole, there are a lot of quantum effects that are easier to find in water than in some more complex molecule with more bonds. Water just has this nice H2O, the 2 bonds. And so those 2 bonds are more coherent than other bonds. In fact, I really, one of the interesting things about TUFT is you can map the, so you can do the hydrogen, you get the hydrogen modes, but then it's harder to do the quantum modes for molecules in the Schrodinger equation. But if you use TUFT, you can get exact molecular modes. I should do that for water, and that might help. So anyway, this is a summary of some of the equations in the coupling mechanism, which I want to do more work on. So you get the fiber phase, the Chern-Simons 3 form, the linking warp is this thing. And then you get the effective metric from that warp, and then you get a thrust. So it's just EM pump propulsion. So those are the main equations. So that's my talk. I really wanted to have the simulation. Next time I'll have a better simulation. So thanks to APEC for running the conference. Thanks to my family, to my cat, to Lou for the math discussion, but that's more like on other stuff than this, although we did talk about gauge fields recently. And then thanks to Dr. Jack Sarfati for discussing space-time torsion. And thanks to a bunch of people that helped me along the way. So that's pretty much it. That's what I had to say.
Jenny, that's awesome. That is awesome. I'm excited that you remember to thank your cat. That is yes. I'm teasing you. Here, let me bring the gang back in here. Who do we have with us? And okay, I'll take down the slideshow.
Hey,
Oh,
everybody.
okay. Yeah. So everybody, please put your hands together for Miss Jenny Lorraine Nielsen. Jenny, thank you so much.
Thank you so much. It's great to be here. You know, I'm really grateful for this group and for how we all talk and share information openly. And I just think that's great.
Oh, yeah. Yeah. Well, and I love it. Like, you're working with a ton of physicists online. You're collaborating too. And so that's really cool. It is good to see everybody working together. And then I love your slideshow. The graphics were amazing on that.
Well, thank you. Yeah, the hot vibration always looks pretty. So that's the one advantage.
Yeah. Well, let me ask, do you guys have any questions for Jenny?
I do.
Yeah.
I
Nicholas,
think
go for
Al
it.
had a question, but I don't know if you put them in. I think he put in. If he's not in, I'll ask. I have two questions. Okay. First of all, what is it that you're twisting?
Time and space and electromagnetic fields.
I beg your pardon. So you're twisting
So it's
field.
the one field. So if you look at my paper, I've basically proven that any unified field theory is on the complex hot vibration, which is a field bundle, which just means a bundle of field lines. So those field lines actually hold the electromagnetic field lines and also the field lines for gravity and other forces.
No, but if I ask you what a field is, you would know and you would answer it's a mathematical thing, stuff like that. It's not a physical thing. That's my point.
It is a physical thing. It's
no,
just
it isn't.
Well, here's
the is not a physical
there's the
thing.
math field and then there's the physical field.
So what is that? So what is that field? Because
have you ever put your hand on accidentally into a light bulb socket and you get shocked? That's the field shocking you.
No, but if you're twisting mathematically, you're twisting mathematical fields. Okay, so
the voltage
my
is the
question is
hold on.
There are two questions. Okay, so what is the field? Okay, if it's not mathematical, is it, for example, an elastic solid?
It's actually not a solid. It's a force.
No, but force has to be something. That's the whole point.
But what is electromagnetism? It's just something that we measure, and we measure we measure the volts of the field. But do we know what the field is? No.
We don't. Mathematically we do. Right. We have a mathematical description that fits with reality. We can predict and stuff like that, and it's good. But we don't know what things are. That's my question. Perhaps
there are relations between things. So relations between effects are what we got. That's all we have. Relations are it. So all you have is one variable. All you have is one variable and how it changes in response to another variable. So that's how all of science is done. We can only measure effects. That's the basic problem of empiricism. So then you combine that with rationalism, which is the idea that there are these forms, like in platonic solids or whatever. So you could think of the field as a kind of a platonic solid on which other things actually take effect, and that platonic solid happens to work and match how relations are bonded across a system. So if you know, for example, how V equals IR. So if you have the resistance and you have the current, you have the voltage. So, we don't really know what anything, what's mass. I remember running around once. There was this one day on campus and I said, what's charge? What's charge? Because a current is like a flow of charge, and charge is something that is all these circular definitions, and it was really bothering me. And then I was talking to one person, he said, well, what's mass? And that really drove me nuts, because what's mass? I can feel something, it seems to exist, it pushes on me, and that's mass. But what is mass? No, we don't know. All we have is the effect something has on us or on an instrument we have. We don't really know what something is.
Because you reference water, and water is very close to an elastic solid in some ways.
What's wet? What's solid? What does solid mean?
All
solid means is that I'm putting my hand here, and my bonds in my field are incompatible with the bonds in this thing, so we don't bond, so we just hit on each other. Yeah. So what's solid?
I think Al is back, so let's.
Yeah. I think one of the big challenges is it's so easy for all of us to get lost in semantics, right? Yeah. And I struggle with that too. It's, and then I think another challenge too is because of the way APEC, not just APEC, but online in general, all of us are drawing from so many different communities and so many different, like, what would you call it, traditions of science and thought, that everybody speaks a little bit different language.
That's
and
true.
and that makes it a challenge too, right? And so, like, the terms that, like, to pick on Drew is from like an intense engineering culture, right? He uses completely different vernacular than someone who is like a theoretical physicist would,
Right, that makes sense. That makes sense.
Yeah. So
I find it a whole lot easier to go through the day by ignoring theoretical physicists, because the other half of my team is one of them, and they're useless. And when you do understand what they're talking about, it's usually like, what'd you have for lunch?
Well, here's the thing, that physics, well, for example, if you're an engineer and you take statics, or if you're an architect and you're trying to hold a building up, all of that is physics, and it was all theoretical. And originally, Newton was a theoretical physicist, and he invented calculus. So all of engineering rests ultimately on theoretical physics. So the question is, well, okay, maybe not just experimenting around in the backyard, but if you're going to build something that works consistently, it has to match the physics.
Yeah. I mean, I think a lot of it,
because y'all keep changing what you call physics. See, rocks don't. You can put a rock on top of a rock on top of a rock, and you build something. And over the last 10,000 years, y'all have changed the definition of physics, I don't know, 50 times.
But
you just keep changing your theories, which are fine. I mean, I love theories. But you just keep modeling your theories and changing your theories to match reality.
If we didn't have Einstein's general relativity, we wouldn't have satellites that work, because they adjust according to time distortion. No, we wouldn't.
No,
we had to model those, and we wouldn't have gotten to the moon either.
Nobody understood what he was talking about when they launched rockets in the 20s.
In the 20s, they didn't get to the moon. They didn't have the right math then, and
they were launching rockets in the 20s.
But they didn't get to the moon.
GPS wouldn't work without Einstein. That's what. So
GPS would work, but it'd be wrong.
It would be impossible to set it up to work unless you had the prediction for what would work, which was for
and the thing that I'm seeing, and this kind of comes out of my focus area, right? But like, and I trip over myself all the time with this. Like, more and more as I'm in this area and as I get older, the fundamental issue that I see is people, because they're coming from different backgrounds, they're not communicating the same way. But then the problem that all of us struggle with is, like, we don't know. It's like I'm saying something, to me it makes total sense. The other person comes from a different background, and it's like they don't get it. But then it's like, and that's where a lot of these arguments originate, right? But like, and you see this stuff online, it's like you get these online hate wars and vendettas and stuff, and it's like, well, wait a minute, where did it come from? It's because they're speaking different languages,
Yeah, well, Tim, and the other thing is that, I mean, there's truths to both sides, right? What Drew is saying, what Jenny is saying, but the thing is that it's actually been an ongoing issue in physics, that we have allowed formalism to kind of lead the way because of the Einstein success, and sort of detached from traditional physics.
Right. Well,
and the other thing that does is that actually harms the theorist in a way that they're kind of blindsided, because, like, for example, there's, when you have particle physicists and they tell you, okay, yeah, there's quarks and there's this and there's that, and you don't really look at the data, you don't like question it, because like you can only do so much. It kind of becomes problematic, right? So we end up in a place where, we have all this great formalism and it can be impressive, but when it comes down to it, it's sort of it can end up being detached, and then the engineers around are like, what are you guys even talking about?
Well, one of the things that I think the big problem is that in the 80s we went into string theory, which is an untestable theory. So then you get people like Sean Carroll talking about post-empirical science, which is complete bullshit. And sorry, Sean. But then you have Sabina talking about, like, physicists get entranced by some concept of beauty, like supersymmetry that looks like another kind of symmetry, but this bigger and better one. And then you look for that, and then there's no evidence it's real. And then they keep changing the equations to try to get this beautiful thing that they wanted to work. And it's sort of like, well, this doesn't work, so let's force it to work this other way. And then you're just completely lost track from reality. But the reason my theory is just a return to sort of the old idea of what a field is. And then looking at what kind of, if you just check the definition of a field, what's the definition of a field of this kind of field, that kind of field, and then that makes physical predictions about how things will actually behave. So particles are one of the things that we're actually better at measuring. So particles actually do exist. They do things. They're effects. Now we call them a particle. It's really just a field effect and how the field is behaving at a certain energy. And if you smash this part of the field together with this other part of the field, it releases some amount of energy, etc. And then you call those particles. I don't really care about particles. The only reason why I work with particles at all is because they make really exact predictions. So like if you're even off like 0.2 sigma, you're off. It's done. It's not real. So the reason I use them is that since I make exact predictions of the particle masses and I predict the neutrino masses, if we can get a neutrino mass and it matches mine, that'll verify my theory. So that's why I liked particles there, just because they make exact predictions.
And that's what I really like about your theory, right? Mm-hmm. So Bucketheim did the same. He also saw this as the proof that his geometrical theory is correct, that he could predict particle masses. And I think so. First of all, thank you for the presentation. It was really, really good, and you always have a very good visual presentation. That I really like that.
I appreciate it.
So I'm a little bit traumatized by the talking point of this theory is the only game in town, right?
Yeah,
from string theory, and you have a very strong claim, basically, that everything that has electromagnetism in it is like needs to have U1 in it, and then it needs to be TUFT, right?
Yeah.
So I don't really agree with that, and please, I would say don't push that too strongly.
Well, here's why I push it. It's the U1 symmetry is established. That's just established by the regular pack. So I just went with the assumption that EM has U1 because that's standard particle physics.
Yeah, but
you know what I'd like to understand, Joel, is what the physical reasoning is for the fundamental axioms or concepts that you use for your theory.
Me or someone?
Yeah,
me?
you.
Yeah.
You just gave the talk.
Yeah, the axioms I use are electromagnetism has U1 symmetry, which just means that like when you have a charge, there's a circular force around it, just like it goes 1 over r squared. That makes a circle around it, and then you measure the force out as the circle expands. So you assume one, it works that way because that's how it always is measured to work. Then you assume there's charge quantization, which requires there to be twist in the field. And then those are the only two assumptions. You have electromagnetism, you have that, and then you get out from there. Those are the only two assumptions.
Hello. Got a quick question. What does any of what you just said have anything to do with propulsion?
Well, here's why. Because if you can make anti-gravity, or what they used to colloquially call anti-gravity, you can float. And so if you do something to the field, if you couple to the field in a way that decreases the gravitational effects in that region, you have propulsion. And so just because I'm just doing math doesn't mean that the math doesn't describe something real. The whole reason that physicists do this stuff is to make predictions about how things will behave under certain effects. So if I can turn up the field with voltage, if I can just create a dense field here with a lot of voltage, and then if I can change the potential of the field to change something in such a way that it couples to the matter so that the matter floats, then I've done something. And so I'm just making...
What have you done? Well, you haven't actually done propulsion.
That's your
propulsion
job.
Is you go way... Hang on. Whoa.
I'm telling you mathematical stuff that you need to do to get it to work. That's your job.
That's wonderful. But you haven't actually done propulsion. You've done, quote, anti-gravity, which I...
Well, anti-gravity is propulsion. I don't really call it anti-gravity. That's just a popular word.
Okay.
What I've done is I've modified gravity. I've modified the gravitational field.
Let's humor our German friend and do a thought experiment, which I cannot pronounce their word for it. So, Joel, what's the word for thought experiment?
Ein Gedankenexperiment.
Thank you. We're way out in space. way out in space. We got our spaceship and nothing else around us.
Yeah.
We turn on our special magical engine, which is done to your math. Can we move?
Yes.
How?
Yes.
We're not coupled to any gravity thing.
What are you saying?
We're not. We're way out in space. There's no other mass around us.
No, gravity doesn't have anything to do with Earth. It's everywhere. Any massive object has a gravitational.
So you're going to couple to the rest of the universe and tug yourself around?
Not the rest of the universe, although technically it's the rest of the universe. You couple to the space around you.
Well, if you're coupling to, but if you're coupling to the universe, wouldn't that go to what Curtis is working with? Wouldn't that go to Jim's work?
Maybe. Yeah. Right off, probably.
So I heard a whole bunch of, I'm going to couple to the Earth's gravity and I'm going to float, and that's.
No, I didn't say anything about the Earth's gravity. I'm not interested.
Well, you said something about coupling to gravity and then you're going to do anti-gravity, and I heard a whole bunch of that stuff.
You couple to space-time torsion, which is in E&M. So really, you're coupling to the electromagnetic field and twisting the electromagnetic field in such a way that you bend space-time. That's
the guy from Japan.
Yeah, Denny's here. Denny's doing a presentation.
So Denny, I want to just make sure I heard you right. You said quantized charge, and the other one was a 1/r.
Yeah, 1/r squared and quantized charge are my only assumptions, and then I get
how do you end? I mean, I've heard you say that you can calculate all the masses, and that's based on only those things.
Yeah, because once you make those assumptions, that means that you have to work with a certain description of the field. That there's only one field that will have those two properties. And
now I have a follow-up questions based on those. Have you ever heard of John Williamson, Martin Vandermark, and the Quisicle Society?
I feel like I've heard of Vandermark, but I don't know about the society.
Yeah, so John Williamson, unfortunately, he passed away a few years back, but he had a model where he took two gamma rays, and in his theory, they would, when they come together, they basically would interact in a way where you ended up getting a positive charge electron formed, and basically the way he described it is the gamma rays would start kind of moving in kind of a momentum or a phase space, and they would move over a torus and have to go around twice to come back to the orientation, and always be pointing the electric field either outward or inward, and then you end up with a magnetic field that wouldn't cancel. So you end up with the spin 1/2 behavior, etc.
Yes.
So that's a well-developed theory. Like if you go look up Quisicle Society on Google, you'll see it. Now that is assuming they're fundamental, right? I'm just showing you this for contrast, right?
Yeah.
So your fundamental is like you already formed the particle. Their fundamental is the field. When you take a field theory like that, there's no sources. Everything on their equation is on the left, and that's
I start with the assumptions about the field too. Although I just go by the field effect, which is charge quantization, which means that we have that. I think they start with that assumption too, which is why they end up with spin 1/2.
No.
Well, guys, and we are at the.
Because then I show you
the 1/r squared.
We are at the top of the hour, guys. So if it's okay, I want to try and segue over to Denny's presentation if we can.
This is fun. Okay.
Is that okay?
Yeah, we will continue this in a focus meeting.
Okay,
Jenny,
yeah. Let's do the theory. Are we going to have a theory meeting?
We will have a theory meeting. Yes.
When is the theory meeting?
We can discuss in the email the final date, but we will do it.
I had a question from Douglas actually, but it was just like a short question.
Oh yeah, if you can go real quick, yeah.
I'm pretty sure he's watching right now, and he sent me this earlier. So he was just asking, you emphasize the topology and not the field magnitude is the primary control parameter. Do you think Beltrami eigenmodes are fundamental objects of nature, or do you think they could emerge from another field, or stochastic field?
The stochastic field would be other. I work with something with Lou Samita. We developed something called the attractor framework, and the attractor is another way you can view the Hopf vibration as a mode of a stochastic field. And so in a sense, I've also proven that any stochastic field over time will eventually get modes that look like the Hopf vibration, but this is beyond So like the question is like, where does this field come from? It could come from random energy. So yeah, it could be stochastic at the base, but this is like way beyond what I usually do.
Okay, I got it.
Awesome. Well, so guys, let's do this. Let's put our hands together one more time for Jenny. Jenny, thank you so much. We may have already clapped a second time. You guys are moving too fast for me, but that's awesome. So let me do this. Jenny, thank you again so much. I'm going to take everybody out temporarily except for Denny. Denny, I am so excited to have you back, man. Thank you.
It is my pleasurable honor, and today's lecture will be quite fast. I'll do what I can. Thank you once again for having me. I hope everything's
and
here.
we'll go to open discussion after that, and you know, when you're done, if you want to hang out and talk, that's cool. And if not, you know, we got the whole crew here, and yeah, everybody's really passionate and excited today. So I'm really pumped up. Let me take myself out, and I'll be here in the background if you need me, man.
Okay, so hello everyone, good morning. My name is Denny, and I put this lecture together not at the last minute, but it was kind of hard to get the technical details. I wanted this to be a bit more math heavy, but unfortunately I didn't get to put everything with the nice little fine ways I'd like to do if that word if what I'm saying makes any sense. In other words, I didn't want to just dump math on people. I wanted to really go through and walk through it, even for lay people, because I'm also not particularly a fan of math. But anyway, the essence of today's lecture will be on what I call solid state. Well, I don't call it this. It's really spatial mass displacement in systems and singular mechanics. Should probably have a little prefatory here. With spatial mass displacement systems, this is a very big camp. We're going to focus on basically two characteristic type systems. They're macroscopic systems. So mass, works. You got really large stuff and you got really small stuff. I'm not here to propose any kind of theory. I'm not here to propose any grand unified theory. I'm really here to talk about a formalism that I've used to work with my own work that has proved to be quite fruitful experimentally and has really great physical fruits as well. It's a normal linear system, so we don't need to deal with any nonlinear stuff, and we'll talk about what that is as we go into the presentation. Make sure my timer is here, so that way I don't lose track of time. So again, didn't get time to do all the nice wheels and whistles. The memes will do most of the talking here. I love memes. You're going to see that I truly am the millennial zoomer here. So first thing we're going to do is recap on enclosement systems. Then we'll go into the two-body problem. That's interesting. You've probably all heard of the three-body problem, but the two-body problem, oh, tongue twister there, is a different kind of hypothesis that was synthesized from a paper by Nielsen in 2017. I actually put it together. I call it the two-body problem because if you ask anyone in classical physics or just classroom physics, is this possible? They just probably say no, but actually that's not correct. If you sit down and you do some of the mathematics with that, we'll go into Mach's principle and some of the different formalisms. I'm going to be flying through all of these things, so I won't be able to get into any kind of true depth. I will only be able to make distinctions. And I'll use some things as I'll put some particular studies on pedestals more so than others, just because of how they contrast, but things will be brought together. Then we have artificial gyroscopes, which are physical entities. So they're not actually necessarily physical objects like a gyroscope. That distinction is very important. A soliton, for example, is a physical object. For example, a mechanical wave, in the way that physicists usually think about it, is a physical object, but not necessarily like a true physical thing that you hold. Okay, and then we'll talk about conservation. We'll discuss three people, Lagrange, Hamiltonian, Noether. And Noether will help us understand how systems are conserved and when they're not conserved. And not having a non-conservative system, one of the systems we'll study is non-conservative, but it's not like slurping energy from the environment. What you'll find is it's basically this optimized kind of resonant system where it'll keep beating correctly. And so it's the motor driving in with the masses that are also moving that give you a nice resonance. So it's not conservative, but it's not like not doing anything. It's doing something interesting. It would make more sense if you were looking at kind of like a harmonic system. It is a harmonic system. Then we'll get into analytical technical methods and their efficacy, a lot of fancy words. That's just saying that there are three different ways that we can evaluate this, and we can evaluate the systems we'll study. I'm going to use two systems, but within those two systems, one of those systems has two different configurations. And we're going to have three separate types of mathematical formulations, which we can go over to lay out how you can get the same exact kind of torque, the same exact kind of force, and also check for the same exact kind of conservation of energy and momentum. And you'll find that everything checks out the same way. And the Euler, Lagrange, and Hamiltonian, they end up being the esoterica mathematica I don't like, but the rotational matrix make everything quite simple because it's just classical Newtonian mechanics. However, there are a little bit of tradebacks when we're going with we're dealing with things like torque and some conservation, and we'll do some discussions and conclusions. Okay, so already killed so much time there. Now we're going to be speeding through. So motivation of today's presentation: clarify lawful solid-state inertial propulsion mass displacement, verify scientific operability through Machininity through physical formulations, and we're going to encourage more science. Okay, so moving forward, I love memes. If anyone has seen this movie, which I forgot, this is my meme here today. So I'm going to be spitting a lot of word salads at you guys. And so, you know, any haters back from my institutional physics days who don't like it, just sit back, and then if the math is wrong, then we'll work through it, and then we'll do even better science. I don't mind being wrong. I just don't like when people say that you're wrong and they don't have any kind of good reason for it, right? So that's annoying. So my apologies in advance. This was supposed to be a historical overview. I have a paper I released not too long ago where I technically go through a lot of these systems here. These are all what we broadly just call as inertial propulsion systems. But most of these don't actually produce any thrust that is equivalent to rocket thrust. Now, there do exist systems which can produce the equivalent of rocket thrust, propellantless rocket engines, which are distinct from just like having masses move around. So they're not the same thing as, say, you would find in the Kennedy drive. I mean, there's great work done by all of these guys, or even Kelly Tippett's machine, gyroscopic machine. These are what I'd call artificial gyroscopes, and there's a way to categorize them. So we'll go into all of that later. Okay, so quick recap. What is implosion? Okay, implosion is just basically a process whereby mass energy is released outwardly and causing the expansion of a given volume. Now, this implosion is just kind of classical physics. This happens at an instant, but the kind of implosion that we've been dealing with is a sustained process. So that so implosion is a process where mass energy or volume of space is compressed inwardly or outwardly. And in general, an implosive propulsive system is just a reactionary system where this implosive process is retained or it's prolonged during the cycle. It is an opened or Mach emitting system in that the generation is implicated with the rest of its surroundings. It does not throw the mass out like conventional rocket engines to make thrusts. Last time I gave a presentation, we focused on fluid-based pneumatic/hydraulic systems. Today, we're going to be focusing on what I've called my specialty, which is solid-based, solid-state systems. So these systems will not be slurping anything like liquids or air to get them moving. Okay, so there are basically 4 categories. I only put 3 here, and I actually threw in the Mach Woodward thing here, but I'm afraid to do that. I like to just kind of treat that separately because the formulations that are used to evaluate that system and how it works is just completely different, but the principles are generally the same. It's still technically a resonator, right? So we have what's called the flying stove model. The reason it's given that name is because of the purported attribution of a particular device to Nikola Tesla, where he's like, I built this flying stove, and basically you'll be able to go anywhere in it and it won't be affected by air. A lot of people mistake it for an electrodynamic craft. It was not an electrodynamic craft. He did have electrodynamic crafts he was working on to exploit electricity to create movement, but the stove was something very, very different. He talked about something called gyro actions. So if that device truly was made by Tesla, the patents, we don't have anything to really confirm that this schematic belonged to him, then this is what it'd be called. We have the 2C Trammell couple mechanism. It's a very unique mechanism because it effectively works like a simple harmonic oscillator that's been constrained. And we have the governor resonator. These are the most scandalous classes of these devices. I absolutely detest them because they should not work. Just based on everything that I've learned in standard physics. So there are many ways to skin a chicken, but most people love a cat. And so there are many ways to go about doing this. So how do we frame this? So first, we got to draw on a lot of work from this guy named Mark Millis. He's done incredible work just overall. If you've done any work in alternative propulsion, you've probably come across his stuff because he's very good at framing scientific problems that can be developed into good theses or formalisms, right? So basically what we're going to try to address, if we want to have a true solid-state inertial propulsion system, it must satisfy the conservation of energy and momentum. This is a requirement. And then it must satisfy net thrust requirements, having unidirectional thrust, and it must have a controllable propulsive effect. And the physics must be consistent with empirical observations of nature. That means that when you turn the thing on, it shouldn't this goes back into my other lecture, but in principle, when you turn the thing on, it shouldn't accidentally rip like a wormhole in time space, right? Okay, so this is just taken from his 2017 paper. So one of the most, one of the most viable methods of doing this will involve involve messing around with the inertial frame of reference, right? So he's completely correct. Completely correct. We can use Mach effect thrusters here, but in recent years, especially the last 2 decades, when people say Mach effect thrusters, they only usually mean Mach Woodward, and that is a false dichotomy. So Mach is pretty broad. And the most developed kind of Mach that has been brought into institution is by Woodward. He's done absolutely incredible lab work. And this is Mendel Sachs. And then, of course, we have Curtis Horneless today, who's also done incredible work with his development of Mach and his solitons and all through the auspices of GR. But I just want to make the clarity here that when we're talking about Mach, Mach is really broad, and there are different formalisms to Mach and different ways to attack Mach, right? And I also want to make clear for today's presentation that the Mach formalism being used today does not require general relativity. That means that it's we're not dealing with nonlinear equations. Everything is being done with simple linear equations. Even though we get into esoterica mathematica with Hamiltonians, Lagrangians, and even the Hamiltonian Jacobi, which I've left out for this presentation, you're still able to get all of the nice results that tell you about force and torque and all of that stuff without relying on any of the what's it called, the auspices of general relativity. Okay, so I used Mendel Sachs as I put him on the hot seat here. But basically, they'll argue that a requirement for Mach systems here is that they have to be, they'll have to be nonlinear. But we're going to show that they can be nonlinear, and you can have force and still have a Machian thing. So anyway, let's go back to Millis's question. Is there a simpler way to frame all of Millis's question in a single sentence? Well, let's go into that. I call this the two-body problem, and how the two-body problem works is this really gross kind of like, I don't think it's gross. I think it's actually a pretty powerful statement. Is it possible to have a driven system so a prime mover can be moved by gas or electric motor? Doesn't matter. And then inside, we say we attach this to a box, and that box contains two principal masses, and we configure them in some sort of way. So can these two masses generate a constant vector of directed displacement or force without any external movement? Now, this is really interesting here, because we're going to need to talk about was it acceleration-based force, which is the kind of Newtonian way of thinking things. And then there is a non-acceleration-based force, which I talk about in singular mechanics. And so that is basically treating the object as a solitonic entity. And solitons really just, they maintain their motion. And so what you'll find is that you do have zero work, but zero work here does not equate to zero motion. You have constant motion with something going on. You've achieved what I call the static, quasi-static equilibrium, and we'll go through all of the requirements for that later. Okay, so now my question to the audience. I can't hear all of you, so we're going to do a little Blue's Clues thing. So let's figure out which team do we want to be on. So we have team red pill, team blue pill. I use the pills because they're the most, I guess, memorable thing in today's world. So let's do conservation calculations. Let's do science and find out. Let's see if this is possible. It's reactionary. Let's explore potential avenues. So these are the other voices that say no. In contrast, it violates conservation. It's perpetual motion. It's reactionless. It's scientifically impossible. I'm MZ, and I'm offering you the red or blue pill. Okay, everybody. So you got 3 seconds to pick. Okay, 3, 2, 1. Okay. Good job, everyone. You did well. You chose the red pill. So today we're going to go on into today's lecture. Okay. So we start with Mach's principle here. So I just took these screenshots. Now, this text here is actually taken from I think it's Lenz and Thuring's paper. It's a really interesting paper. They do a good job of giving a Cliff Notes version of some different versions of Mach. And then, of course, there's Mach's mechanics. And Mach himself didn't do the best job of developing his theory. It's just kind of like, this is an open question here. Perhaps we could say that everything in the universe is influenced by, how did he frame this? So there was Mach's bucket, where he was asking like the bigger question, if we have a bucket and we have that rotating, and then the water starts to move out, and then we also apply that in reverse, and then we have the universe rotating to figure out like what's going on with force. But anyway, okay, so I don't want to go into any kind of tangent because I can do that all day. But anyway, so there are a lot of different formalizations with Mach. Some are more friendly with Einsteinian treatments and Newtonian treatments of time than others. And then, of course, there is the physical way, which we try to treat space-time using either pseudo-Riemannian geometry or just pure Euclidean geometry. I love Euclidean geometry very much, because it is quite flexible and it's easy to move back and forth between things. So we have a Machian zoo, a zoo of different things. I want to also just clarify here, because there's good work being done by Professor Ian McCulloch, I believe is his name. And his work isn't necessarily like an explicit Machian formalism. He doesn't do that, but he does go in and talk about Mach here now and then. But anyway, there are a lot of different theories and things going on in Mach, along with myself as well. And there's a lot of great work that's also been going on with Mach. So we also have a grand unified zoo. And so I want to make a distinction between grand unification theories and just formalisms. So formalism is usually a framework which is developed from an existing body of work to address a specific question within a narrow niche or field. So hence a lot of the Machian stuff. And then the requirements of a GUT generally vary, but they usually try to solve everything. So usually, not GUTs are very specific in the way they go about doing things, right? So they might be trying to unite something within electricity with, say, classical mechanics and so on and so forth. Then you have different flavors of GUT. For example, if you look at the pictures I've provided here, this here is from, I can't even remember his name, Ken Wheeler's interpretation, or not interpret. Ken Wheeler is very interesting, not only interesting, but actually really brilliant when it comes to magnetism, at least how he understands it and how he uses stuff. I wouldn't go about doing formulations that way, but I mean, his mind is incredible. Then we have Gabriel Dias, who did a lot of great work back in the day. Then you have guys like Eric Weinstein. I mean, these guys are just completely different in the way they go about trying to make their theories. But anyway, moving on. So Mach's principle, at least in terms of implosion, what we covered last time, if the universe is a closed system, then its constituent parts are locally open. That means everything else that has motion is just basically a subsystem of the greater universe. So an implosive system does not expel mass outwards. It reorganizes it, just repeating stuff again here. So this is basically how singular mechanics works without going into the nuts and bolts. I love saying that, don't I, of everything. So it can be laid out by these three principles. These are the tenets. In my paper, I actually really lay out singular mechanics, but this is how it can be summarized. So basically, matter, the first principle is really important, is that it's not based on causality. So this is another place where I differ from like Sachs and others in terms of covariance. Matter, so we say motion is, so we have a state with motion, right? It's not based on causality. It's actually based on state. And that is really being derived from quantum mechanics, that treatment there. So matter preserves its energy-defined state of motion unless acted on by an external force, right? State in classical Newtonian mechanics is usually considered, a causality thing. So it's affected from a before and after relationship. I'm even thinking about Leslie Lamport now. But actually, the way we think about state here is more closer to quantum mechanics. And at the end, I'll make a point to draw from, Tipler, about how Tipler believes that quantum mechanics is just a stronger version of classical mechanics and how this notion of state can actually be carried on. Okay, so the next point is that force mediates motion energy redistribution. So acceleration is a finite conservation-bound reorientation of motion under confrontation. And so we have a reciprocal relationship with force here, and inertial frames are determined by shear states of motion energy. This expression I have here will look a little funky, but it has been developed actually independently, even before myself, from a purely thermodynamic way, from a purely thermodynamic perspective. And we're going to see who's done that. She's done incredible work. I've done it through a purely mechanistic perspective. But anyway, summarize how this works. When everything is put together, you can derive what I call artificial gyroscopes, which are basically physical objects, and we have force treated as a process, right? So in treating force as a process, we have Newton's laws. We have Newton's laws carried out concurrently, rather than being put into separate boxes and saying, okay, now we are explicitly applying the second law here, and we have the third law. When we're looking for the third law to be applied, with the actions, like having an action here and a force here. Anyway, so, okay, so these are just old things that I wrote way back when in 2019 trying to describe conservation. And you can go and look at that playlist I have here. It does a great job. But this is the professor I talked about. And if you remember the expression that I laid over here, she's done great work. And she has her own, I guess she's trying to call it maybe a grand unified theory. I don't know that it is, but it is definitely an exceptional formalism. So far as treating force as a process in terms of how even singular mechanics works. She's done a great job through the thermodynamics perspective. I've done a lot of work through the mechanistic perspective. Highly recommend her work. She is a professor, probably Emeritus equivalent in Germany, and has published a few papers. So bottom line here with Mach is just make sure you do the science and just keep the dogmas to yourself. Otherwise, we're not going to be moving forward. Okay, so let's go into artificial gyroscopes. So an artificial gyroscope is a particular kind of programmable soliton. This is very important. Okay, so a soliton is a physical construct, or I should say an artificial gyroscope is a physical construct. It can be actualized as a physical object. So at the beginning of this lecture, I was saying physical object. Forgive me, I just woke up, so I'm a little tired. It's a physical construct. So these are physical constructs. You can't actually technically hold them, right? But they can be actualized as a physical object, as you see here. A purely physical object would be a gyroscope. Okay, so matter waves are an example of something which is a purely physical construct here. And they can also be physically actualized, but they do not equal mechanical waves, right? Okay, so what are the requirements of actually making an artificial gyroscope? The system must contain at least 2 mass parts. Why? Because of Isaac Newton, his third law. That's why. You're not just going to have something magically go in one place and in the other unless there's something like there's some sort of action happening to it. Okay, so then the second requirement is that motion energy must be constrained into a repeatable circuit, right? So this circuit isn't any kind of circuit. If you've ever heard of the brachistochrome problem, right? Which actually relates to dynamics in cycloidal dynamics. Before I did all of this work, when I was in high school, I worked on something called a cyclogyro, which is interesting. So this theme of cycloid keeps coming up. But they're when you have a cycloidal system, especially for these closed systems, they work like simple harmonic oscillators. And so what you find is they're able to maintain a constant change in velocity while also having what you call a constant acceleration, even though when you work out some of the calculations from a purely acceleration-based force place, it would say 0, like you'll find in the Hamiltonians. If you use confrontation, you'll see that you do get a constant motion, and technically that equates to, I guess, what you could say a constant acceleration. But acceleration, in the way that we define it in singular mechanics, just differs slightly in the way that some might be accustomed to. Okay, so moving on, the constrained exchange must settle on to a steady state equilibrium. This is the state I was talking about, where the physical construct really becomes a soliton. And so it continues to move in this constant velocity without being unimpeded by anything else. And believe me, a soliton definitely has a real force it's carrying with it. If you got schmacked by a soliton, you would definitely know. Okay, so next question, who wants to build an artificial gyroscope? We're going to build 2 artificial gyroscopes, which we'll be using which we'll actually be examining for the rest of this lecture. Okay, so let's start. We have to start with using our minds because it's a mathematical object which will become a physical object, or it's a mathematical object which will receive physical treatments, and then it will be actualized into a physical object. So first we'll draw a circle, and we'll call this circle the host frame. I also like to call it a nucleus. And we'll put a dot on it, just like we put a little carrot nose on a snowman, and we call this dot C. And then we look at the edge of the circle. Any point from an edge to an edge of a circle is just called the diameter. We're going to call that r over 2. And we're going to call it r over 2 because any point from the center of the circle is just going to be r, or the radius, okay? Okay, so then we're going to add 2 more circles, and we're going to make sure that the diameter of these circles is equal to r of the bigger circles. So that means that if we cut the circle in half, the diameter of this circle is r over 2, and its radius would be r over 4. Okay, so we have 2 of these, right? This is important. Now let's get physical. Let's add mass. So now it's becoming a real object. We'll just glue a little mass object to the top of this one here, and we'll call that dA, and then we'll glue another mass object to the part of here, and we'll call that dB. Basically, all of this is dB as an entity. And then finally, we'll put it all together. And we put the 2 little masses into a hoist frame, and then we have 2 separate discs here. And we call this an arm. Really, the arm is the same thing as the radius here. Okay, and then we have specific positions here with the way we're going to try and chart this. Basically, the origin would be right here. And then we basically have created a 2C couple, and that's why I put this guy here. I can't say his name correctly, but he is accredited with discovering the 2C couple. And so we have the equations here, which are basically going to describe the rotation of disk A, and then we have the equations here, which are going to describe the rotation of disk B. Okay, and then X is the center of mass of the position. So if you go through and you do the calculations for this, you actually find that the center of mass is up here. You're like, wait, that doesn't make any sense. My intuition tells me the center of mass is right here. I'm talking about the center of mass when the system is actually dynamic and moving around. And so what we have here, like I said, was a 2C couple, is basically effectively 2C couple and a simple harmonic oscillator, right? It literally works the same exact way as a simple harmonic oscillator. We have the equilibrium point, and then we also have the point where we have like a disequilibrium, right? But one thing you'll notice characteristically here is that the velocity is changing. But it's also kind of interesting. Velocity is changing, but we also maintain a constant RPM, which is kind of weird, you know? And so to look at a live demonstration, I've given the QR code, okay? For those of you who are like actually pure millennials, I'm both millennial and Zoomer, but maybe for the millennials that appreciate this, we have a guess that quantum state here. And so it might be non-obvious here. I'm kind of jumping the gun here, but if we do a bit more work on this, we can equate the dynamics of this. I mean, if we're giving a physical description to this, right? No context. its behavior so far as the mass part on the top with A and B in terms of the exchange is actually equivalent to this, like in terms of how you would give the description. This is no different from work I did for a senior thesis here. Not that that was worth anything. All of this would honestly be a better senior thesis, but it's a shame I didn't get to do that. Anyway, moving aside from there, anyway, this is a quantum singlet in the way that we can define its characteristics. It won't have a torque, but it will still have these exchange properties here. So let's move on. Let's build another artificial gyroscope, and let's see how I'm doing with time. I'm going to have to speed this up even faster. Okay, so let's build a donut. I like donuts, but let's keep them nice Euclidean donuts. Anything that's not Euclidean might become kind of dangerous for us, but fun, mathematically fun. So we use this general torus formula. Now let's like cut it into sections. And then when we cut into sections, now we'll just make it physical. So we'll add some, little attributes like little ball bearings on it. And then let's add some mass to it too. So just like we did for the other thing. And then let's configure the mass. So we're configuring masses now. Why are we always configuring masses? Because we're getting mass states. Mass states are a real thing. And you can program them so they have different normal modes in the way that they behave here with the poloidal and toroidal motion. Actually, if you look at this here, when I started this work way back when, I don't know, maybe 7 years ago when I returned to school to try and give some physical articulation for this, I thought it would be really convenient to use the calculations which are used for fusion reactors to figure out the dynamics of a particle. And I had a partially working, I had a partially working simulation, but I had also some problems with the dynamics for certain cases. It wasn't telling me what was going on for the 3-particle pace or the 2-particle pace. And torque was a little pain to calculate. Anyway, these two people that I've crowned with Mobius bands are attributed with discovering the Mobius strip. And the Mobius strip has a lot of interesting properties here. This is a 2-pi Mobius strip, so it's different from just the normal pi Mobius strip. If you walk on the surface of a pi Mobius strip, I believe you end up on the same place. But the 2-pi Mobius strip, if you walk and you were intersecting that, if you were intersecting the cross area of the Mobius strip, you would still get the same effect. This topology is really nice because it allows you to preserve the features of an acceleration and velocity, right? Without messing up stuff. So anyway, this is just a generalized geometric way of looking at the low energy state and the high energy state mass region. And there are ways to calculate that. And then again, we have guess that quantum state. So again, I'm jumping the gun here, but what kind of quantum state is this? Oh my gosh, it's actually a triplet. I can't tell you the number of times I was getting the quantum states wrong with this. It was actually kind of embarrassing. But anyway, it actually really does behave like a triplet in terms of the dynamics and how you stack it, right? So as you keep putting more triplets upon one another. So first, it ends up having a torque. And a torque, if any of you can think about, torque is basically a rotational force. But what I mean by rotational force is not something that's just spinning. So if you can imagine like a Viking boat, and let's say they had their prisoners, and they had this long pole, and on that pole they had perpendicular poles, and they were making their prisoners push the pole, that would be a torque. So a torque would be that instant they're pushing a force, and it's rotating the thing. That would be a torque, rotating the pole, if my analogy made any sense. Okay, so moving forward, now let's talk about conservation. So conservation is very, very important in physics. So you can basically take a collection of things within a system. Marble, this was the best example I could think of. You can move them around, you can energize them, heat them up, you can reorganize them however you like, and the contents of that thing will remain the same. It was a French lady who I think got her head decapitated. Bless your soul, who figured this out. And she and her other friend, was it Mary? I can't remember. Marie Antoinette? Don't get angry at me if I got it wrong. I can't remember. Okay, so anyway, the basic idea is something like this. So for like symmetry, right? If I flip the marbles over, I'm not going to have more marbles than I started off with. If I heat them, you're still going to basically have the same content of marbles. If you shake them around, you're still going to have the same content of marbles. So again, if you flip them over, you're not going to have more. Put Buddy Jesus there because maybe he can do that. But that's for what we're dealing with, what we see usually like in the normal world when things happen, when you flip it over, you don't get more. Unless a magician is trying to pull some tricks or you're, like Buddy Jesus or something. And then if you shake it, it's not going to disappear. And that's not to say there aren't real physical reasons for this. There actually could be physical reasons for this, especially the shaking. Maybe something happened and it tapped into some interdimensional energy and popped out. And our equations are insufficient for that. I don't know. I'm not trying to answer those questions right now. We're just dealing with the very basic low-level things for ground feeders like myself, because I try not to get too involved in kind of the you can do a lot of things with physics, man, and it gets really complicated and confusing. Anyway, let's look at the rock stars who are important. We got Lagrange, Joseph Louis Lagrange. I don't know if he's French, so I probably butchered up his name. Did some nice multivariable math. Physicists use it as an example for mechanistic dynamics of system. We have Hamiltonian, who made a reformulation of Lagrange, and it basically just gives us more information about the system. And then we have Emmy Noether, who is an absolute rock star, who is also unappreciated, like another lady, I forgot her name. In physics, you did not get the Nobel Prize for finding something related to symmetry. An Asian lady, can't remember her name. But anyway, we're moving on. So this is basically how the Lagrange works. Can't go into too much detail, but depending on the kind of system examining, you're going to take your toolbox of physics and look for the right kind of kinetic energy equation that you'd like to use. And then you do the same thing with the potential energy, and then you subtract the two, and then you get the Lagrange. It sounds easy, but it's actually not the setup, because you have to employ something called the Euler-Lagrange. And so this is this kind of like wacky expression. And you find this in multivariable calculus when we're doing something called optimization. It's actually really, really useful. And then you have another portion term with lambda next to this. We don't really need to get into all of the stuff with this, because I'm just going to, again, at some point in this lecture, I'm just going to throw equations at you. I'll say, if you want to go check it out and check the math I've done, you can go look at the paper and go look at things again. But anyway, just some nomenclature that might be helpful for people. Usually we put position as Q here. And so then this dot here, it means change. So for those of you who haven't done calculus, change is basically when something is like being animated. So d over dt, the Leibnizian form is with the prime. So this is change of position with respect to time. And this is literally just position. So where something is, you can think of this as maybe if we're playing a YouTube video and it's paused, we're in one position. This is when the YouTube video is pressed play, and then you see things moving. So you literally see the scroller moving. And so, okay, repeat 30 minutes. I'm doing almost great on time. So then we have the Euler-Lagrange here. And basically what I described here, and all I did here is just basic algebra, add this to this side here, and then we are able to get this expression. Okay, let's move on. So Hamiltonian, it's basically the same idea here, except V is the potential, and then we can add that to T, which is considered the kinetic energy. I really wish we just did like KE plus PE like we do in normal classroom physics, or minus the symbol to give us the total energy, right? Anyway, the cool thing about the Lagrange and the Hamiltonian is that we can get information about the force dynamics and torques based on the energy and vice versa. And we can also check for conservation. And in principle, it's supposed to be a lot easier. In physics, sometimes we have weird problems where they seem kind of impossible, but if you use conservation, you're able to solve them in terms of dynamics. Not that I was good at doing any of those things, but I know that they work. So I can attest that they work. So anyway, this is more information on the Hamiltonian dynamics. So you get this expression here. Again, he just kind of reformulated Lagrange. It tells us about the system's total energy derived through position and momentum. So, and then we have here P, obviously, which is just, I shouldn't say obviously, P, we usually think of momentum. And it's going to become confusing with the, what do you call it, the different variables I'm using. And so P here is the position. And this is change in position, if you remember what I did in the other slide right before in Lagrange. And then Q is the momentum here. And so Q is defined as this. So basically the change is this partial here. I can't remember if it's the del or the other one, but they're specific. They're two different things. And I think they're written the same exact way. And then, yeah, so this is just literally the change. Excuse me. Okay, so this is just the way momentum changes is determined with the way how energy changes, and then vice versa. Here is the way the position changes. It changes with the way the energy changes with momentum here. So momentum changing and energy. And then this here is position with energy. Okay, so then we got the rock star Emmy Noether. So if the Lagrangian or Hamiltonian has no explicit time dependence, it means, and then the system has time symmetry. Does not necessarily mean it's conservative. But by Noether's theorem, we can determine whether it's conservative or not, whether that symmetry corresponds to a conservation of energy. So this here from the Lagrange gets 0. It's pretty good, but doesn't necessarily tell us if it's conservative or not, but gets us really close to determining that. And it's easier for the Hamiltonian. If the Hamiltonian has no explicit time dependence, then the total energy is conserved. And so we have dependence there. Okay, so these are the 3 systems to be examined for this lecture. The rest of everything else we're going to do. They are the singlet and they are the triplet. The triplet is a very special case because, again, we have mass states and we can program this in different ways depending on how we arrange the masses. But the geometry, the prime geometry we're using here is basically a 2 pi twisted Mobius band, which comes with a lot of weird benefits, right? Especially when you're studying the center of mass. So the singlet is just going to be as you see here. The triplet, though, this case is going to be a very, very interesting case. So we'll talk about the non-conservation and even the center of mass. When these two things are moving, the center of mass actually traces a circle. We'll find in the calculations, and it becomes non-conservative because it's kind of like it hits this. It has a resonance to it. You'll see, and then the triplet mass pattern maintains a stable center of mass. However, it has a torque, unlike the singlet. So in terms of the dynamics, it matches with the singlet quite well, except that it has a torque. And then if you just keep adding any number of masses, according to that 2 pi Mobius band, you maintain the torque, and then you have the same force that's keep coming. You have the same force in the center of mass. Really, I should say confrontational force, because we're talking about a vector of motion, and it achieves static equilibrium. But anyway, we're going to ask these 4 questions. Does it produce force? Does it produce torque? Does it conserve energy? And does it conserve momentum? Now, forgive me, because again, I was afraid that if I made a 200 PowerPoint slide, I didn't even know if I'd be able to get through it, because it's my second time ever giving a kind of lecture. So at some point, I'm just going to be like dumping things on you guys, and we'll just be going with speed. But the best way to check or re-verify everything I've done is to really just look at my paper and go through the math. And the most recent one, which I basically uploaded this night, and I'm going to have to go through maybe another week or 2 and just clean up some stuff with the talking. So we have the rotation matrix analysis. I love this because it's just basically purely Newtonian. You know, I'm drinking my little hot chocolate. If this were a brand, it would be delicious, man. Okay, so how does this work? So theta basically tells us the rotation here. I'm using this image here because it's the most accurate way to see what's going on. You have 2 gears, and if the internal gear is meshing or moving with the other gear, it won't rotate in this way. It'll actually like, I shouldn't say this way or that way. It's kind of hard to describe without you seeing it, but you can look at my animations. But anyway, this describes the rotation of the big host, and this describes the internal rotation, phi here, these smaller gears. Okay, so all you need to know, you don't need to necessarily understand this, is that this is what we call a generator when we're doing other stuff. These are used quite a lot within, what do you call it, particle physics. But anyway, this expression here describes the rotational dynamics that are going on for the big circle. And then when this expression here describes the rotational dynamics that are going on with these small circles. And we're going to use them, we're basically going to treat them like operators. And then when we apply them to, if you guys can remember when we built our first artificial gyroscope way back when in the lecture, when we apply these rotation operators to the positions of these, then we can see the full dynamics of their pure rotations in motion. And then when we just slap on force to them, and then we pay attention to a few other things, we can extract information that is precisely accurate about how the system's dynamics should work. And so here is basically that. So the center of mass, as I described last time, when you solve for it, then you can apply the rotation, what's it called, the rotation matrix here, theta. And then you do a little bit of math, you get some help from a nice trig identity here. And you end up finding that the center of mass is right here. Okay, and then this is basically what you get when you sit down and you look at what's going on for each time. And I don't remember how many time steps I divided this, but you can go in and divide it into even more time steps. I have a program where I can actually list each particular, any kind of time you want infinitesimally for this. And then you can find the forces. And what you find is that the force is acting here at the center of mass. And so then this is what you get so far as the energy conservation. These are very basic energy conservations, because for this system here, we can effectively treat it as a spring in terms of the way the dynamics work. I mean, it's really no different from a spring or simple harmonic oscillator. That's why we're able to use these expressions here. So we end up having a constant energy, and this really shouldn't say confrontation energy. It's really just total energy here. Everything's constant. And then we're going to look here. This is kind of annoying, but I think this should be correct. Yeah, it should be correct here. So this unrectified here, this unrectified is referring to the when you don't have the secondary hoist actually moving. So first you have the 2 masses which are rotating, but then you don't have the actual frame also being rotated as well. But when you do have the frame rotated, then you're able to rectify all of its components, and you're able to end up with this. And so quickly, case closed. Are we able to produce force? Yes. Does it produce torque? No, not at all. I did not show the torque calculations here. I'm kind of jumping the gun here because That's also in the code. You can just go look at my code. Does it conserve energy? Yes. And does it conserve momentum? Yes. So let's move on to the rotation matrix 2 mass part analysis. And let me check how I'm doing with time. It's okay. So does it conserve? Oh, all of the questions I probably already asked that. Can't even remember. So basically the same idea as before. We have something to describe the rotational dynamics of the system here. So we have a poloidal motion, which just means the internal rotation of the disk as it's moving. So I wish I had, I need to start bringing more physical objects. If something which is just rotating itself. But then we also have translational motion. It's not really translational. It's orbital motion, which is kind of like a translational motion. And that can be seen with the blue here, right? And that's what this is describing here. And then we have the positions here. So dA basically would describe a disk which looks like this. Its mass state is positioned up. And then we have dB where its mass state would be positioned down. And then these are the expressions that we can use to calculate force. So we're getting to the point in the lecture where I'm kind of just throwing things at you here. So this is just very basic force again, normal Newtonian force. And we can sum this up for different masses. And then we have here for torque as well. And then another thing we have to take into account is the moment of inertia. And so the moment of inertia, if I remember, probably forgot it here. I didn't even add my nice little description about the moment of inertia, but it's something we have to take into account. And when we're calculating it, it really depends on the shape of an object, right? But we apply this formulation here. It's really useful if we're going to be making code. Actually, that's why I use the rotation matrix to begin with. But anyway, this was the Euler something method. I can't remember the exact name, but it works really well. And we use it in mechanics, in upper level physics. And when we put it all together in code, we get motion, supposedly motion, and we graph it. And we have kinetic energy, and then we have potential energy here. And when you add the two, again, simple harmonic oscillator. This system is also still basically an effective simple harmonic oscillator. We have energy and momentum. Now, this calculation here is actually a bit scandalous. And why? Because the Hamiltonian and the Lagrangian will reveal for the two particle case that this is actually a non-conservative system here. So we got some interesting things going on here. So that's why I put not really, but we are able to see that it does produce a force and it does produce a torque. One thing I accidentally left out here was the chart, which actually shows what's going on at the center of mass, and then also with the torque as well. But for the center of mass, for the two particle system, it actually oscillates and it traces a circle. Like that's, I think, about R over 8 or something as it's going around. So let's move. Ooh, that went here. Oh, yeah, I remember what I did here. I got tired. So for the triplet case, it's basically identical to what we just did for the two particle case. But if you want to see what's going on there, just to save time for the lecture, so we don't have 250 slides, this case is closed by code. It does produce force, it does produce torque, and then you do end up with energy being conserved. You have constant work, but then you also have constant motion, which is going on. So it's moving along like a soliton mass. And then this is actually a summary of what's going on descriptively. I don't know if I can read through everything, but I got really tired. And I was trying to find a way to put all of my words in a descriptive, into a descriptive chart, which laid out what was going on explicitly with the dynamics, also with the equations here. But I mean, I think I'll read this off for the Hamiltonian and Lagrangian, because for the matrix, it's not that interesting other than we accomplished a lot of work. We proved torque, we proved force, we proved energy conservation, and basically not energy conservation, really, without using a lot of heavy machinery. So all of this was not with the use of any kind of nonlinear EQs. So mainstream physicists, probably back from school, how I wish they were friendlier to me, will say that, well, this is probably wrong. It was way too easy. But professionals will be like, let's use the Lagrange. And this is usually how chaotic it can get sometimes. And by the way, this isn't even the most chaotic it can get if you're trying to solve some other stuff. We're not even using nonlinear equations. We're using like linear and algebraic solutions to solve this, right? Poisson brackets, among many other things. Anyway, it's Ruthians. Okay, so Lagrangian analysis. Let's start here. Basically, all of this is the same as before here, but we do introduce, I do give a different treatment here where we have the laboratory frame positions of D and DA and DB here. I just do a bit more math here, and then this here. Trying to figure out, I just don't want to keep talking. I just don't want to keep talking. I want the work to do all of the work for me. Okay, so basically here, if you finish all of the math, you get that done. We have L equal to T, the Lagrangian, which is basically equal to T here, the energy. And then we don't have a torque, but we do have a force. Okay, so for the singlet, for the mass positions, they were formerly dA, dB. I do treat them as R sub A, R sub B. And again, this is basically a simple harmonic oscillator. So the Lagrange, which is the action, we can get this expression here. And then we have potential. I really don't want to go and talk through all of this. I could. But what's important to note here, I made a distinction here, and this is probably the only time I'm ever going to make a distinction here, is when you do this calculation right here, using the standard mr double dot, which is basically just saying m times acceleration, mass times acceleration, and you work out the Lagrangian, you're going to get zero force. And if you work it out using confrontation based on the provisions provided by singular mechanics, all that is basically saying the mr omega squared, you don't get zero force, you do have a force. This force is an emergent force. And one of the reasons it's not traced when you do this is this kind of begs the question, is the best way to describe it, that there's going to be a pure translation. And the translation is going to be generating some kind of acceleration, constant acceleration, right? But it has no way of being able to evaluate a system where there are emergent forces that are synchronized with one another. That's a very important distinction. And that's why you're able to get force when you finish up the calculation. So when we sum everything that's going on with Qx here, as I said before, the non-emergent or the traditional acceleration base gives you 0, but then you combine that with, really shouldn't say elastic, should just say confrontation force, you get a directed force. Okay, so do we get a force? Yes. Does it produce torque? No. Does it conserve energy and momentum? Yes. And actually, I don't even know if I have Q sub phi here. This is why we know there's no torque here. So just to go back, because that might have been unclear. Now we're into the 2 triplet mass part case, and I'm still doing pretty good with time. Same exact idea. So same thing, same setup, more or less here. So then we're going to examine, when we do the mathematics, I think I left a lot of it out here. When we do the mathematics of things, we get the torque here, and we find that the torque here is twice the Q sub phi here. This is really interesting. And then we also see that the center of mass is accelerating. And the center of mass, this is what the Lagrange is telling us. In the rotation matrix, when we did the calculations for the 2-particle case, we found that the center of mass was tracing out a loop. And this actually still traces out a loop, but we also find that is accelerating for the normal Newtonian expression, right? So it's kind of annoying and actually kind of weird here, because you would expect it to give you 0 here, right? You would expect there should be no dynamics. In the other, when the other 2 systems, the singlet and the triplet with 3 mass parts, when the calculations are all said and done using the traditional MA type expressions, we end up with 0. But for the 2-particle case, you end up with a non-zero quantity that is accelerating. And so it's really interesting. If anything, it only helps the case because it proves that there indeed is a force coming from this and a torque. But in the confrontation case, we get also a non-zero here, non-zero force, but it says it's constant. And so let's see, confrontation force is equal to this thing. And then we have a torque. And then let's see, yeah, we have a torque. And this is like a breathing system. So this is the resonating system here. That's what this is describing here, the G being a function of phi, where it's like, so the motor is moving and rotating at a constant rate, but the system is also kind of like synchronized. So I guess the best way to describe it is as one mass is tracing up into the high energy state, the other is going to the low energy state. And then they, as they reach a certain equilibrium point, then that role is switched and it's in the lower state. And so then it's flipped, and then it's actually getting more energy from the torque, and then it's going to the low energy state again, and then it's flipped, and it just keeps doing that. And so it's like this synchronized kind of, I think of like a slide. What's it called? What's it called? Not slide, excuse me, a swing going back and forth. So energy here is constant, momentum not conserved. And so momentum, I mean, just so far as Noether goes, not conserved. So Noether is not happy here. So does it concern, or actually, I think I made a mistake here. I shouldn't say. So energy, oh, energy is constant here. I think I made a mistake. Sorry, guys. Very tired. So energy is conserved here. Momentum is not conserved for sure. Momentum is not conserved as I described with what's going on with the dynamics, but energy is conserved. And energy is conserved again in the Hamiltonian. I think I made the mistake of saying it's not conserved. So energy is definitely conserved. I think it's momentum which is not conserved in the way that it behaves like a kind of breather. And in that way, it actually kind of behaves more like the traditional lab resonators you'd find in category 3 systems like Mach stuff. And then again, it kind of reminds me of Michel Broyle's previous presentation. But I digress. We'll keep going on. Okay, so let's move on. We're into the three mass part analysis, and this is where I just start throwing expressions at you without giving you the math. If you want, you can go onto my ResearchGate and you can look at this here. But basically, we have a standing force. So we have a standing force at a center of mass, and then we have a standing torque, so a constant torque, which is also happening as well as the system rotates. And then so far as energy goes, Miss Noether is very happy. Energy and momentum goes. So we have constant energy. So energy is conserved and we have zero work. But then we have, again, it reaches that static state equilibrium. So it starts behaving like an actual soliton. And then when we apply momentum here, we have a confrontation register. So that's where we apply confrontation force, and then we're able to get constant motion. The acceleration register doesn't show everything. Again, it's kind of incomplete. It's not wrong. It's just kind of presupposing that you're going to have a purely accelerated acceleration-based force. And Ms. Noether is happy here. So case closed for this. Okay, so I actually might take time to read through this because I think I'm doing pretty nice on time here. So does it produce force? Basically, they all produce force. There's no question about that. Does it produce torque? Yes, they all produce force with the exception of the singlet. So the way the torque works, this is really important here. So for the two triplet mass part, so both oscillating with a Q sub phi. And so that's the breathing with that term I mentioned, the G as a function of phi, the G as a function of phi here. That's the high energy and low energy state. And it only happens with the two particle state. When you add anything beyond it, it stabilizes and it disappears here. So yes, we end up having a torque, and then it just becomes this like constant kind of processing. So then does it conserve energy? It exchanges energy here is what's going on. And I think this, believe it or not, the triplet 2 particle case is probably the best example of an implosive system, because an implosive system works with the rest of its, what it's doing is actually proving that a system of two masses is not constrained between the two masses alone. It's actually affecting everything else within the system around it. And if you guys can remember my first lecture, I was talking about if the Schauberger devices really did work, they ended up being like a Tesla coil, where a Tesla coil actually utilizes the air, which also becomes a capacitor as well, right? And that's basically the pursuit of the spirit behind implosive systems, is that they're not closed boxes. You can definitely calculate them as closed boxes, but they interact with the rest of their environment. Let's see what else is important. I think does it conserve momentum part? I talked a bit about that already in great detail. Then we go into the Hamiltonian analysis. How I miss my black cat. And I like memes. Okay, so same questions being asked. Everything is basically the same setup as before. Again, the Hamiltonian is just basically a reformulated version of the Lagrangian. So most everything still kind of holds here. And this is momentum here. I'm so sorry, guys. It gets really annoying when you start working with some of these equations because you run out of variables to use. So you start reusing some variables, and then you're not very explicit with what you're trying to say with others here. So momentum here. And then we have the Hamiltonian here. And then same thing here. We have Hamiltonian and momentum here. And I'm really not going to go through the process of all this stuff here. More math. And then after we finish all of this lovely math, we were able to work out the force. And here's the really cool thing. Again, these are just three completely different formulations. So we did the rotation matrix, we did the Lagrangian, and now we're doing the Hamiltonian. And we're still ending up with the same kind of force being calculated at the center, which is fascinating, right? And we're also finding conservation, right? So it was way easier to just use the rotation matrix. And this is why I've never gone to the trouble of using the Lagrangian and Hamiltonian. Usually, a lot of people, when they try to apply these, you can actually feed this into any GPT or the two-body problem in general, and it will probably incorrectly stop with the Hamiltonian using an acceleration-based approach force, because it won't take into account confrontation and how that works, where we treat force as an angular propagation, right, over some sort of characteristic. We say arc length sometimes, but it's really confrontation length, because arc does not necessarily mean the interaction between just like two bodies going like this. It can be some characteristic distance. But anyway, when you take into account confrontation, it's all there. It's literally the same thing that you find in the rotation matrix. And so Miss Noether is happy again with the singlet. The singlet is just the most reliable system because when you do all of the calculations, it doesn't have a torque. It has a force. The force is happening at the center. And then, yeah, this is the Poisson bracket, which is kind of a headache. I'm not even sure that I applied it correctly, to be honest. I'm going to have to go back and look there. But so far as the case being closed, the case is all done. Okay, so let's move on. Okay, so we got the triplet case of 2 mass parts. Does it produce force? And all of the other questions. Okay, let's move on. So we've reached the end. So at this point, I'm just going to be throwing things to you because I got like 20 slides or less. And how much time do I have? About 5 minutes. Yeah, about 20 slides or less. So we have a force here, and the force is not constant. And we have an oscillation here. So it's oscillating. This is with the Hamiltonian. And so let's see here. This basically, yeah, this matches Lagrange. That's correct. We have the torque. Everything that we had last time. Miss Noether is not happy here because Noether theorem is not conserved here. Energy is constant, but the momentum is not conserved. So she is not happy there. So again, I made a mistake here. Forgive me, guys. Energy is conserved, but the momentum is what's not being conserved in the way that it behaves. So it's a non-conservative momentum here. And then we have the 3 mass part case. Same thing, literally the same exact thing as before, except now we have standing center of mass. So we have the forces being conserved, and then this is interesting here. It actually precesses at 3 omega, and I believe that's also the case in the Lagrangian. I don't know if I left that out or not. I can't. It's been so long, so many things I've been trying to do. So everything is constant according to the way that we deal with confrontation with force here. This is conserved, momentum is conserved, energy is conserved, and Miss Noether is happy again. And so case is closed for this one. This is a really nice case here. Does it produce a torque? Yes. Does it produce a force? Does it conserve energy? And does it conserve momentum? Absolutely, it does. Okay, let me see if I want to read through some of this here. All of this is really good because it's like a super Cliff Notes version of all of the descriptions that I won't provide if I didn't get to talk about them. So let's just look at the energy conservation, momentum conservation, and Shipyard is trying to block me from reading it. So I'm going to have to really like zoom in. But anyway, the first for the singlet, yes, obviously it's conserved, and the triplet, it's conserved. Energy is not conserved here for the 2-part triplet case. It's exchanged here. Energy is exchanged here, but it's also conserved. I have to go back and maybe take a look at what I did wrong there. And then so far as does it produce a torque? Singlet doesn't produce a torque, but the triplet produces a torque. And does it produce a force? They all produce a force. So yes, they all produce a force. So far as the torque, only the 3-dimensional category 1 systems produce a torque. The flying stove systems produce a torque. Do they conserve energy? Yes, they all conserve energy. Excuse me. And do they conserve momentum? So only the singlet and then the 3 mass part triplet conserve energy, but the triplet 2-part does not conserve energy. Okay, so this was a meme. I love memes so much. Does the rotation matrix using Newton, does the Lagrangian, does the Hamiltonian? And I verify that they obey conservation and are valid. They are valid Machian systems, right? At least from the definitions that we've put for this formalism, right? So I say, let's team up together, right? So I'm just a different formalization of Mach here. So we have the same outcome, basically singular mechanics. All it is just Mach without GR. That's literally all it is. So it's GR agnostic. It doesn't say that GR is absolutely like negative. It's just, I don't need GR to reach the same conclusions about deriving force. And I can actually apply this to category 3 systems. So the resonating type systems, although it would probably be more of a headache. In that case, it might be easier. I don't know if it would be easier. Actually, there probably could be a simpler way of doing it using the mass states that I already have there. But I won't go into that because then I'd just be like talking, speculating. So then this is Mach Woodward. And I just use Mach Woodward because everyone knows Mach in today's word because of Woodward, who's done absolutely phenomenal work. I say we team up and we work together. But the haters, wherever they are still going to be like, it must violate conservation and you probably messed up in the math somewhere. It's not a real Machian system. And what I'm really trying to say is you're just wrong because I'm definitely correct. And I have not bothered to look at any of the math in any serious way, right? So these are just honest points of departure, right? It doesn't make the other formalism, so GR formalism, wrong. And again, I'm just becoming Middlesex, who's done great work, by the way, absolutely phenomenal work. So I talked about this earlier. So how covariance works. So in my treatment, I shouldn't say my treatment, because I'm not the only one who uses singular mechanics. Kit Grails has done a great job. And if you want to look for actual like textbook physics problems of what we mean as force as a process, which is also really fascinating, because one of the first papers I dropped was gravity as a high frequency electromagnetic wave in a vacuum. And I created like a chart based off of force interactions, because one summer I got to do research with a fellow who was doing work with molecular dynamics. And so we were using, was it the Leonard-Jones potential? And I realized that I could probably guess how, if there was such a thing called anti-gravity or gravity having a repulsive effect, you could probably like maybe guess how it might look like within a certain kind of potential area with the way the potential looked at. But anyway, I bring that up just because Kit Grails also had a graph, which was, she put out before I did, but it was very similar to that kind of same idea. It was just really interesting because we're completely independent. And she has done a very great job with the thermodynamic work. And I've just taken on work with the mechanistic stuff. I should probably email her. But anyway, where was I going with this? I got on my tangent. I think very hyperbolically. So usually things are supposed to come back. And if they don't, kind of end up lost. But anyway, covariance. That was what I was talking about. Covariance. Okay. So covariance here is based on causality, right? So the before and after. That's very important for like my work on time here, but covariance is a little different for what I'm using, because we're dealing with mass as basically an energetic conduit, right? The behavior of the massless motion is dependent on its state. We're really just treating it as a glorified quantum object. But the way that we use quantum mechanics differs. We're not like, we can apply wave functions, but we don't apply them maybe in the same standard way that you would expect to apply them for, say, classical mechanics. And I can go into that a bit more detail, maybe in a different lecture, where I show what happens if you try to frame a classical mechanics problem using the conventions of quantum mechanics. But anyway, we differ in our definition of covariance, but it doesn't mean that we're both not using covariance. And that's me going over, but I've done it. I only have like 7 slides left. And then this necessity that if we're going to have a Machian system, that they must be nonlinear, right? And it's disproven here. Like, these are linear systems and they don't rely on GR in any way. I've been able to prove that just with a system of 2 bodies, you can have conservative systems which independently produce force. And so what I like to say is, if inertia is silver, if gravity is gold, inertia is silver. So if you can basically get like a levitating system, man, I could have hoverboards today just by spinning 2 masses. But I could also be wrong, right? I don't discount the idea that all this could be completely wrong and you run the experiments and that there's nothing there. Although I will say the experiments I ran seemed a bit promising. So anyway, alternative mechanism for mass and inertia, and I can talk a bit about this because it's no secret or no surprise to anyone. Mix and matching things to get a working formalism of what you're trying to do. I don't really care too much about grand unified theories, but I really respect people who are working on them. Like, it's a lot of work. But one which is definitely, or 2, I should say, that have really, they work together. They're basically a glorified version of the Lesage model of an atom, which is actually a really, really powerful tool. Would be the Musha's work with the 0-point vacuum energy. And then because he's able to derive gravity, the gravitational constant just from the vacuum. And I actually have to go back because I actually have a few questions that I can't read. It's been a while since I worked on it. But Theodore Edmund Davis's model is also another one which talks about the same kind of idea with mass generation and how force, the mechanics between force. But Theodore Edmund Davis, unfortunately, did not have a physics background, so he wasn't able to bring any kind of physics equations with it. But despite doing that, you'll find that a lot of his work matches well with people who have done work with the 0-point vacuum. He did a lot of great work. So anyway, Frank Tipler, brilliant mind. Everyone knows Tipler, or should know Tipler in physics, right? His paper he published, he's still alive and he's still publishing papers, believe it or not. And one of the papers I happened to stumble on, pure coincidence, it was in 2020. And it talks about multi-worlds. I'm actually a proponent of the multi-world interpretation of quantum mechanics. And I finished a code, I'll publish it in ResearchGate, where you can actually, it doesn't require general relativity at all. And you are able, and it was actually kind of influenced by the Tobar paper on showing how it is possible to have closed time-like curves without any kind of violation or paradoxes, weird paradoxes going on. And they did that through a very computer science kind of perspective. If you read that paper, it was like an algorithm because they actually didn't invoke any of the principles of general relativity. So we know that, like, if you were a particle and you were trying to travel forward and backward in time, you could do so consistently without any kind of issues. How that would happen, nobody knows. But anyway, I think the multi-world interpretation is just a really powerful tool. But anyway, he uses the Hamiltonian Jacobi, which is a formulation I did not use in the slide because I was just done with doing all of the math here. And at the end, he basically says that, classical mechanics is basically a more powerful version of quantum mechanics. And he explains a little bit more in detail. And he's doing it from the multi-world interpretation. But technically, what I've done here with the gyroscopes, artificial gyroscopes, as I've called them, because they're effectively, they are quantum objects. That's what they are. All they are is just quantum objects which have been repurposed and reconfigured into real world physical objects. And they produce force. And we can do things with that. So this one here is a little inside joke or meme. Newton, I have no problems with Einstein. I want to make that very clear. Einstein was an absolute boss. He's brilliant. I absolutely revere Einstein. Might have a few disagreements with him, but he was absolutely brilliant, like genius. Anyway, so I leave today's presentation with the greatest row of modern science, again. So a lot of people have just wandered off equation through equation. And one of the other things is I guess this isn't like the cardinal sin. A lot of the equations that we develop try to beg the question and say, well, okay, so if this works, then if I do this particular setup, I would expect to get this get this result within a particular kind of category. But we have a lot of less principle-based experiments where, like kind of going back to like the Greeks, well, I wonder if air is like lighter than, I don't know, or I wonder if dirt is heavier than air, or it's more denser than air or something, right? So you need to figure out a bigger principle which can, show this action working here, like making a pneumatic system. And we've just lost a lot of that principle experience. So I was going to say, do your part and stop scientific ignorance by now taking to the lab. There's a really nice experimental setup that you can use called the pendulum test here. I didn't get to cover it here, and I really do want to do historical treatment of what do you call it, in mass displacement systems, because that's what was covered today. These are a class of viable mass displacement systems, which are working from a unique Machian interpretation through solid singular mechanics, right? Again, singular mechanics is a very specific formalism of Mach, which I have developed. It did not come out of a vacuum. So then, final word to them haters, wherever they might be. If you won't honestly try to do the science, then try Jesus. At the very least, he loves you. And with that, I'm not angry. I'm just loafy. Namki Kurat for those who care, because some people are stuck in delusions. And I care about reality. I do care about reality quite a bit. So we got links, we got contacts, we got everything here. If you ever want to go and reach out to me, you can come here. And I want to thank Tim for giving me the opportunity to present, and all of you for just being present, because this was painful, man. This was absolutely painful. Painful for two reasons. First, I didn't get to lay out the math as I would like in a way that is completely heuristic. That makes it easier for people to follow. I was like, okay, we got Hamiltonian here, Lagrange here. This is kind of how this works. And this spits out this spits out this. I think we did a pretty decent job for the singular case, but we didn't do for the other cases. But we made it through. Good job, everybody. Otsukare-sama deshita. To minasama muri denai de. Something like that. Don't give up. Japanese words, Japanese phrases I should know now, right? I don't. I'm trying. Anyway, we're done.
Awesome. Denny, thank you. Thank you. That's awesome, man. That is so awesome. That is so awesome. Let me bring everybody in. I'll take the presentation down. Man, you ran through so much stuff. Okay.
I'm a bit constrained for time, but I think I should be good. Yeah.
Okay. Al isn't here. Gabriel is still here. Jenny looks like lost her thing. She lost her connection. Sure. So, okay. Well, guys, let's do this. Please put your hands together for Denny. Denny, thank you so much, man. Thank you so much. You do amazing work. I mean, you just steamrolled through that. That was amazing.
Yeah, I didn't steamroll it correctly. There were some errors, but at least we're done, right? Yeah, so to speak. And it's been so long because my mind. Recently, I've been working on my old paper, right? So I shouldn't say moonlight. So a consequence of working on this is I've been really interested in time, and basically I like loopholes. So if I'm able to do anything without using the most kind of hard components, I'll do that, right? Leveraging the computer science background. And so my mind has been on multi-world stuff right now and like closed time like curves. And so this I haven't touched in like a couple of months. And so I just kind of try to bring it back. So we'll see how it goes.
I totally get what you're saying. Thank you so much for presenting, though. I mean,
thank you for having me.
You're doing absolutely brilliant work. Everybody that we've had present today did an amazing job. I'm just pleased as punch. I'm so excited. So, okay. Well, yeah. Did you guys have any questions, or I mean, if we could go to open discussion, or we could do lab updates. It's up to you guys.
Not the brightest here.
I would have a question, but I'm totally confused with what you just said. Okay, there's so much information.
Yeah, I know. I'm sorry.
With relation to propulsion, there are two companies that sort of have ideas that you do, and they have satellites in space. This is Evo. I don't know how you pronounce it. And there's one company in Italy, similar thing.
Gennaro Aerospace, right?
Yeah,
So Gennaro Aerospace, no, that's exactly what I covered here. So I did not cover the Category 3 systems, but Gennaro Aerospace is a resonator, and it's actually based off of Henry Bull's work. It's not based off of Henry Bull's work, but if you examine the work of Henry Bull, it's basically a dampener. And in my paper, the recent one I published there, from a classroom physics perspective, I described what's going on in their work, and you can read their patent because all they're doing is just using resonant modes and they're fine-tuning them. And actually, you find that there's a lot of overlap with what you find with Woodward's stuff with Mach in terms of the pure experiment, what they're trying to do, right, with certain kind of modes. So that's exactly what Gennaro is doing. They're basically just having a mass and then they're oscillating it, right? But you don't just oscillate it. There are some other requirements you got to have there with the dampening and some other stuff that's going on. So,
but what bothers me, is okay, it may work, okay. How do you transfer the energy to that system that provides propulsion? Because if you start moving, you're getting energy. So you have to get that energy from somewhere. And that transfer of energy, so you transfer that mechanical energy to what? So you're pushing against something. You have to be pushing against something.
Yeah.
Well, I mean, what I interpreted was you're pushing against virtual particles, right?
Yeah, actually, so I didn't get to go over this, and this might be the subject for a different kind.
I just looked up that Gennaro thing. It's a micro thruster.
It's a micro. So yeah, it's a micro thruster. If you look at
it's a rocket engine.
Yeah.
It doesn't matter how clever it is.
Well, it's not. So, yeah. Well, just one clarification. So rocket engine is spitting stuff out, but Gennaro is not spitting anything out. So it would
looks like they are.
No, they're not. Where does it say they're spitting something out? I want to see where, because I've looked through the patents.
I agree with you, Denny.
Okay. Yeah, they're not spitting anything out. It's not a rocket thruster. It's a
microjet array.
Engine. That's what they're calling it, but it does not spit anything out. You can go read the patent. In fact, I did a case study on this inside of my paper. So I am pretty confident that it's not spitting anything out. So, I mean, it's as much a rocket engine, if you will, and it's much the same way that the EM drive and then also the Mach effect drive are rocket engines, if that's what you want to call them. I think the reason they're calling it a rocket engine is because it's more friendly for people who aren't familiar with the physics. And if you don't call it a rocket
engine because it's a rocket engine, it uses microjets.
There are no microjets. What are the microjets? Tell me what they are.
It says there are microjets.
So but what are the microjets? Show me in the patent where it says the microjets, because I've read through the patent, and so we can go through the paper as well. In fact, maybe if I have to, I can go pull it up here, but there are no microjets.
There's a microfluid cavity energized by a microresonator.
Yeah, so you know what the
orifices.
So you know what the micro.
Do you know what through a micro orifice? You have a rocket engine.
No, but you want to know what the microfluid is, and you want to know what the micro orifice is, right? The micro orifice is just basically an electromagnetic coil. I mean, literally, you can see that in the patent. I can show you the picture. The orifice they're talking about is just an opening of free space for the inertial impact to happen with that mass. So they're just using a bunch of like flashy words. This is very common when you're looking through patents.
Yeah, I think what you're saying is that they're
I can't hear you, Curtis. Sorry, you're
shooting the water. Can you guys hear me?
Your mic is being weird.
Yeah.
Okay.
Your microphone.
Resonating. You have two mics.
Yeah.
Maybe. Yeah.
I have two mics.
Your microphone got abducted.
Okay. How about?
But yes.
How about now? Not conserving.
Yeah. You're not conserving energy or momentum.
Yeah.
Or Or maybe you are. It's just being lost, dissipated. It's just.
I don't know.
It's like a rocket engine.
So Denny, are you saying like hits a wall?
Yeah. It's basically so it has a mass.
It's
with two electromagnetic coils, right? Actually, there are different configurations they have. And they're basically having it rebound. That's all they're doing. It's an oscillator. It's effectively an oscillator if you look at it. And then there are certain kind of modes that they calculate within it to have more preferable kind of oscillations.
So that does sound
yeah, Curtis.
By the way, Tim, I think Jenny's trying to get.
Okay, yeah, and Curtis, I think your computer, you may need to reboot. I think it's your machine. I'm not sure why, but it's.
I was going to say that there are some overlaps between some of the methods that Denny is mentioning and my methodology. For example, the superfluid being resonated, and also the resonator between two different systems you were just describing.
Yeah. And also, Drew, forgive me. That was more of my academic nature coming out and being quite aggressive. I get pretty defensive because people are so ready to come at me. So almost like, where? Okay. Show me. Where?
Asking no worries at all. So is there from your perspective in the resonator where there's the two things that are interacting and resonating and interacting, I'm trying to describe what you were just talking about. I
hate that system.
What is the mechanism for that generating propulsion in your, know?
Yeah, so I call those category 3 systems, and I absolutely detest those systems mechanically because they should not work. When I say they should not work, if I gave it to anybody in a standard physics problem, the mechanical systems, if you look at them, they should not work. And describing like how they are working in terms of their anatomy is really strange. So basically, I've studied two types. You have a mechanical system, which is just a governor, if you've ever seen a governor. So it has a spring, and that spring has a certain K to it. And then you have a rotation. And what's basically happening is you have an implicit, so the rotational force which is coming outward is actually also being redirected inward, and it's also providing a force. This is a very oversimplified way of putting it. But that should not work. Everything should cancel out.
But but actually the Beltrami flow would do that. It would go in. Yeah.
But the only way I've been able to figure those things working geometrically is with very specific geometries. So I know for a fact, so the 2-pi Mobius band is one such because it's a non-orientable geometry, right? And so it comes with very good benefits. So I know that for a fact. The 2C couple basically works in the same exact way because it comes with those same exact benefits.
So my theory is basically a whole bunch of Mobius bands. The field is essentially Mobius.
No, your theory is correct. What you're saying, so I didn't get to talk about with the other stuff, right? So I'd like to do a presentation on Theodore Edmund Davis's stuff. But basically, I argue that the space-time quantum volume, and I'm just using the formalizations of fluid here, right? The superfluid vacuum, right, is what we call, or what I call the superfluid vacuum, or the space-time quantum flow, is full of a lot of small particles which are bumping into one another, and sometimes they move faster than light speed. But the fundamental behavior, the character, like what they're doing in terms of the mechanics at that small level, is basically small little Mobius bands, 2 Mobius bands, right? Now, they all might not be 2-pi Mobius bands, but I'm able to actually show that force, so something which allows them to maintain a constant motion as a soliton. I can show that this happens here on a small scale, and I can also show it's the same thing that happens on the large scale. So I would agree with you there in terms of that. But I mean, I'm not into like all of the heavy machinery of all of this stuff.
No, that's okay.
I saw some of your stuff.
It's interesting to me because like it's a twisted circle is basically the basis of how a non-trivial Hop vibration works.
Very powerful tool as well.
Yeah.
Hop vibrations as well.
So I'm thinking that if you could you send me your slides?
I could send you my slides.
I'd love that. And then maybe I can come up with why some of these things are working, because like I was thinking that some of these things that turn electromagnetism to seemingly anti-gravity is working on. It's basically space-time torsion that's causing it. The effect.
Yeah. And I think the other thing in the paper, so the paper I'm working on, reworking a lot of stuff in the part 3, because I basically use normal modes with math states. And I basically tried to just hypothesize a field equation, 2 field equations, right? But if you do the dimensional analysis with the curl, so the curl is actually really good and it can work.
Yeah, the curl is the thing. Yeah, it's the curl of the field vector.
But the problem with the curl that I use, so basically all I did was I repurposed something called the spectral energy.
Okay.
And so
close.
it's a very, but I mean, it really comes down to energy. And then you're going to be looking at basically when we're talking about confrontation, we're looking at characteristic distances, right? But what's happening with energy is still fundamentally the same, right? So in principle, it looks well or right, but the dimensional analysis was wrong. And also I made a weird error
it'll work with Beltrami flow.
Maybe. And then the other thing I do is that to deal with time, because time is physical, I try to make time a physical entity by basically just working with the cutoff that draws from how Puthoff's work, but then also with Musha, who's also drawing from Puthoff's work. And so I name these entities. Everyone knows or has heard, I absolutely hate it when physicists just start making up names for particles. So I was very annoyed to use this. But I call it a kaon. I don't call it a kaon. They're called kaons, and Ricami and some other people way back when were talking about this really smart Italian physicist. Yeah. And I just call it a kaon, or I call it something else. Same thing, same exact thing. Yeah, okay. And basically, all I'm saying is that, like whoever mentioned acceleration here, it's pushing on something. When anything is moving, if you move at a fast enough speed, what you actually have happening is you're pushing on the space-time quantum vacuum, the fluid, right? And so that's also having basically negative energy is being imparted to you. It's almost acting kind of like how would you call it, like resistance within water.
Right. As you get towards C, you're going to get more and more resistance.
Exactly. And so there are some other things which come with that. Of course, if you can figure out a kind of shielding, then it's very easy to basically make faster than light from point A to B here and some other stuff. But so tachyonic stuff, those particles, they move. I have my first paper I put out on gravity's high frequency wave. The first section is just one page, lays it out really well what I'm trying to say. Other stuff in the math might not be so correct, but everything else is pretty like fluid.
That's okay. So. It's interesting to see people working with this stuff at all. So yeah, that's great. I think that your math, I'll take a hack at some of what you're doing and see if it works with Beltrami better, because I think that the resonance modes will make sense once we put it there. Anyway.
I'm all for the resonance modes. Yes, sir.
Okay. I don't want to sadden you, but it's a micro rocket engine.
Okay, what do you mean by micro rocket engine? Tell me.
They use acoustic energy to move fluids at high speeds and eject them.
So answer me this: is an acoustic engine, or is an acoustic whatever you just said, a rocket engine or a jet engine? Answer me this, right? Is it spitting anything out?
Yes, it's spitting out whatever fluid's in it.
The question is, do they get thrust from exhausting mass, right? Is there the delta M, delta T impulse? Is that what they're using?
Yeah, that's the question.
That's the question.
It almost looks, because I only read the beginning of the patent, but it almost looks like the old German, no, not the German one, the whatever it was, the buzz engine, where it actually sucks in the gas, adds energy. Yeah, the V1. It sucks in the buzz engine and shoots it out at a higher velocity. It almost looks like that, but
I don't know.
It's talking about microsatellites, which tells me that they're simply turning whatever the thing is. It's probably a postage stamp size thing with 1 million cells, and each little microcell produces about 2 micronewtons of thrust. But once your little cell runs out of juice, however much juice you can pack in that little cell, once it runs out of it, it's a paperweight.
Yeah, so I mean, two things.
I'm happy for them. They created some really interesting acoustically accelerated fluid, but it's just a rocket engine.
Well,
so
here's the
two things there. Just so I just want to make very clear: in no way with any of my work am I trying to imply that I'm sucking energy out of the vacuum right now, right? Like, so I agree with you. When you don't have something like a motor which is being powered by something, it won't work. It's as simple as that, right? So none of my systems are trying to.
You can pull momentum out of nothing. I do it every day.
Well, I mean, sure, okay, but I'm just saying in terms of people listening, so that they understand that it's a prime mover and all that stuff. And then the second thing is, I'll look back, I'll read more, because I don't know that I'm totally convinced, but I hear you and I get what you're saying with the microscopes as well.
Basically, the Barger sphere, I think that if you you could turn that into an acoustic resonator propulsion thing too.
I'm afraid of dealing with acoustics. So yeah, you guys like Drew and the guys at what's it called?
with mass ejection rocketry. I don't care how good it gets. You're never going to get above 20,000 ISP.
Well,
Okay, you're
right, but
you're
acoustics
really not
aren't.
even going to get to 20,000 ISP, but you're never going to get above it. I don't care how good it is, because you'd be accelerating the ions to the speed of light, and you're not going to have enough energy to do that. So,
Well,
you're completely
there's
completely
nothing
correct
in
there.
mass ejection rocketry that is of any value to this group. Because
well, I agree with that.
They already have the best
But
engines in the
acoustics
world.
aren't identical to mass ejection rocketry. They're similar, but not the same.
They're not the same. Yeah. So
could you say all that again, please?
Mass ejection rocketry and acoustic levitation function differently. They're
Acoustic
different.
levitation requires that you have a fluid in the system that you're
No, it
bouncing.
actually doesn't. For example, you can see that they've levitated ping pong balls with acoustics. So like
the fluid in the system is air.
well, gas.
Okay. The definition of I have a degree in this. The definition of acoustic levitation is that you're bouncing mass off the ping pong balls, and you're giving the energy to the mass by the acoustic waves that you're superheating the gas.
But you can use acoustics to couple to things that aren't necessarily functioning in Newtonian physics.
Who cares? Once you get out and vacuum, none of this means anything.
Well, I understand what you're saying there.
And unless your rocketry works in vacuum, you're not getting to Mars.
Well,
may I just chime in here? So Drew, so far as what you're trying to say with the acoustic stuff, the medium, the fluid you're talking about, yeah, totally. Like air or something has to happen for the acoustic propagation to take place, right? For the cavitation.
Yes.
I get that. Like, so I have no problems with that. Totally agree with you there. So I'm not, again, category 3 systems, I did not cover at all in this lecture. So I'm more than welcome to like going back and like really critically looking at that paper again and examining it. So I provide one solution or from my readings of the paper as to how it's producing force right there. But I also don't doubt your work. Again, you guys are doing absolutely phenomenal work. And especially you guys who work with the small little mass stuff where you have to do a lot of fine tuning, literally fine tuning, right? So I get that and I understand that. But I can definitely say confidently, and like you said, 2000 ISP, I'm not looking to make a faster than light drive with any of these things, right? But hey, if I can get a hoverboard, man, or hey, if I can even get something which is a great conveyor, there's no problem with this. And in fact, it's a lot cheaper to just have something which is built off of purely aluminum and tungsten as a solid state propellantless rocket engine. And that's basically my whole platform with the solid state mass propulsion, right? And it's also to just show that there's a link.
Solid state mass propulsion. Are you going to emit anything from the bottom of your hoverboard?
No, there's nothing being emitted there.
Nothing is emitted. So,
but I think it's because you have a fundamental misunderstanding of the two-body problem. It's the reaction between the two masses. So it comes down to Newton. And I think you're misunderstanding it, right? So I think there is a category, and
I have no idea what you're talking about.
Okay, so
I love your presentation, dude, but it was completely lost on me. So
okay, that's fine.
Just take a super easy example, and you tell me how you're going to levitate a hoverboard.
So I actually did. I gave you 3 different examples. And so the easiest example, if you'd like to see, is with the 2 pi Mobius band. And all you have to do is literally have 2 masses, and you have them configured in a particular kind of way. So you have a toroidal and a poloidal rotation to them. Now, these aren't weird words. All I'm saying is you have a regular rotation, and then you have an orbit to both of them. Right. And if you do the mechanics of the calculation, you will find what I'm saying. Even if you don't understand it right now, just go and do the math. That's what I'd say. In physics, go and do the math and check the math first.
So
there's no possibility I'm going to go do the math on anything. Curtis, is there any way you can spin these 2 little bands and generate thrust in a vacuum?
So now is Curtis the authority on this subject, right?
There is a way to do it.
He's closer to reality than you are.
Well, there's
really? Okay, that's great. But I mean, here's the thing, right? So I don't mean, and I'm not. I really do respect Curtis's work. I'm not saying like, oh, is it? But I'm saying you just asked him directly as if to say, okay, well, you definitely know if this works or not. But you didn't even try the math. You didn't even look at it.
And you said, spin 2 shapes.
My thought would
I can show you that your math is wrong. And I can show you, explain quickly, okay?
Okay.
See, basically what we talked about you eventually we agree that you have to push against something like virtual or transient particles.
You
Your
don't need the
math
medium
says
for this.
nothing about that.
Because you
without
don't need the
pushing
medium,
against
and I keep
anything.
saying that you
All
don't
you
need
need
the
is a
medium,
field.
and that
You don't need particles. You need a
I don't
field.
even argue for a field. That's
Yeah.
the whole principle behind confrontation is the two masses, but I don't think anyone's really reading that correctly. But you know what? It's fine. Leave it as it is. Right
No, I
now.
think
I can make another
I
No, but
understand
you
what
have
you're
to
saying.
explain that. I'm not saying that you're wrong, but if your math doesn't say that you pushing against
what is the math?
something,
My thought would be that
It has
to go
to.
back and I mean the cool thing about YouTube, right, is everything is recorded. So my thought would be to go back through it and then review that. Yeah, that'll make life easier because
And if you send your
I mean,
notes that would help.
Because I do feel like I'm going kind of insane. So when I hear people say that your math is wrong and this and that, I'm like, okay, well, first of all, in the presentation, and I've been saying this from the very beginning, I have an entire lecture series on confrontation where I lay out the math for between two bodies and how you get an emergent force, right?
No, it
Without
actually
anything
doesn't
related to
sound
the
too
medium, right?
confusing.
So I would recommend first looking at the first video on inertial confrontation there, right?
Well, and
So then
Denny, could you send that over? Could you send those over?
It's on the presentation there. So if you look at the one with my little smile and the other stuff, it's right there. The playlist is all there. It's on the presentation. It's on the presentation. You can even just go to my YouTube channel. You can go and look at it, right? So it's an entire long presentation on this, right?
Yeah.
Because this entire misunderstanding keeps going on. And it's just so annoying to kind of, like, I keep saying it again and again and again. And, you know, I can repeat things and say, I believe this, I believe that.
No.
But, you know, if
You
someone
have
just
to
wants to
math, like,
say,
work out step by step something.
but if somebody just wants to say, okay, your math is wrong, and I didn't actually take time to like really go through any of it, and I maybe fed it into a ChatGPT engine and it found an error here and here because it put into a category error, then that's not good research. That's not good science. I really, when I do research on a subject, I try to look at the paper, I make highlights. In another presentation, you'll see that I did, it was like Henry Wallace, his gravitator, whatever it's called, right? Looks so esoteric and strange, right? But I took time to read every single line of it and try to understand the physics behind it.
Okay, sorry, I have to apologize. I said it wrong. Okay, it's not your math is wrong. Okay, you explaining something that I don't see a principle. There are two principles. You either look at the Mach principles in your case, or you pushing against the vacuum foam. That's all there is, and that's all I need to do. It's I didn't say, okay, your math may show some effect, but if you don't have that effect explained in physics or in physical interaction, that's...
You know what? Yeah, you know what? I agree with you. If I don't have the effect explained in physical interaction, then it's null. You're completely right. And it either has to be explained through either the Mach effect or something else. You're completely correct. You're right. You're right. And so I will try to look at that again. And maybe I just need to figure out another way of saying something.
But I'm not saying about the Mach.
Saying that there's some kind of inertial interaction. You're saying that
and for the record, I'm an experimentalist before all of this stuff right here. Had I not run out of funds, I could still be able to do this. But one of the things I've done is open sourced everything. So I'd be more than happy for someone to just build this and disprove me, right? That's fine. That's fine. It's just it's good science. Because then I know it's wrong. And then I just like back off and I'm like, oh, okay. But at the very least,
I'm saying just show me the principle. I mean the reactions, not math. Okay.
So I've shown what I can now, and hopefully in the future, as I
it's probably Nicholas.
All right, that'd be great.
It probably works.
I'm in the same position as you are.
I think there might be an explanation for what you're trying to say here. You're saying there's an inertial interaction in a two-body problem when you spin one thing this way and one thing this other way. Is that what you're saying?
It's not necessarily spinning, no. So confrontation just basically says that. So if you have two masses, right? I have a mass here and I have another mass here. If I flick one, which is imparting energy to it right here, that causes a reaction according to Newton's third law, right? So the equations that we use to describe that relation that's happening here. So as this is moving, if you actually look at...
So what's the coupling mechanism between the two masses?
Just a string. That's it. A string. A tension. That's it.
Okay.
So in all of these systems, the coupling is the frame themselves, right? Yeah, the coupling is the frame themselves. They're not happening in like space. They're coupled to. So the frame is the string, right? But if you look at the equations of motion that are happening here, that's a linear hit that you have here, or a lateral hit, which is better, right? And so when you hit that here, this, in responding to this motion here, this will cause it to slow down, right? And as it's causing it to slow down, as it's causing it to slow down, this causes a rotation to it, right? So this is the rotational force that you described, but this is more linear, right?
Right.
And then you can extrapolate off of that. And if you don't care for anything I've done, at least read Britt Calais' work. Go read her work as well, because she does the same exact thing
Who
but
is it?
from thermodynamics. Look in the slides. So when I talk about what is it called, Mach principle, I mentioned a completely different professor from Dresden University, right? Who's also argued, and she also argues about this in like, was it Machian terms and other stuff, but from thermodynamics.
Yeah.
And so in terms of presentation, look at the problems that she does, and work.
Have you tested it with pendulums?
These are pendulums.
It looks like just pendulum. Yeah, okay.
They are simple harmonic oscillators, right? They're simple harmonic oscillators, but there are different ways you can have different harmonic oscillators here, right? But I will say that it does get annoying when you keep trying to say the same thing in many different ways, right? And then you give people all of the stuff and they just don't bother. Instead, it's easier to just go, it doesn't work. It's not, or it's incorrect. But to that effect, I understand.
Welcome to our world.
Hey, Denny, I have a question for you. Have you looked at Andre Aziz's work? The Weber electrodynamics and the he actually applies the Weber force law to kind of Newton's theory.
Andre, what's the name? Could you like type it in the
Aziz,
chat?
ASSIS.
ASSIS. Andre.
Andre.
No, I don't think I know him. Is he?
So when you're talking about Machian theories, basically, other than mine, right? So mine is
there are many
developed.
Mine is my theory is Machian.
There's Carver-Mead's G4V work, which is based on Einstein's work pre-GR. And then there's Andre Aziz actually has a Machian relational theory that is basically goes back to Newton. So he's using Newton and Weber, extending Newton to be relational. Of course, it's instant, but it's based on force laws and that kind of stuff. So I'm just kind of curious if you when you did the work you're digging, if you looked at Carver-Mead's G4V and then Andre Aziz's Weber kind of relational mechanics.
So there's a lot there, and could you type in, put his name in the box, because I would definitely appreciate the ability to go and like read through and look through that. So because there's a lot of work with Mach. So even Mendel's work is a lot. Your work is a lot. Carver-Mead's work is a lot, right? So going through all of it, I didn't do a historicity on Mach because there's just no way I had time for that. And but there's a lot of good work on Mach that's been done. And you said it was before. So Einstein was more nice to Mach, like 1915 or so, right? He started to lose faith in ever reconciling Mach with GR later on. But you're saying that his work kind of like takes off from there and is able to develop from a Newtonian place?
Yeah. Well, no, that's Carver-Mead, right? So G4V is based on basically the relational work that Einstein was doing before he went to the tensor stuff. So
I've seen. Yeah.
I
have to go through and look.
So basically, and Carver kind of he shows that he could have gotten the bending of the light, that made GR so famous, but there was a step missing, and he kind of shows that in his in one of his presentations. But yeah, so G4V is more of like a inertial direct theory that's kind of, I would think it's one of the more modern, better ones, right? So you have the Siyama stuff, and then there hasn't been that much since then. Of course, there's Hal Fern's Hoyle-Nalekar, where she fixed that theory, and that theory is based on GR, but it also adds a fluid, right? So that one also is good. But in terms of what you're discussing here, I think it kind of reminded me of Aziz's, the way Aziz does stuff, and I see what you're saying in terms of the nonlinear dynamics of mechanical systems. That is an important aspect of things. And that's in my work, I use that quite heavily for the particle sector. So I kind of like that you kind of hint at that, but I would think you might want to go a little bit more in depth with that, right? Because that, when you're doing Lagrangians and Hamiltonians, you can start writing difference equations and like going and kind of like seeing what we can do in nonlinear dynamics, and that's kind of where chaos comes in, and that's kind of the, you know, where sometimes you can and may or may not be able to predict, right? It's depending on initial conditions, you know, you can get something where you can't necessarily predict the motion. But in terms of like energy levels, you can actually write things out and constrain what a system is going to do if you're talking about just standard mechanics. So
I would say, please put this name inside of the box. It's just more reading, and I love learning more than anything else about all of this. So I really, really do appreciate that. And the nonlinear dynamics, I was just trying to prove that it could be done without nonlinear dynamics, but it could end up that all of this is really just like not functional, right? At the end of the day, like, and I'm perfectly fine with that. I don't mind. That's a part of science, right? So if all this just ends up not working, right? Somebody puts any of these systems to the test and they don't work, then that's fine. Because at least now when somebody's like researching this, they say, okay, well, Denny researched this and he assumed this hypothesis and it didn't work. But that's an important contribution that's been made, because it's a non-reality that you should follow, right? So
yeah, I think what the reason, to clarify, the reason I'm bringing up nonlinear dynamics is that in the Woodward experiment, you know, Jim had we had the drive on a torsion pendulum.
Yeah.
And, you know, the thing would exhibit nonlinear dynamics. So it would have stick-slip behavior and then get unbalanced. And so we got motion. So anytime you have a mechanical system and it starts getting complex and you can get the nonlinear dynamics, that introduces experimental and systematic doubts about what is really going on, right? So if we're trying to say that, okay, there's some exotic or some, you know, non-standard kind of effect, it becomes, when you go in that domain, right, it becomes problematic. So that's kind of the reason I'm pointing it out to you. It's not necessarily that, oh, you know, go learn that stuff. No, it's more like just be aware.
Once you get into chaos math, you can just plot it. Like chaos is deterministic usually.
But what you're saying makes a lot of sense for me, because something that rubs me wrong in the calculations that I did was the two particle system, exactly what you're describing right now, right? So that kind of chaos starts coming out with the conservation, right? And it's not like arbitrary. Like there are other formulations I want to go and do with that particular system and explore again, but it was completely unexpected. Center of mass, how that was supposed to behave was fine. Expected force, expected torque. But what's going on with the energy and what's also going on with the momentum in the way that's supposed to be happening, especially with the Lagrange or the Hamiltonian, even with the Hamiltonian Jacobi, there were some weird things. So just,
The Jacobian wasn't making sense?
No, I mean, I just wouldn't expect to get so for momentum, I wouldn't get the non-conservation of momentum in the way that was being presented there. Energy was fine. There are different ways to like look at that, but it doesn't rub me wrong. It doesn't rub me right. The singlet is fine. The 3-part triplet is fine if you move up with n masses, but that.
So you're saying experimentally you don't get you violate conservation of momentum?
I'm saying when I apply all of this to the simulations, it's just it does weird things. You know. So
okay. Gotcha.
I do have to get going, guys. Something at 5.
You can violate conservation of energy, but not momentum.
Yeah. Well, Denny, thank you for presenting. Thank you.
So you can violate conservation of energy, but not momentum. So
we do it every day.
Okay, so
guys, we understand the parameters of it, but that's okay.
Okay, no. I might actually have that fundamentally like misunderstood, and that's not something I'm going to like. No, I can do this here and here. So that's something to seriously look at there, right? So
Timmy, no, he's listening to you.
So Denny, if you have just one more minute,
sure.
First of all, I really loved your presentation, but your speed is so fucking high; it's very hard to follow. Right? The last one, it was not that complex. Yes, was not that complex of a topic, right? So your speed was okay, but in this one, it was really hard to follow. I'm gonna rewatch it at like 50% or 75% speed.
Okay.
As I understood it, like your artificial gyroscope, it uses topology and phase to organize an inertial confrontation current, which you believe couples to like an external vacuum degree of freedom. And this coupling is not completely clear yet, right? So,
Yeah, so
that's how
it's
I understood it, and that makes sense to me because, like,
Okay.
from Curtis UQFT and also from Heim theory and other advanced theories which go beyond the standard model, like there are exotic couplings that you could tap into, right? Especially if you use topology and phase in an intelligent way.
Right.
So
Yeah.
topology is important, and phase as well. Those two things are very important. Not necessarily saying anything about a field. Everything is just supposed to be kind of like closed box subsystem, so to speak. But yeah, exactly. So yeah. Those are important. Thank you guys for having me. I got to get rolling. So
you.
thank you very much.
Yeah,
Have a great
Denny,
day.
thank you. Thank you so much.
Yes.
Thank you so much. Okay, well, guys, should we do lab updates? Does anybody have lab updates? And if not,
I did,
we can.
but I got told I was fiction.
You're not fiction, true.
Now I worry.
You're
I'm
truer
very
than
worried now.
fiction.
I've seen it with my own eyes. No
Fiction, right?
fiction, just an awesome space.
We're all fiction
coming to
in each
life.
other's minds. We all have like fan fiction about each other in our heads.
Yeah, I got an update. Tim, can I safely do my screen?
Yeah, just do the click the plus button. Yeah, this is different than Zoom, so it should already have permissions.
All right, let's see what happens.
And let me see.
Oh, there we go. Okay.
Yeah, and then it'll add it, and then I have to push a button to add it to the screen. There we go. Hold on. There we go. Okay, add to stage. Perfect.
Okay. I've been in our new facility about a month now, a little under it, and I got to tell you, I envy those who have moved in and gone through the misery of setting their operations back up and are back to playing, real time, because it absolutely crippled our operation for a month. I mean, just nothing got accomplished except moving in and getting the electrical sockets to work. So we finally are back online, and I went ahead and ran a test. And because we still are poor, we're looking to produce a open air demonstrator. Well, open air demonstrators are the absolute bane of ultra high field electrostatics. So I did work out a clever little system, and it's kind of hard to see what you're looking at here, but basically you're looking down on a scale, and on the scale is one of our thruster articles that is tuned to operate in open air. And I got it blurred out, but basically when you turn it on, it starts at 0 milligrams. Those are the tape is over the last little digit because it jumps around too much, but basically that's negative 22 milligrams of thrust. And as you can see, in 1 hour, or it starts at 0, obviously, and at 1 hour, at 6 kV, which is just about the edge of the envelope before you start blowing the thing apart because of the breakdown of air, it was running at around negative 25 milligrams. At about 16 hours, because I wanted to see how it would work overnight, hoping it would pack up a lot more charge, and it didn't. It pretty much topped out at around negative 24, and then after 16 hours of runtime and being disconnected from everything, literally isolated, it was at negative 22, and it stayed at that for the next 12 hours. So we're just continuing to evolve. The nice thing about this particular design is that I can stack these things up as high as I want. So we're working on a slightly lighter weight version of it, but either way, I'm going to put 10 of these things or 20 of these things together, put them in a plastic box, set it on a scale, and hit the button and watch it pull up. And for those of you who have never debunked or tried to debunk a propulsion system, if you can think of a clever way that I can pull up against gravity and it be a fraud, please let me know, because I'm very excited to hear your thoughts on that. We can't figure a way that we're doing it. So we can't figure out a way that our scale is lying to us. But I mean, it could be, but we can't figure it out how. Besides, when you flip this whole thing over, it pushes down. Then you flip it back over and it pulls back up. So that's what we've been up to. We've been Just trudging along. Oh, and we got
Drew?
another podcast next week.
Drew?
Yeah. Yeah.
I have a question for you. Okay. So your stuff is generating constant force and stuff like that, and you turn off the power to it. That's my understanding. Yes?
Mm-hmm. Yes.
Okay. So if something is generating force, okay, it's moving something. So the stuff that it's moving with gets more energy. So you have to have a theory where that energy is coming from.
I do. I know we
Okay, so
know
can you tell
exactly
me?
where it's coming from.
Where?
We're stealing it from God.
Okay, I never met the guy,
No.
so
Here's the deal. If you turn it on, and when you first turn this thing on, and let's say you're running for a minute or so, it would be like -3 or 4 milligrams, maybe -3. And then as you watch for an hour, it slowly sneaks up, -4, -5, 6, 7, 8, 9, 10, 11, 12. And then at about an hour, you can disconnect the power and it still makes thrust. And you say, well, what's going on here? Well, what's going on is that we're taking free charge, which is running around into the metal surfaces. All the metal surfaces that are generating field are generating it with free charge. And we are driving free electrons or free charge into the dielectric in the form of bound charge. And once you drive bound charge into the dielectric, it doesn't have enough reason to sneak back out quickly. It will eventually bleed back out. It will eventually bleed all the way through and dissolve. But for the most part, it ain't going anywhere for weeks on end. So when you cut the power, all the free charge goes right back into the power supply, and that's the end of that story. But the bound charge that has been driven into the materials, that ain't going nowhere.
No,
and it's charge that generates field. And
but look, put your stuff in the vacuum of space. Okay, there's no gravity, so it just moves, starts to move this, and then you keep it on for a week, and it's moving faster and faster.
Yes,
moving faster and faster. It gets
We
more
know.
and more energy. That energy
know.
needs to come from. I'm not saying, but you need to show me where that energy is coming from.
We did. Third order quantum QED, quantum electrodynamics. Charles just got all excited about it. He just cracked the whole. I don't know what he did.
That's great.
Nobody understands his squiggles, but he can show you. He actually did. We did a presentation on it. He can show you where the momentum is coming from out of the QED.
That's
so
great.
I'm really excited to
that.
see the new stuff that Charles did, because currently I think he can't say it for sure, and I think
he
that
can
is
now. He got all.
okay.
I got the text.
That's really
week.
exciting. So
he's all excited.
If he can present on it, or if he would like to send it to me so I could check it, that would be awesome. Because like so far, what makes Exodus so extremely exciting to me is that there is no explanation, right? So you have an experimental setup,
right,
and you have no explanation so far.
Well, we have a pretty good understanding of where it's coming from. I mean, we're definitely getting it out of the whatever it is, the virtual pair, the virtual pairs, and because they're born with whatever. As I understand it, the little virtual pairs that are quadrillions and trillions and trillions of them every nanosecond. They're born with everything they're ever going to have, and then they wink out with everything they're ever going to have, and at somewhere between wink in and wink out,
they carry away momentum.
Steal some of the momentum from them little bitty bits.
So can I ask Charlie a question? Because I would like to know what in his mind is the energy density, because I need that for my theory as well. If he figured that out.
You can ask him anything you want. All you got to do is find him.
Okay.
He takes a lot of vacations. He's very stressed. He works at NASA a lot.
Oh, I haven't
when he isn't
worked
working
at NASA.
at NASA. He's off globe trotting and doing podcasts and just doing other amazing things. But yeah, drop us an email.
But at one point, I would like to know what in his point, what's the vacuum energy density, because you need to explain your behavior.
Okay, I don't know really what vacuum energy density is, but I can try and remember to ask him.
Okay, thank you. I'd appreciate it so much. Thank you.
Well, he's
Yeah.
using QED, so
Oh, it's 1/220.
Yeah.
I'm sorry, that's not the right value of it. I'm sorry.
Oh, that was it. What's that? What's that fine thing?
Fine structure constant.
Yeah, he
Yeah.
figured that out. He can.
Oh, where
he
it's
knows
coming
what,
from?
Yeah.
Oh, great. I'd
Yeah,
like
he was
to
all
know that
excited
too.
about that. Really?
Well,
I don't know what.
so
it,
I should
don't,
ask
actually know
if
what it is.
does
Again,
anybody else
another
have
thing I
lab
don't care
updates?
about.
I want to jump in and make sure. Does anybody else have lab updates, or are we good on those? Curtis, did you have any?
Or... I can read more about Drew's.
No, not this
Okay.
time.
Well, maybe I can pull Drew in the future. I mean, Drew, we can go. Why don't we do this? Why don't we go to open discussion, and then you guys can focus on whatever comes to mind. Whatever comes to mind. It's just about 5 now, so I mean it's Pacific time, about 5 p.m. Pacific. I mean, you want to go? We could either go until 5 or go until 6 or whatever works for you guys.
I just had a question. I just wanted to know where I can read more about Drew's work.
You can't read anything about Drew's work because Drew's work is all make things real. But
Well,
you can read
Gabriel,
an awful lot about Charles's work.
Yeah, there's a lot. Well, there's a lot on alt propulsion on the alt propulsion website. I would say Google it. There are also a ton of YouTube videos, and then Drew like he is at the APEC conference like every time, so he's always doing updates on his stuff. But yeah, I would say Google it. Like
Okay, I was just wondering if you actually write it, if you post it somewhere about your work.
We don't.
Okay, I got you.
We have a website. It's terrible. We
you
now
do?
have an IT department. Well, we don't have an IT department, but we're renting a dude who's a really great IT guy, and he promises us that our website will go from its current really sad state to amazing. It's going to look just like Tim's stuff.
Oh, I hope so then. That's cool. Thank you.
That's what we're working on. But, you
That's
know, we
awesome.
got to solve all the other problems first. We got to get email and something called cybersecurity. You know,
yeah, I feel that.
Really depressing.
No, it'll work out.
Yeah,
It'll
there's
work out.
a lot. There's a lot of
Do you have any
infrastructure.
simple, non-physicky questions that you wish to ask? I'd be
Oh
happy
no,
to.
I was just gonna read it if there was anything. I would just spend a lot of time just reading it. That's what I
We have a
wanted to
patent.
do.
You
Okay,
can read that.
The what?
The patent.
The patent? Oh,
It's
okay.
about 150 pages of good luck.
Well, I'll read at least a few for sure. I would
Okay.
like to, just so I can see it. Yeah,
It's got
that's
pictures.
pretty
I drew them, so I know the pictures are cool. But the rest of it, it's all babble, as far as I can tell. It's theoretically it's real, but you can't build a rocket from it. So you can build a rocket from the pictures. That's why I drew the pictures, so that I knew that you'd be able to do. That way, you'd be able to look at the patent and build a propulsion thing right from the patent.
Gotcha. Thank you.
You don't even have to know how to read to build one. You can just look at the pretty picture and reproduce it. I made a
Gotcha.
video that shows you how.
Oh, you did? Okay, cool.
Yeah.
Cool.
Made
I'll
a
like
great video. That's on our website. I'm not sure our website's operational, but if it does get back online, there's a bunch of videos, and one of them is me showing you how to build a thruster that will
Gotcha.
work, because a bunch of people have built them and sent us pictures of them working.
Yeah, I see. Thank you.
You're welcome. Curtis, did you get your little buzzy thing that goes back and forth? Did you get it to work?
I'm still waiting on the funding to come back. So we gotta once that's hopefully next month I can get started again.
Awesome. Yeah, funding has been a real nightmare.
I still have all the equipment, but that's not what I'm going to be probably doing first. I'm probably going to go back to the Mach-Lorentz thruster instead.
Which one's that?
The Mach-Lorentz thruster is what they used to call the flux capacitor. It's based on a paper Jim did a long time ago. It uses the Lorentz force instead of asymmetric masses. So
is that thing that's got a little disc here and a big disc here, and it looks like a cone?
No.
Yeah, because that was silly.
That's nothing to do with Jim's work.
Okay.
Yeah. So the modular
Dude,
thruster.
You need to draw some pictures and show us what you're doing.
Yeah, what Jim has it in his paper, but it uses the same type of material, piezoelectric material, but you excite it in a certain way where when it has that transient mass happen, you're using the Lorentz force, the electric and the magnetic field to rectify it. So you're able to, and because you're able to determine which direction they're pointing, you can determine the direction of the force. So the thing that's cool about that versus the mega drive is that the mega drive is more or less you're going one direction where you're pointing. You can kind of go the other direction, but the force it's not symmetric in terms of what you can generate. But the MLT you can go either direction, and that's one that because it's electromagnetic in terms of the how the forces ends up coming out, you can scale it up, right? So that's kind of what my plan is to do that experiment next, and hoping to have an experiment. My goal is to have a Newton of force. So that's kind of what
that's what I'm working on next too. I got to go back into vacuum in order to get up to a Newton though.
So, and by the way, I'm kind of curious. We had a few months back that asymmetric. What was it? It was that fractal.
The VEM guy, right?
Yeah. Now I'm wondering, has that been replicated?
The what now?
The VEM.
VEM.
Like, do we know it actually works? Has anyone gone there and seen it? I mean,
Tim, you're muted.
Sorry, David Perez.
Let's start from the beginning. Oh, that's the David Perez thing?
Yeah, I don't think it's been
I wish somebody would go there and let me know if that thing's real or not, because I want to build one bad.
What kind of forces are they claiming they got?
He was saying he got pounds of force out of it.
And he did have, if I remember correctly, he did have a fellow he's collaborating with who replicated it, right? But that's not really an independent third party. That was kind of my take on it.
As far as I can tell, that it was a kid, like an intern, that came to his place, used his equipment and his process, and reproduced a very limited amount of thrust. Well, that's wonderful, that's amazing. But if there was something curious going on with twisting of the wires or straining of the wires or something, in all that RF nightmare, then you ran two tests with the same equipment in the same configuration, and you called it two different things. You called it test one, and then this one supported test one because it was a different test, and it got a great answer. Well, you're using the exact same hardware in the same exact configuration. That's a little bit that's stretching the edge of the envelope for corroborating testing.
Yeah.
So I'm not slamming on the guy. I mean, I sincerely hope it's real. I think the whole flying through the sky and dropping into whatever wormholes and stuff like that, I don't think any of that's right. But I would love for his RF system to be real, because I'm pretty sure I know how it works.
Yeah, he was the fellow that was basing this on lightning storms or something, right?
Yeah, it was a metrological process that set up RF fields in clouds, and it was right at the point where the icing would form, and it was a certain frequency, and it was right in, I don't know, the 100 megahertz range or something. I've never heard of that kind of frequency in clouds, but I'm not a metrologist, so I really don't know.
Hold on, Drew. He was talking about simulation, talking about a machine learning guys and stuff like that. And the guy the student that reproduced this, I mean, we pointed out some basic problems with the setup. Okay, so my understanding of the guy's talk was basically, oh, here's my theory, stuff like that. Here is what my chat GPT or whatever guy tells me I'm correct, and I can build something. But
no, this guy had
physical.
an actual device.
This guy, we're talking about the dude with the V-shaped thing.
It might be a different.
I know,
yeah.
but that was about setup, and that was it, and there was nothing there.
Well,
no, he ran that thing.
Yeah.
There's videos of him running that thing over the years.
Yeah.
And it's like the scale, and he made force. I'm just saying, there was videos of all this. I don't know if it was real or not.
It could be electromagnetic
I'm not
force.
throwing,
like really
I'm not
easily.
throwing scat on the guy. He may have done something amazing. I just really want to know if it's real or not.
But that was my understanding about the talk. He was talking about simulation or AI responses, and the student had a simple thing. So maybe there is something else, I don't know. But that's how I don't know. I'm not judging or anything. That's my understanding. I'm just describing my understanding. That's it.
If somebody tells me that they built something and it worked, and then they checked it with an AI simulation, that's like, I built something and it worked, and everything after that is a pointless exercise in conversation. I don't believe in any of the AI nonsense. I don't think any of it's real. I don't think any of it's right. I think that hallucinating thing and the butt kissing thing that AIs do has eliminated their credibility. But
there's no hallucination, no buts there. It just basically it's correlation. It's a matrix. It's just basically running one mathematical equation, and that's it. And they don't care.
And yet they get that wrong every time. So
and that's the whole point.
I'm not going to worry about it.
It's solving convolution matrix. That's it. Nothing to it.
I just really wish somebody that I believed knew what they were looking at would be able to go and check this guy's stuff out. I mean, I called him up and offered him to go up there and hang with them and check out his setup. And he's like, no. So, it's not going to be me.
Is it Gravelflyer 2.0 or what's?
I don't know. I would love to think this guy has got it. But, making something work and understanding why it works and being able to scale it and reproduce it, and that's a very different set of words.
Yeah.
But I would love to think this guy's got it. I don't know. I hope he does. Because he makes a lot more thrust than we do.
But he was also driving faster than light very quickly. So that's very key.
He was doing some very curious things. He said the dude who was flying was doing some curious things. Don't know. I've put a lot of hours in light aircraft. I've never had anything like that happen. But
yeah.
So,
well, guys, should we keep going for a while, or should we close things down for this evening? It's been a pretty intense day.
I think I actually gotta go. But thank you so much for having me.
Oh yeah,
I think I'm gonna cut out
Gabriel,
too,
thank
Jimmy.
you again.
Yeah,
You're
nice
heading out?
Yeah, but first of all, Mikola, have you got anything in the works? You got anything building?
I am building. I'm moving to torsion balance at the moment, but I have to have some time because I'm busy at work. But I would say within 2 months, I should have some results, and there'll be either, and it's all bullshit, or I'm into something. I know that for sure in 2 months.
Awesome. Well, man, I'm wishing you success.
Thank you. But I mean, I'll let you know soon. Within 2 months, I'll know.
Sweet. Joel, are you doing anything in reality?
Nah, I'm just looking at the crazy nature and national parks in America all over, right? But yeah, I might actually look at some experiments when I'm back in Germany. So as I told you, there's the Gödel Institute in southern Germany, and they collected anti-gravity experiments from Europe from the last 100 years. And yeah, I got a contact there, and I'm trying to go there in person to look at the experiments. And yeah, maybe they have cool stuff to update you about. They have a huge building. They have a lot of funding, so that should be interesting. You will get an update as soon as I'm there.
Cool. Well, I'll be back in touch. I'm gonna get back on the sketches and stuff, trying to figure out what the heck's going on from a
Oh, yes,
guys,
please.
why
Ask
don't we
Charlie
close
about
things?
the energy density.
Why don't we close
if you
things
don't
down
forget.
for today then?
Okay.
Yes, let's do that.
Yeah,
Thank you.
I'm wiped out too. I am wiped out too. It has been
All
back
right.
to back. I mean, it's all good stuff, but just like work, and yeah, we're kicking butt though. Everything is moving forward, right? That's the problem, and then AI on top of it. So it's like everything is moving forward all at once, and it's just like living on coffee and Diet Coke. And that's not. I'm not complaining, but it's like, come on.
Yeah.
But it was a great APEC. Thank you so much for organizing it, Tim. As usual,
Yeah.
you did a great job, and we had very good
Thank you.
speakers.
Yeah, again, this was APEC. It was July 11th, 2026. Thank you to all of you guys. Thank you to our presenters, and thank you for to everybody who has participated in our community.